Hey everyone, welcome to our machine learning full course by Simplilearn. Have you ever thought about how Google finishes your sentences, how Netflix always know what you want to watch, or how chatbots seem to understand what you're saying? That's all made possible through machine learning. And in this course, you will learn all of that, how it works, and how to build smart systems of your own. You might be wondering what makes machine learning so special. Well, it's a big part of how today's technology is getting smarter. From recognizing faces in photos to recommending products online, machine learning is everywhere. It helps computers learn from data and make decisions without being told exactly what to do. By 2025, machine learning will be a must-have skill in industries like healthcare, finance, marketing, and many more. Companies are looking for people who can use machine learning to solve real-world problems and create intelligent solutions. And here's the exciting part. The career growth is huge. In India, machine learning experts can earn anywhere between 10 lakh to 25 lakhs per year, and in the US, it can go beyond $120,000 a year. This course is perfect if you're just starting out. We'll begin with the basics of what machine learning is and then move on to important concepts and techniques that are used in real-world projects. Step by step, you learn how to go from beginner to someone who can confidently work with machine learning. So let's get started on this journey together. Before we commence, if you're interested in launching a high career growth in artificial intelligence and machine learning, this program might be the best thing you'll ever come across. The professionals
Part 1. This is part 1 of a machine learning series put on by Simplilearn. My name is Richard Kirschner. I'm with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. What's in it for you today? Well, we'll start off with a brief explanation of why machine learning and what is machine learning. And then we'll get into a few of the types of machine learning. Machine learning algorithms, linear regression, decision trees, support vector machine, and finally we'll do a use case where we're going to classify whether a recipe is of a cupcake or a muffin using the SVM or the support vector machine. Sounds like a delicious way to explore machine learning. So why machine learning? Why do we even care about having these computers come up and be able to do all these new things for us? Well, because machines can now drive your car for you. It's still very in the infant stage, but it's just exploding, as we see with Google's Waymo, and then Uber had their program, which unfortunately crashed. They know that this is huge. This is going to be the huge industry to change our whole transportation infrastructure. Machine learning is now used to detect over 50 eye diseases. Do you know how amazing that is to have a computer that double checks for the doctor for things they might miss? That's just huge in the health industry. Pretty soon they actually do already have that in some areas where maybe not for eyes, but for other diseases where they're using the camera on your phone to help pre-diagnose before you go in and see the doctor. And because the machine can now unlock your phone with your face. I mean, that's just cool, having it being able to identify your face or your voice and be able to turn stuff on and off for you depending on where you're at and what you need. Talking about an ultimate automation, our world we live in. And as we dig in deeper, we have a nice example of Facebook. As you can see here, they have the Facebook post with Halloween. Comment yes if you want it. Order here. Nobody likes spam posts on Facebook that annoy them into interacting with likes, shares, comments, and other actions. I remember the original ones were all, if you don't click on here, you will have bad luck or some kind of fear factor. Well, this is a huge thing in a social media when people are getting spammed, and so this tactic, known as engagement bait, takes advantage of Facebook's newsfeed algorithm by choosing engagement in order to get the greater reach. To eliminate engagement bait, the company reviewed and categorized hundreds of thousands of posts to train a machine learning model that detects different types of engagement bait. So in this case we're using Facebook, but this is of course across all the different social media. They have different tools they're building, and the Facebook scroll GIF will be replaced. Kind of like a virus coming in there. It notices that there's a certain setup with Facebook and it's able to replace it. And they have like vote baiting, react baiting, share baiting. They have all these are kind of general titles, but there certainly are a lot of ways of baiting you to go in there and click on something. So they fed all this data was fed into the machine, and then they have the new post. The new post comes up, that takes over part of the Facebook setup. And that's what you're looking at. You're looking at this new post that's replaced, like a virus has replaced that. So what Facebook did to eliminate this is they start scanning for keywords and phrases like this and checks the click-through rate. So it starts looking for people who are clicking through it without even looking at it, or clicking through it and it's not something that normally would be clicked through. Once Facebook has scanned for these keywords and phrases, it is now able to identify the spam coming in. And this makes your life easier, so you're not getting spammed. It's not like walking through an airport, and in a lot of countries you have like hundreds of people trying to sell you timeshare. Come join us, sign up for this. It eliminates that annoyingness, so now you can just enjoy your Facebook and your cat pictures, or maybe it's your family pictures. Mine is family. Certainly people like their cat pictures too. Another good example is Google's DeepMind project AlphaGo. A computer program that plays a board game Go has defeated the world's #1 Go player, and I hope I say his name right, Kiji. The ultimate Go challenge game of 3 of 3 was on May 27th, 2017, so it was just last year that this happened. And what makes this so important is that, Go is a game, so it's not like you're driving a car or something in our real world, but they are using games to learn how to get the machine learning program to learn. They want it to learn how to learn. And that is a huge step. A lot of this is still in its infant stage as far as development, as we saw what happened with the, as I referred to earlier, the Uber cars. They lost their whole division because they jumped ahead too fast. So it's still an infant stage, but boy, is this like the beginning of just an amazing world that is automated in ways we can't even imagine what tomorrow's going to look like. We've looked at a lot of examples of machine learning, so let's see if we can give a little bit more of a concrete definition. What is machine learning? Machine learning is the science of making computers learn and act like humans by feeding data and information without being explicitly programmed. And we see here we have a nice little diagram where we have our ordinary system. Your computer, nowadays you can even run a lot of this stuff on a cell phone because cell phones have advanced so much. And then with artificial intelligence and machine learning, it now takes the data and it learns from what happened before. And then it predicts what's going to come next. And then really the biggest part right now in machine learning that's going on is it improves on that. How do we find a new solution? So we go from descriptive, where it's learning about stuff and understanding how it fits together, to predicting what it's going to do, to post-scripting, coming up with a new solution. And when we're working on machine learning, there's a number of different diagrams that people have posted for what steps to go through. A lot of it might be very domain specific. So if you're working on photo identification versus language versus medical or physics, some of these are switched around a little bit or new things are put in. They're very specific to the domain. This is kind of a very general diagram. First, you want to define your objective. Very important to know what it is you're wanting to predict. Then you're going to be collecting the data. So once you've defined an objective, you need to collect the data that matches. You spend a lot of time in data science collecting data, and the next step, preparing the data. You got to make sure that your data is clean going in. There's the old saying, bad data in, bad answer out, or bad data out. And then once you've gone through and we've cleaned all this stuff coming in, then you're going to select the algorithm. Which algorithm are you going to use? You're going to train that algorithm. In this case, I think we're going to be working with SVM, the support vector machine. Then you have to test the model. Does this model work? Is this a valid model for what we're doing? And then once you've tested it, you want to run your prediction. You want to run your prediction or your choice or whatever output it's going to come up with. And then once everything is set and you've done lots of testing, then you want to go ahead and deploy the model. And remember I said domain specific. This is very general as far as the scope of doing something. A lot of models, you get halfway through and you realize that your data is missing something and you have to go collect new data because you've run a test in here someplace along the line. You're saying, hey, I'm not really getting the answers I need. So there's a lot of things that are domain specific that become part of this model. This is a very general model, but it's a very good model to start with. And we do have some basic divisions of what machine learning does that's important to know. For instance, do you want to predict a category? Well, if you're categorizing things, that's classification. For instance, whether the stock price will increase or decrease. So in other words, I'm looking for a yes-no answer. Is it going up or is it going down? And in that case, we'd actually say, is it going up? True. If it's not going up, it's false, meaning it's going down. This way, it's a yes-no, 0, 1. Do you want to predict a quantity? That's regression. So remember, we just did classification. Now we're looking at regression. These are the two major divisions in what data is doing. For instance, predicting the age of a person based on the height, weight, health, and other factors. So based on these different factors, you might guess how old a person is. And then there are a lot of domain-specific things, like do you want to detect an anomaly? That's anomaly detection. This is actually very popular right now. For instance, you want to detect money withdrawal anomalies. You want to know when someone's making a withdrawal that might not be their own account. We've actually brought this up because this is really big right now. If you're predicting the stock, whether to buy stock or not, you want to be able to know if what's going on in the stock market is an anomaly. Use a different prediction model because something else is going on. You got to pull out new information in there. Or is this just the norm? I'm going to get my normal return on my money invested. So being able to detect anomalies is very big in data science these days. Another question that comes up, which is on what we call untrained data, is do you want to discover structure in unexplored data? And that's called clustering. For instance, finding groups of customers with similar behavior given a large database of customer data containing their demographics and past buying records. And in this case, we might notice that anybody who's wearing a certain set of shoes goes shopping at certain stores, or whatever it is, they're going to make certain purchases. By having that information, it helps us to market or group people together so that we can now explore that group and find out what it is we want to market to them if you're in the marketing world. And that might also work in just about any arena. You might want to group people together, whether they're based on their different areas and investments and financial background, whether you're going to give them a loan or not. Before you even start looking at whether they're a valid customer for the bank, you might want to look at all these different areas and group them together based on unknown data. So you don't know what the data is going to tell you, but you want to cluster people together that come together. Let's take a quick detour for quiz time. Oh, my favorite. So we're going to have a couple questions here under quiz time. And we'll be posting the answers in the part 2 of this tutorial. So let's go ahead and take a look at these quiz times questions, and hopefully you'll get them all right, and it'll get you thinking about how to process data and what's going on. Can you tell what's happening in the following cases? Of course, you're sitting there with your cup of coffee, and you have your checkbox and your pen trying to figure out what's your next step in your data science analysis. So the first one is grouping documents into different categories based on the topic and content of each document. Very big these days. You have legal documents, you have maybe it's a sports group documents, maybe you're analyzing newspaper postings, but certainly having that automated is a huge thing in today's world. B, identifying handwritten digits in images correctly. So we want to know whether they're writing an A or capital A, B, C. What are they writing out in their handwriting? C, behavior of a website indicating that the site is not working as designed. D, predicting salary of an individual based on his or her years of experience. Boy, HR hiring setup there. So stay tuned for part 2. We'll go ahead and answer these questions when we get to the part 2 of this tutorial. Or you can just simply write at the bottom and send a note to Simplilearn, and they'll follow up with you on it. Back to our regular content. And these last few bring us into the next topic, which is another way of dividing our types of machine learning, and that is with supervised, unsupervised, and reinforcement learning. Supervised learning is a method used to enable machines to classify, predict objects, problems, or situations based on labeled data fed to the machine. And in here you see we have a jumble of data with circles, triangles, and squares, and we label them. We have what's a circle, what's a triangle, what's a square, and we have our model training, and it trains it so we know the answer. Very important, when you're doing supervised learning, you already know the answer to a lot of your information coming in. So you have a huge group of data coming in, and then you have new data coming in. So we've trained our model. The model now knows the difference between a circle, a square, a triangle. And now that we've trained it, we can send in this case, a square and a circle goes in, and it predicts that the top one's a square and the next one's a circle. And you can see that this is being able to predict whether someone's going to default on a loan, because I was talking about banks earlier. Supervised learning on stock market, whether you're going to make money or not. That's always important. And if you are looking to make a fortune in the stock market, keep in mind it is very difficult to get all the data correct on the stock market. It is it fluctuates in ways really hard to predict. So it's quite a roller coaster ride. If you're running machine learning on the stock market, you start realizing you really have to dig for new data. So we have supervised learning. And if you have supervised, we should need unsupervised learning. In unsupervised learning, machine learning model finds the hidden pattern in an unlabeled data. So in this case, instead of telling it what the circle is, and what a triangle is, and what a square is, it goes in there and looks at them and says, for whatever reason, it groups them together. Maybe it'll group it by the number of corners. And it notices that a number of them all have 3 corners, a number of them all have 4 corners, and a number of them all have no corners. And it's able to filter those through and group them together. We talked about that earlier with looking at a group of people who are out shopping. We want to group them together to find out what they have in common. And of course, once you understand what people have in common, maybe you have one of them who's a customer at your store, or you have 5 of them are customer at your store, and they have a lot in common with 5 others who are not customers at your store. How do you market to those 5 who aren't customers at your store yet? They fit the demographics of who's going to shop there, and you'd like them to shop at your store, not the one next door. Of course, this is a simplified version. You can see very easily the difference between a triangle and a circle, which might not be so easy in marketing. Reinforcement learning. Reinforcement learning is an important type of machine learning where an agent learns how to behave in an environment by performing actions and seeing the result. And we have here where in this case, a baby. It's actually great that they used an infant for this slide because the reinforcement learning is very much in its infant stages. But it's also probably the biggest machine learning demand out there right now, or in the future. It's going to be coming up over the next few years, is reinforcement learning and how to make that work for us. And you can see here where we have our action. In the action in this one, it goes into the fire. Hopefully the baby didn't, it was just a little candle, not a giant fire pit like it looks like here. When the baby comes out, and the new state is the baby is sad and crying because they got burned on the fire. And then maybe they take another action. The baby's called the agent because it's the one taking the actions. And in this case, they didn't go into the fire. They went a different direction, and now the baby's happy and laughing and playing. Reinforcement learning is very easy to understand because that's how, as humans, that's one of the ways we learn. We learn whether it is, you burn yourself on the stove, don't do that anymore. Don't touch the stove. In the big picture, being able to have a machine learning program or an AI be able to do this is huge because now it's starting to learn how to learn. That's a big jump in the world of computer and machine learning. And we're going to go back and just kind of go back over supervised versus unsupervised learning. Understanding this is huge because this is going to come up in any project you're working on. We have in supervised learning, we have labeled data, we have direct feedback. So someone's already gone in there and said, yes, that's a triangle. No, that's not a triangle. And then you predict an outcome. So you have a nice prediction. This new set of data is coming in and we know what it's going to be. And then with unsupervised training, it's not labeled. So we really don't know what it is. There's no feedback. So we're not telling it whether it's right or wrong. We're not telling it whether it's a triangle or a square. We're not telling it to go left or right. All we do is we're finding hidden structure in the data, grouping the data together to find out what connects to each other. And then you can use these together. So imagine you have an image and you're not sure what you're looking for. So you go in and you have the unstructured data, find all these things that are connected together. And then somebody looks at those and labels them. Now you can take that labeled data and program something to predict what's in the picture. So you can see how they go back and forth and you can start connecting all these different tools together to make a bigger picture. There are many interesting machine learning algorithms. Let's have a look at a few of them. Hopefully this gives you a little flavor of what's out there. And these are some of the most important ones that are currently being used. We'll take a look at linear regression, decision tree, and the support vector machine. Let's start with a closer look at linear regression. Linear regression is perhaps one of the most well-known and well-understood algorithms in statistics and machine learning. Linear regression is a linear model. For example, a model that assumes a linear relationship between the input variables x and the single output variable y. And you'll see this if you remember from your algebra classes, y equals mx plus c. Imagine we are predicting distance traveled y from speed x. Our linear regression model representation for this problem would be y equals m times x plus c, or distance equals m times speed plus c, where m is the coefficient and c is the y-intercept. And we're going to look at two different variations of this. First, we're going to start with time is constant. And you can see we have a bicyclist. He's got his safety gear on, thank goodness. Speed equals 10 meters per second. And so over a certain amount of time, his distance equals 36 kilometers. We have a second bicyclist who's going twice the speed, or 20 meters per second. And you can guess if he's going twice the speed and time is a constant, then he's going to go twice the distance. And that's easily to compute. 36 times 2, you get 72 kilometers. And so if you had the question of how fast would somebody who's going 3 times that speed, or 30 meters per second is, you can easily compute the distance in our head. We can do that without needing a computer. But we want to do this for more complicated data. So it's kind of nice to compare the two. But let's just take a look at that and what that looks like in a graph. So in a linear regression model, we have our distance to the speed, and we have our m equals the VE slope of the line. And we'll notice that the line has a plus slope. And as the speed increases, distance also increases, hence the variables have a positive relationship. And so your speed of the person, which equals y equals mx plus c, distance traveled in a fixed interval of time, and we could very easily compute, either following the line or just knowing it's 3 times 10 meters per second, that this is roughly 102 kilometers distance that this third bicyclist has traveled. One of the key definitions on here is positive relationship. So the slope of the line is positive. As distance increase, so does speed increase. Let's take a look at our second example where we put distance is a constant. So we have speed equals 10 meters per second. They have a certain distance to go, and it takes them 100 seconds to travel that distance. And we have our second bicyclist who's still doing 20 meters per second. Since he's going twice the speed, we can guess that he'll cover the distance in about half the time, 50 seconds. And of course you could probably guess on the third one, 100 divided by 30, since he's going 3 times the speed, you could easily guess that this is 33.333 seconds time. When we put that into a linear regression model or a graph, if the distance is assumed to be constant, let's see the relationship between speed and time. And as time goes up, the amount of speed to go that same distance goes down. So now your m equals a minus VE slope of the line. As the speed increases, time decreases, hence the variable has a negative relationship. Again, there's our definition, positive relationship and negative relationship dependent on the slope of the line. And with a simple formula like this, and even a significant amount of data, let's see what the mathematical implementation of linear regression. And we'll take this data. So suppose we have this data set where we have x, y, x equals 1, 2, 3, 4, 5, standard series, and the y value is 3, 2, 2, 4, 3. When we take that and we go ahead and plot these points on a graph, you can see there's kind of a nice scattering, and you could probably eyeball a line through the middle of it. But we're going to calculate that exact line for linear regression. And the first thing we do is we come up here and we have the mean of xi. And remember, mean is basically the average. So we added 5 plus 4 plus 3 plus 2 plus 1 and divide by 5. And that simply comes out as 3. And then we'll do the same for y. We'll go ahead and add up all those numbers and divide by 5. And we end up with the mean value of y of I equals 2.8. Where the xi references it's an average or means value, and the yi also equals a means value of y. And when we plot that, you'll see that we can put in the y equals 2.8 and the x equals 3 in there on our graph. We kind of gave it a little different color so you could sort it out with the dashed lines on it. And it's important to note that when we do the linear regression model should go through that dot. Now let's find our regression equation to find the best fit line. Remember, we go ahead and take our y equals mx plus c, so we're looking for m and c. So to find this equation for our data, we need to find our slope of m and our coefficient of c. And we have y equals mx plus c, where m equals the sum of x minus x average times y minus y average, or y means and x means, over the sum of x minus x means squared. That's how we get the slope of the value of the line. And we can easily do that by creating some columns here where we have x, y. Computers are really good about iterating through data, and so we can easily compute this and fill in a graph of data. And in our graph, you can easily see that if we have our x value of 1, and if you remember the xi, or the means value, is 3, 1 minus 3 equals a negative 2, and 2 minus 3 equals a negative 1, so on and so forth. And we can easily fill in the column of x minus xi, y minus yi, and then from those we can compute x minus xi squared and x minus xi times y minus yi. And you can guess it that the next step is to go ahead and sum the different columns for the answers we need. So we get a total of 10 for our x minus xi squared and a total of 2 for x minus xi times y minus yi. And we plug those in, we get 2/10, which equals 0.2. So now we know the slope of our line equals 0.2. So we can calculate the value of c. That'd be the next step, is we need to know where it crosses the y-axis. And if you remember, I mentioned earlier that the linear regression line has to pass through the means value, the one that we showed earlier. We can just flip back up there to that graph, and you can see right here, there's our means value, which is 3, x equals 3 and y equals 2.8. And since we know that value, we can simply plug that into our formula, y equals 0.2x plus c. So we plug that in, and we get 2.8 equals 0.2 times 3 plus c, and you can just solve for c. So now we know that our coefficient equals 2.2. And once we have all that, we can go ahead and plot our regression line. Y equals 0.2 times x plus 2.2. And then from this equation, we can compute new values. So let's predict the values of y using x equals 1, 2, 3, 4, 5 and plot the points. Remember, the 1, 2, 3, 4, 5 was our original x values. So now we're going to see what y thinks they are, not what they actually are. And when we plug those in, we get y of designated with y of p. You can see that x equals 1 equals 2.4, x equals 2 equals 2.6, and so on and so on. So we have our y predicted values of what we think it's going to be when we plug those numbers in. And when we plot the predicted values along with the actual values, we can see the difference. And this is one of the things that's very important with linear regression in any of these models, is to understand the error. And so we can calculate the error on all of our different values. And you can see over here we plotted x and y predict. And we draw in a little line so you can sort of see what the error looks like there between the different points. So our goal is to reduce this error. We want to minimize error value on our linear regression model. Minimizing the distance. There are lots of ways to minimize the distance between the line and the data points, like sum of squared errors, sum of absolute errors, root mean square error, etc. We keep moving this line through the data points to make sure the best fit line has the least square distance between the data points and the regression line. So to recap with a very simple linear regression model, we first figure out the formula of our line through the middle, and then we slowly adjust the line to minimize the error. Keep in mind, this is a very simple formula. The math gets, even though the math is very much the same, it gets much more complex as we add in different dimensions. So this is only 2 dimensions, y equals mx plus c, but you can take that out to x, z, I, j, q, all the different features in there, and they can plot a linear regression model on all of those using the different formulas to minimize the error. Let's go ahead and take a look at decision trees, a very different way to solve problems in the linear regression model. Decision tree is a tree-shaped algorithm used to determine a course of action. Each branch of a tree represents a possible decision, occurrence, or reaction. We have data which tells us if it is a good day to play golf. And if we were to open this data up in a general spreadsheet, you can see we have the outlook, whether it's rainy, overcast, sunny, temperature, hot, mild, cool, humidity, windy, and did I like to play golf that day, yes or no? So we're taking a census. And certainly I wouldn't want a computer telling me when I should go play golf or not. But you can imagine if you got up in the night before, you're trying to plan your day, and it comes up and says tomorrow would be a good day for golf for you in the morning and not a good day in the afternoon or something like that. This becomes very beneficial, and we see this in a lot of applications coming out now where it gives you suggestions and lets you know what would fit the match for you for the next day or the next purchase or the next whatever, next meal out. In this case, is tomorrow a good day for playing golf based on the weather coming in? And so we come up and let's determine if you should play golf when the day is sunny and windy. So we found out the forecast tomorrow is going to be sunny and windy. And suppose we draw our tree like this. We're going to have our humidity, and then we have our normal, which is if you have a normal humidity, you're going to go play golf. And if the humidity is really high, then we look at the outlook. And if the outlook is sunny, overcast, or rainy, it's going to change what you choose to do. So if you know that it's a very high humidity and it's sunny, you're probably not going to play golf because you're going to be out there miserable, fighting off the mosquitoes that are out joining you to play golf with you. Maybe if it's rainy, you probably don't want to play in the rain. But if it's slightly overcast and you get just the right shadow, that's a good day to play golf and be outside, out on the green. Now in this example, you can probably make your own tree pretty easily because it's a very simple set of data going in. But the question is, how do you know what to split? Where do you split your data? What if this is much more complicated data where it's not something that you would particularly understand? Like studying cancer, they take about 36 measurements of the cancerous cells And then each one of those measurements represents how bulbous it is, how extended it is, how sharp the edges are. Something that as a human we would have no understanding of. So how do we decide how to split that data up? And is that the right decision tree? So that's a question that's going to come up. Is this the right decision tree? For that, we should calculate entropy and information gain. Two important vocabulary words there are the entropy and the information gain. Entropy. Entropy is a measure of randomness or impurity in the data set. Entropy should be low, so we want the chaos to be as low as possible. We don't want to look at it and be confused by the images or what's going on there with mixed data. And the information gain, it is a measure of decrease in entropy after the data set is split, also known as entropy reduction. Information gain should be high, so we want our information that we get out of the split to be as high as possible. Let's take a look at entropy from the mathematical side. In this case, we're going to denote entropy as I of P of and N, where P is the probability that you're going to play a game of golf, and N is the probability where you're not going to play the game of golf. Now, you don't really have to memorize these formulas. There's a few of them out there depending on what you're working with. But it's important to note that this is where this formula is coming from, so when you see it, you're not lost when you're running your programming, unless you're building your own decision tree code in the back. And we simply have a log squared of P over P plus N minus N over P plus N times the log squared of N of P plus N. But let's break that down and see what it actually looks like when we're computing that from the computer script side. Entropy of a target class of the data set is the whole entropy. So we have entropy play golf. And when we look at this, if we go back to the data, you can simply count how many yeses and no in our complete data set for playing golf days. In our complete set, we find we have 5 days we did play golf and 9 days we did not play golf. And so our I equals, if you add those together, 9 plus 5 is 14. And so our I equals 5 over 14 and 9 over 14. That's our P and N values that we plug into that formula. And you can go to 5 over 14 equals 0.36, 9 over 14 equals 0.64. And when you do the whole equation, you get the minus 0.36 log root squared of 0.36 minus 0.64 log squared root of 0.64. And we get a set value. We get 0.94. So we now have a full entropy value for the whole set of data that we're working with. And we want to make that entropy go down. And just like we calculated the entropy out for the whole set, we can also calculate entropy for playing golf and the outlook. Is it going to be overcast or rainy or sunny? And so when we look at the entropy, we have P of sunny times E of 3 of 2. And that just comes out how many sunny days yes and how many sunny days no over the total, which is 5. Don't forget to put we'll divide that 5 out later on. Equals P overcast equals 4 comma 0 plus rainy equals 2 comma 3. And then when you do the whole setup, we have 5 over 14. Remember I said there was a total of 5? 5 over 14 times the I of 3 of 2 plus 4 over 14 times the 4 comma 0 and 514 over I of 2, 3. And so we can now compute the entropy of just the part that has to do with the forecast. And we get 0.693. Similarly, we can calculate the entropy of other predictors like temperature, humidity, and wind. And so we look at the gain outlook. How much are we going to gain from this? Entropy play golf minus entropy play golf outlook. And we can take the original 0.94 for the whole set minus the entropy of just the rainy day and temperature, and we end up with a gain of 0.247. So this is our information gain. Remember, we define entropy and we define information gain. The higher the information gain, the lower the entropy, the better. The information gain of the other 3 attributes can be calculated in the same way. So we have our gain for temperature equals 0.029. We have our gain for humidity equals 0.152, and our gain for a windy day equals 0.048. And if you do a quick comparison, you'll see the 0.247 is the greatest gain of information, so that's the split we want. Now let's build the decision tree. So we have the outlook. Is it going to be sunny, overcast, or rainy? That's our first split because that gives us the most information gain. And we can continue to go down the tree using the different information gains with the largest information. We can continue down the nodes of the tree where we choose the attribute with the largest information gain as the root node and then continue to split each subnode with the largest information gain that we can compute. And although it's a little bit of a tongue twister to say all that, you can see that it's a very easy to view visual model. We have our outlook, we split it 3 different directions. If the outlook is overcast, we're going to play. And then we can split those further down if we want. So if the outlook is sunny, but then it's also windy, if it's windy, we're not going to play. If it's not windy, we'll play. So we can easily build a nice decision tree to guess what we would like to do tomorrow and give us a nice recommendation for the day. So we want to know if it's a good day to play golf when it's sunny and windy. Remember the original question that came out? Tomorrow's weather report is sunny and windy. You can see by going down the tree, we go outlook sunny, outlook windy. We're not going to play golf tomorrow. So our little smartwatch pops up and says, I'm sorry, tomorrow's not a good day for golf. It's going to be sunny and windy. And if you're a huge golf fan, you might go, uh-oh, it's not a good day to play golf. We can go in and watch a golf game at home. So we'll sit in front of the TV instead of being out playing golf in the wind. Now that we looked at our decision tree, let's look at the third one of our algorithms we're investigating. Support vector machine. Support vector machine is a widely used classification algorithm. The idea of support vector machine is simple. The algorithm creates a separation line which divides the classes in the best possible manner. For example, dog or cat, disease or no disease. Suppose we have a labeled sample data which tells height and weight of males and females. A new data point arrives and we want to know whether it's going to be a male or a female. So we start by drawing a line. We draw decision lines, but if we consider decision line 1, then we will classify the individual as a male. And if we consider decision line 2, then it will be a female. So you can see this person kind of lies in the middle of the two groups, so it's a little confusing trying to figure out which line they should be under. We need to know which line divides the classes correctly, but how? The goal is to choose a hyperplane, and that is one of the key words they use when we talk about support vector machines. Choose a hyperplane with the greatest possible margin between the decision line and the nearest point within the training set. So you can see here we have our support vector, we have the 2 nearest points to it, and we draw a line between those 2 points. And the distance margin is the distance between the hyperplane and the nearest data point from either set. So we actually have a value, and it should be equally distant between the 2 points that we're comparing it to. When we draw the hyperplanes, we observe that line 1 has a maximum distance. So we observe that line 1 has a maximum distance margin, so we'll classify the new data point correctly. And our result on this one is going to be that the new data point is male. One of the reasons we call it a hyperplane versus a line is that a lot of times we're not looking at just weight and height. We might be looking at 36 different features or dimensions. And so when we cut it with a hyperplane, it's more of a 3-dimensional cut in the data, or multi-dimensional. It cuts the data a certain way. And each plane continues to cut it down until we get the best fit or match. Let's understand this with the help of an example. Problem statement. I always start with a problem statement when you're going to put some code together. We're going to do some coding now. Classifying muffin and cupcake recipes using support vector machines. So the cupcake versus the muffin. Let's have a look at our data set. And we have the different recipes here. We have a muffin recipe that has so much flour. I'm not sure what measurement 55 is in, but it has 55, maybe it's ounces? But it has a certain amount of flour, a certain amount of milk, sugar, butter, egg, baking powder, vanilla, and salt. And so based on these measurements, we want to guess whether we're making a muffin or a cupcake. And you can see in this one, we don't have just 2 features. We don't just have height and weight as we did before between the male and female. In here, we have a number of features. In fact, in this, we're looking at 8 different features to guess whether it's a muffin or a cupcake. What's the difference between a muffin and a cupcake? Turns out muffins have more flour, while cupcakes have more butter and sugar. So basically the cupcake's a little bit more of a dessert, where the muffin's a little bit more of a fancy bread. But how do we do that in Python? How do we code that to go through recipes and figure out what the recipe is? And I really just want to say cupcakes versus muffins, like some big professional wrestling thing. Before we start in our cupcakes versus muffins, we are going to be working in Python. There's many versions of Python, many different editors. That is one of the strengths and weaknesses of Python, is it just has so much stuff attached to it, and it's one of the more popular data science programming packages you can use. In this case, we're going to go ahead and use Anaconda and Jupyter Notebook. The Anaconda Navigator has all kinds of fun tools. Once you're into the Anaconda Navigator, you can change environments. I actually have a number of environments on here. We'll be using Python 3.6 environment. So this is in Python version 3.6. Although it doesn't matter too much which version you use. I usually try to stay with the 3x because they're current, unless you have a project that's very specifically in version 2x. 2.7 I think is usually what most people use in the version 2. And then once we're in our Jupyter Notebook editor, I can go up and create a new file. And we'll just jump in here. In this case, we're doing SVM muffin versus cupcake. And then let's start with our packages for data analysis. And we almost always use there's a few very standard packages we use. We use import numpy, that's for number Python. And they usually denote it as NP, that's very common. And then we're going to import pandas as PD. And numpy deals with number arrays. There's a lot of cool things you can do with the numpy setup as far as multiplying all the values in an array, in a numpy array, data array. Pandas, I can't remember if we're using it actually in this data set. I think we do as an import. It makes a nice data frame. And the difference between a data frame and a numpy array is that a data frame is more like your Excel spreadsheet. You have columns, you have indexes, so you have different ways of referencing it, easily viewing it, and there's additional features you can run on a data frame. And Pandas kind of sits on numpy, so you need them both in there. And then finally, we're working with the support vector machine. So from sklearn, we're going to use the sklearn model, import SVM, support vector machine. And then as a data scientist, you should always try to visualize your data. Some data obviously is too complicated or doesn't make any sense to the human. But if it's possible, it's good to take a second look at it so that you can actually see what you're doing. Now for that, we're going to use two packages. We're going to import matplotlibary.pyplot as PLT. Again, very common. And we're going to import Seaborn as SNS. And we'll go ahead and set the font scale in the SNS right in our import line. That's what this semicolon followed by a line of data. We're going to set the SNS. And these are great because the Seaborn sits on top of matplotlibary, just like Pandas sits on numpy. So it adds a lot more features and uses and control. We're obviously not going to get into matplotlibary and Seaborn. That'd be its own tutorial. We're really just focusing on the SVM, the support vector machine from sklearn. And since we're in Jupyter Notebook, we have to add a special line in here for our matplotlibary. And that's your percentage sign or ampersand matplotlibary in line. Now, if you're doing this in just a straight code project, a lot of times I use like Notepad++, and I'll run it from there. You don't have to have that line in there because it'll just pop up as its own window on your computer, depending on how your computer's set up. Because we're running this in the Jupyter Notebook as a browser setup, this tells it to display all of our graphics right below on the page. So that's what that line is for. I remember the first time I ran this, I didn't know that, and I had to go look that up years ago. It was quite a headache. So matplotlibary inline is just because we're running this on the web setup. And we can go ahead and run this, make sure all our modules are in. They're all imported, which is great. If you don't have them import, you'll need to go ahead and pip, use the PIP or however you do it. There's a lot of other install packages out there, although pip is the most common. And you have to make sure these are all installed on your Python setup. The next step, of course, is we got to look at the data. You can't run a model for predicting data if you don't have actual data. So to do that, let me go ahead and open this up and take a look. And we have our cupcakes versus muffins. And it's a CSV file, or .csv, meaning that it's comma-separated variable. And it's going to open it up in a nice spreadsheet for me. And you can see up here we have the type. We have muffin, 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 cupcake, cupcake, cupcake. And then it's broken up into flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. So what we can do is we can go ahead and look at this data also in our Python. Let us create a variable recipes equals, we're going to use our pandas module, .read CSV. Remember, it's a comma-separated variable. And the file name happened to be cupcakes versus muffins. Oops, I got double brackets there. Do it this way. There we go. Cupcakes versus muffins. Because the program I loaded, or the place I saved this particular Python program is in the same folder, we can get by with just the file name. But remember, if you're storing it in a different location, you have to also put down the full path on there. And then because we're in pandas, we're going to go ahead and you can actually, inline you can do this, but let me do the full print. You can just type in recipes.head in the Jupyter Notebook. But if you're running in code in a different script, you need to go ahead and type out the whole print recipes.head. And pandas knows that that's going to do the first 5 lines of data. And if we flip back on over to the spreadsheet where we opened up our CSV file, you can see where it starts on line 2. This one calls it 0, and then 2, 3, 4, 5, 6 is going to match. Go and close that out because we don't need that anymore. And it always starts at 0. And it automatically indexes it since we didn't tell it to use an index in here. So that's the index number for the left-hand side. And it automatically took the top row as labels. So pandas using it to read a CSV is just really slick and fast. One of the reasons we love our pandas. Not just because they're cute and cuddly teddy bears. And let's go ahead and plot our data. And I'm not going to plot all of it. I'm just going to plot the sugar and flour. Now obviously you can see where they get really complicated if we have tons of different features. And so you'll break them up and maybe look at just 2 of them at a time to see how they connect. And to plot them, we're going to go ahead and use Seaborn. So that's our SNS. And the command for that is sns.lmplot. And then the 2 different variables I'm going to plot is flour and sugar. Data equals recipes. The hue equals type. And this is a lot of fun because it knows that this is pandas coming in. So this is one of the powerful things about pandas mixed with Seaborn and doing graphing. And then we're going to use a palette set 1. There's a lot of different sets in there. You can go look them up for Seaborn. We'll do a fit regular equals false, so we're not really trying to fit anything. And it's a scatter, KWS. A lot of these settings you can look up in Seaborn. Half of these you could probably leave off when you run them. Somebody played with this and found out that these were the best settings for doing a Seaborn plot. And let's go ahead and run that. And because it does it inline, it just puts it right on the page. And you can see right here that just based on sugar and flour alone, there's a definite split. And we use these models because you can actually look at it and say, hey, if I drew a line right between the middle of the blue dots and the red dots, we'd be able to do an SVM and a hyperplane right there in the middle. Then the next step is to format or process our data. And we're going to break that up into 2 parts. We need a type label, and remember we're going to decide whether it's a muffin or a cupcake. Well, a computer doesn't know muffin or cupcake, it knows 0 and 1. So what we're going to do is we're going to create a type label, and from this we'll create a numpy array np where, and this is where we can do some logic. We take our recipes from our panda, and wherever type equals muffin, it's going to be 0. And then if it doesn't equal muffin, which is cupcakes, it's going to be 1. So we create our type label. This is the answer. So when we're doing our training model, remember we have to have a training data. This is what we're going to train it with, is that it's 0 or 1. It's a muffin or it's not. And then we're going to create our recipe features. And if you remember correctly from right up here, the first column is type. So we really don't need the type column because that's our muffin or cupcake. And in pandas, we can easily sort that out. We take our value recipes dot columns. That's a pandas function built into pandas. Dot values, converting them to values. So it's just the column titles going across the top. And we don't want the first one. So what we do is, since it always starts at 0, we want 1 colon till the end. And then we want to go ahead and make this a list, and this converts it to a list of strings. And then we can go ahead and just take a look and see what we're looking at for the features. Make sure it looks right. Let me go ahead and run that. And I forgot the S on recipes, so we'll go ahead and add the S in there and then run that. And we can see we have flour, milk, sugar, butter, egg, baking powder, vanilla, and salt. And that matches what we have up here, right where we printed out everything but the type. So we have our features and we have our label. Now, the recipe features is just the titles of the columns, and we actually need the ingredients. And at this point, we have a couple options. One, we could run it over all the ingredients. And when you're doing this, usually you do. But for our example, we want to limit it so you can easily see what's going on. Because if we did all the ingredients, we have, that's what, 7, 8 different hyperplanes that would be built into it. We only want to look at one so you can see what the SVM is doing. And so we'll take our recipes and we'll do just flour and sugar. Again, you can replace that with your recipe features and do all of them, but we're going to do just flour and sugar, and we're going to convert that to values. We don't need to make a list out of it because it's not string values. These are actual values on there. And we can go ahead and just print ingredients, and you can see what that looks like. And so we have just the amount of flour and sugar, just the two sets of plots. And just for fun, let's go ahead and take this over here and take our recipe features. And so if we decided to use all the recipe features, you'll see that it makes a nice column of different data. So it just strips out all the labels and everything, and we just have just the values. But because we want to be able to view this easily in a plot later on, we'll go ahead and take that and just do flour and sugar. And we'll run that, and you'll see it's just the two columns. So the next step is to go ahead and fit our model. We'll go ahead and just call it model. And it's a SVM. We're using a package called SVC. In this case, we're going to go ahead and set the kernel equals linear. So it's using a specific setup on there. And if we go to the reference on their website for the SVM, you'll see that there's 8 of them here. 3 of them are for regression. 3 are for classification. The SVC, support vector classification, is probably one of the most commonly used. And then there's also one for detecting outliers, and another one that has to do with something a little bit more specific on the model. But SVC and SVR are the 2 most commonly used, standing for support vector classifier and support vector regression. Remember, regression is an actual value, a float value or whatever you're trying to work on. And SVC is a classifier, so it's a yes, no, true, false. But for this, we want to know 0, 1, muffin, cupcake. We go ahead and create our model. And once we have our model created, we're going to do model.fit. And this is very common, especially in the sklearn. All their models are followed with the fit command. And what we put into the fit, what we're training with it, is we're putting in the ingredients, which in this case we limited to just flour and sugar. And the type label, is it a muffin or a cupcake? Now, in more complicated data science series, you'd want to split into, we won't get into that today, we split it into training data and test data. And they even do something where they split it into thirds, where a third is used for, where you switch between which one's training and test. There's all kinds of things that go into that, and it gets very complicated when you get to the higher end. Not overly complicated, just an extra step which we're not going to do today because this is a very simple set of data. And let's go ahead and run this, and now we have our model fit. And I got an error here, so let me fix that real quick. It's capital SVC, it turns out. I did it lowercase. Support vector classifier. There we go. Let's go ahead and run that. And you'll see it comes up with all this information that it prints out automatically. These are the defaults of the model. You notice that we changed the kernel to linear. And there's our kernel linear on the printout. And there's other different settings you can mess with. We're going to just leave that alone for right now. For this, we don't really need to mess with any of those. So next, we're going to dig a little bit into our newly trained model. And we're going to do this so we can show you on a graph. And let's go ahead and get the separating And we're going to say we're going to use a W for our variable on here. And we're going to do model.coefficient underscore 0. So what the heck is that? Again, we're digging into the model. So we've already got a prediction and a train. This is the math behind it that we're looking at right now. And so the W is going to represent two different coefficients. And if you remember, we had y equals mx plus c. So these coefficients are connected to that, but in two-dimensional. It's a plane. We don't want to spend too much time on this because you can get lost in the confusion of the math. So if you're a math whiz, this is great. You can go through here and you'll see that we have a equals minus w of 0 over w of 1. Remember, there's two different values there. And that's basically the slope that we're generating. And then we're going to build an xx. What is xx? We're going to set it up to a numpy array. There's our np dot line space. So we're creating a line of values between 30 and 60. So it just creates a set of numbers for x. And then if you remember correctly, we have our formula y equals the slope times x plus the intercept. Well, to make this work, we can do this as yy equals the slope times each value in that array. That's the neat thing about numpy. So when I do a times xx, which is a whole numpy array of values, it multiplies a across all of them. And then it takes those same values and we subtract the model intercept. That's your, remember we had mx plus c, so that'd be the c from the formula, y equals mx plus c. And that's where all these numbers come from. A little bit confusing because it's digging out of these different arrays. And then what we want to do is we're going to take this and we're going to go ahead and plot it. So plot the parallels to separating hyperplane that pass through the support vectors. And so we're going to create B equals a model support vectors. Pulling our support vectors out there. Here's our yy, which we now know is a set of data. And we have we're going to create yy down equals a times xx plus b1 minus a times b0. And then model support vector B is going to be set that to a new value, the -1 setup, and yy up equals a times xx plus b1 minus a times b0. And we can go ahead and just run this to load these variables up. If you want to understand a little bit more of what's going on, you can see if we print yy, we just run that, you can see it's an array. This is a line. It's going to have, in this case, between 30 and 60, so it's going to be 30 variables in here. And the same thing with yy up, yy down. And we'll plot those in just a minute on a graph so you can see what those look like. You just go ahead and delete that out of here and run that so it loads up the variables. Nice clean slate. I'm just going to copy this from before. Remember this, our SNS, our seaborn plot, LM plot, flour, sugar. And I'll just go ahead and run that real quick so you can see remember what that looks like. It's just a straight graph on there. And then one of the neat things is because seaborn sits on top of pie plot, we can do the pie plot for the line going through. And that is simply plt.plot. And that's our xx and yy, our two corresponding values, xy. And then somebody played with this to figure out that the line width equals 2 and the color black would look nice. So let's go ahead and run this whole thing with the pie plot on there. And you can see when we do this, it's just doing flour and sugar on here. Corresponding line between the sugar and the flour and the muffin versus cupcake. And then we generated the support vectors, the yy down and yy up. So let's take a look and see what that looks like. So we'll do our PL plot. And again, this is all against xx, our x value. But this time we have yy down. And let's do something a little fun with this. We can put in a k dash dash. That just tells it to make it a dotted line. And if we're going to do the down one, we also want to do the up one. So here's our yy up. And when we run that, it adds both sets of line. And so here's our support, and this is what you expect. You expect these two lines to go through the nearest data point. So the dashed lines go through the nearest muffin and the nearest cupcake when it's plotting it. And then your SVM goes right down the middle. So it gives it a nice split in our data, and you can see how easy it is to see, based just on sugar and flour, which one's a muffin or a cupcake. Let's go ahead and create a function to predict muffin or cupcake. I've got my recipes I pulled off the internet, and I want to see the difference between a muffin or a cupcake. And so we need a function to push that through. And we'll create a function with def. And let's call it muffin or cupcake. And remember, we're just doing flour and sugar today. We're not doing all the ingredients. And that actually is a pretty good split. You really don't need all the ingredients to know it's flour and sugar. And let's go ahead and do an if-else statement. So if model predict is of flour and sugar equals 0. So we take our model and we run a predict. It's very common in sklearn where you have a dot predict. You put the data in, and it's going to return a value. In this case, if it equals 0, then print you're looking at a muffin recipe. Else, if it's not 0, that means it's 1, then you're looking at a cupcake recipe. That's pretty straightforward for a function, or def for definition. DEF is how you do that in Python. And of course, if you're going to create a function, you should run something in it. And so let's run a cupcake, and we're going to send it values 50 and 20, a muffin or a cupcake. I don't know what it is. And let's run this and just see what it gives us. And it says, oh, it's a muffin. You're looking at a muffin recipe. So it very easily predicts whether we're looking at a muffin or a cupcake recipe. Let's plot this. There we go. Plot this on the graph so we can see what that actually looks like. And I'm just going to copy it and paste it from below where we're plotting all the points in there. So this is nothing different than what we did before. If I run it, you'll see it has all the points and the lines on there. And what we want to do is we want to add another point. And we'll do plt plot. And if you remember correctly, we did, for our test, we did 50 and 20. And then somebody went in here and decided we'll do YO for yellow, or it's kind of an orangish yellow color is going to come out. Marker size 9. Those are settings you can play with. Somebody else played with them to come up with the right setup so it looks good. And you can see there it is graphed, clearly a muffin. In this case, in cupcakes versus muffins, the muffin has won. And if you'd like to do your own muffin cupcake contender series, you certainly can send a note down below, and the team at Simplilearn will send you over the data they use for the muffin and cupcake. And that's true of any of the data. We didn't actually run a plot on it earlier. We had men versus women. You can also request that information to run it on your data setup so you can test that out. So to go back over our setup, we went ahead for our support vector machine code. We did a predict 40 parts flour, 20 parts sugar. I think it was different than the one we did, whether it's a muffin or a cupcake. Hence, we have built a classifier using SVM, which is able to classify if a recipe is of a cupcake or a muffin, which wraps up our cupcake versus muffin. So the key takeaways, what is machine learning? We discussed that with some of the different aspects of machine learning on there. We went into types of machine learning. If you memorize, we have supervised, unsupervised, and reinforcement learning. We discussed regression line or best fit, and we did the building a decision tree and what the logic is behind that. And finally, we did classification using SVM, support vector machine, and we did the code in there.
My name is Richard Kirshner with the Simplilearn team. That's Get Certified, Get Ahead. We're going to cover mathematics for machine learning. So today's agenda is going to cover data and its types. Then we're going to dive into linear algebra and its concepts, calculus, statistics for machine learning, probability for machine learning, hands-on demos. And of course, thrown in there in the middle is going to be your matrices and a few other things to go along with all this. Data and its types. Data denotes the individual pieces of factual information collected from various sources. It is stored, processed, and later used for analysis. And so we see here just a huge grouping of information, a lot of text stuff, money, dollar signs, numbers, And then you have your performing analytics to drive insights. And hopefully you have a nice your shareholders gathered at the meeting and you're able to explain it in something they can understand. So when we talk about types of data, in our types of data, we have a qualitative, categorical. You think nominal or ordinal. And then you have your quantitative or numerical, which is discrete or continuous. And let's look a little closer at those data types. Vocabulary, always people's favorite is the vocabulary words. Okay, not mine. But let's dive into this, what we mean by nominal. Nominal, they are used to label our variables without providing any measurable value. Country, gender, race, hair, color, etc. It's something that you either mark true or false. This is a label. It's on or off. Either they have a red hat on or they do not. So a lot of times when you're thinking nominal data labels, think of it as a true-false kind of setup. And we look at ordinal. This is categorical data with a set order or a scale to it. And you can think of salary range as a great one. Movie ratings, etc. You can see here the salary range. If you have 10,000 to 20,000, number of employees earning that rate is 150. 20,000 to 30,000, 100, and so forth. Some of the terms you'll hear is bucket. This is where you have 10 different buckets and you want to separate it into something that makes sense into those 10 buckets. And so when we start talking about ordinal, a lot of times when you get down to the brass bones, again, we're talking true-false. So if you're a member of the 10 to 20K range, so forth. Those would each be either part of that group or you're not. But now we're talking about buckets and we want to count how many people are in that bucket. Quantitative, numerical data falls into two classes, discrete or continuous. And so data with a final set of values which can be categorized. Class strength, questions answered correctly, and runs hit in cricket. A lot of times when you see this, you can think integer, and a very restricted integer, i.e. you can only have 100 questions on a test, so it's very discrete. I only have 100 different values that it can attain. So usually you're talking about integers, but within a very small range. They don't have an open end or anything like that. So discrete is very solid, simple to count, set number. Continuous, on the other hand, continuous data can take any numerical value within a range. So water pressure, weight of a person, etc. Usually we start thinking about float values where they can get phenomenally small in what they're worth. And there's a whole series of values that falls right between discrete and continuous. You can think of the stock market. You have dollar amounts. It's still discrete, but it starts to get complicated enough when you have jump in the stock market from $525.33 to $580.67. There's a lot of point values in there. It'd still be called discrete, but you start looking at it as almost continuous because it does have such a variance in it. Now, we talk about we went over nominal and ordinal, almost true-false charts, and we looked at quantitative and numerical data, which we're starting to get into numbers. Discrete, you can usually, a lot of times discrete could be put into true-false, but usually it's not. So we want to address this stuff, and the first thing we want to look at is the very basic, which is your algebra. So we're going to take a look at linear algebra. You can remember back when your Euclidean geometry. We have a line. Well, let's go through this. We have a linear algebra is the domain of mathematics concerning linear equations and their representations in vector spaces and through matrices. I told you we're going to talk about matrices. So a linear equation is simply 2x plus 4y minus 3z equals 10. Very linear. 10x plus 12.4y equals z. And now you can actually solve these two equations by combining them. And that's where we're talking about a linear equation. In the vectors, we have a plus b equals c. Now we're starting to look at a direction. And these values usually think of an x, y, z plot. So each one is a direction. And the actual distance of like a triangle, AB, is c. And then your matrix can describe all kinds of things. I find matrices confuse a lot of people, not because they're particularly difficult, but because of the magnitude and the different things they're used for. And a matrix is a chart or think of a spreadsheet, but you have your rows and your columns. And you'll see here we have A times B equals C. Very important to know your counts. So depending on how the math is being done, what you're using it for, making sure you have the same rows and number of columns or a single number. There's all kinds of things that play in that can make matrices confusing. But really it has a lot more to do with what domain you're working in. Are you adding in multiple polynomials where you have like ax squared plus by plus, you start to see that it can be very confusing versus a very straightforward matrix. And let's just go a little deeper into these, because these are such primary. This is what we're here to talk about, is these different mathematical computations that come up. So when we're looking at linear equations, let's dig deeper into that one. An equation having a maximum order of 1 is called a linear equation. So it's linear because when you look at this, we have ax plus b equals c, which is a 1 variable. We have 2 variable ax plus by equals c, ax plus by plus cz equals d, and so forth. But all of these are to the power of 1. You don't see x squared. You don't see x cubed. So when we're talking about linear equations, that's what we're talking about. In their addition, if you have already dived into, say, neural networks, you should recognize this ax plus by plus cz setup plus the intercept. Which is basically your neural network, each node adding up all the different inputs. And we can drill down into that. Most common formula is your y equals mx plus c. So you have your y equals the m, which is your slope, your x value plus c, which is your y-intercept. They kind of labeled it wrong here. Threw me for a loop. But the c would be your y-intercept. So when you set x equal to 0, y equals c. And that's your y-intercept right there. And they just had a reversed value of y when x equals 0. It equals the y-intercept, which is c. And your slope gradient line, which is your m. So you get your y equals 2x plus 3. And there's lots of easy ways to compute this. This is why we always start with the most basic one when we're solving one of these problems. And then, of course, one of the most important takeaways is the slope gradient of the line. So the slope is very important, that m value. In this case, we went ahead and solved this. If you have y equals 2x plus 3, you can see how it has a nice line graph here on the right. So, matrices. A matrix refers to a rectangular representation of an array of numbers arranged in columns and rows. So we're talking m rows by n columns. Here, A11 denotes the element of the first row in the first column. Similarly, A12, and it's really pronounced A11 in this particular setup. So it's row 1, column 1. A12 is A of row 1, column 2. First row and second column, and so on. And there's a lot of ways to denote this. I've seen these as like a capital letter A, smaller case a for the top row. Or, you can see where they can go all kinds of different directions as far as the value. You just take a moment to realize there needs to be some designation as far as what row it's in and what column it's in. And we have our basic operations. We have addition. So when you think about addition, you have 2 matrices of 2 by 2, and you just add each individual number in that matrix. And then when you get to the bottom, you have, in this case, the solution is 12. 10 plus 2 is 12. 5 plus 3 is 8, and so on. And the same thing with subtraction. Now, again, you're counting matrices. You want to check your dimensions of the matrix. The shape. You'll see shape come up a lot in programming. So when we're talking about dimensions, we're talking about the shape. If the two shapes are equal, this is what happens when you add them together or subtract them. And we have multiplication. When you look at the multiplication, you end up with a very slightly different setup going. Now, if we look at our last one, we're like, why? This always gets to me when we get to matrices, because they don't really say why you multiply matrices. My first thought is 1 times 2, 4 times 3. But if you look at this, we get 1 times 2 plus 4 times 3, 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3, 6 times 3 plus 3 times 5. If you're looking at these matrices, think of this more as an equation. And so we have, if you remember, when we back up here for our multiple line equations, let's just go back up a couple slides where we were looking at two variable. So this is a two variable equation, ax plus by equals c. And this is a way to make it very quick to solve these variables, and that's why you have the matrix, and that's why you do the multiplication the way they do. And this is the dot product of 1 times 2 plus 4 times 3. 1 times 3 plus 4 times 5. 6 times 2 plus 3 times 3. 6 times 3 plus 3 times 5. And it gives us a nice little 14, 23, 21, and 33 over here, which then can be used and reduced down to a simple formula as far as solving the variables as you have enough inputs. And then in matrix operations, when you're dealing with a lot of matrices, now keep in mind, multiplying matrices is different than finding the product of two matrices. Okay? So when we're talking about multiplication, we're talking about solving for equations. When you're finding the product, you are just finding 1 times 2. Keep that in mind, because that does come up. I've had that come up a number of times where I am altering data and I get confused as to what I'm doing with it. Transpose, flipping the matrix over its diagonal. Comes up all the time, where you still have 12, but instead of it being 12, 8, it's now 12, 14, 8, 21. You're just flipping the columns and the rows. And then, of course, you can do an inverse, changing the signs of the values across this main diagonal. And you can see here we have the inverse a to the minus 1, and it ends up with, instead of 12, 8, 14, 12, it's now minus 22, minus 12. Vectors. Vector just means we have a value and a direction. And we have down 4 numbers here on our vector. In mathematics, a one-dimensional matrix is called a vector. So if you have your x plot and you have a single value, that value is along the x-axis and it's a single dimension. If you have 2 dimensions, you can think about putting them on a graph. You might have x and you might have y, and each value denotes a direction. And then, of course, the actual distance is going to be the hypothesis of that triangle. And you can do that with 3 dimensionals, x, y, and z. And you can do it all the way to nth dimensions. So when they talk about the k-means for categorizing and how close data is together, they will compute that based on the Pythagorean theorem. So you would take the square of each value, add them all together, and find the square root, and that gives you a distance as far as where that point is, where that vector exists, or an actual point value. And then you can compare that point value to another one. And it makes a very easy comparison versus comparing 50 or 60 different numbers. And that brings us up to eigene vectors and eigene values. Eigene vectors, the vectors that don't change their span while transformation, and eigene values, the scalar values that are associated to the vectors. Conceptually, you can think of the vector as your picture. You have a picture, it's 2 dimensions, x and y. And so when you do those 2 dimensions and those 2 values, or whatever that value is, that is that point. But the values change when you skew it. And so if we take and we have a vector A, and that's a set value, B is you have A and B, which is your eigene vector. 2 is the eigene value. So we're altering all the values by 2. That means maybe we're stretching it out one direction, making it tall, if you're doing picture editing. That's one of the places this comes in. But you can see when you're transforming your different information, how you transform it is then your eigene value. And you can see here, vector after line transition, we have 3a. A is the eigene vector, 3 is the eigene value. So A doesn't change, that's whatever we started with, that's your original picture. And 3 is skewing it one direction, and maybe B is being skewed another direction. And so you have a nice tilted picture because you've altered it by the eigene values. So let's go ahead and pull up a demo on linear algebra. And to do this, I'm going to go through my trusted Anaconda into my Jupyter notebook, and we'll create a new notebook called linear algebra. Since we are working in Python, we're going to use our NumPy. I always import that as NP, our NumPy array. Probably the most popular module for doing matrices and things in. Given that this is part of a series, I'm not going to go too much into NumPy. We are going to go ahead and create two different variables, A for a NumPy array 10, 15, and B 29. We'll go ahead and run this, and you can see there's our two arrays, 10, 15, 29. And I went ahead and added a space there in between, so it's easier to read. And since it's the last line, we don't have to put the print statement on it unless you want. We can simply do A plus B. So when I run this, we have 10, 15, 29, and we get 30, 24, which is what you expect. 10 plus 20, 15 plus 9. You could almost look at this addition as being just adding up the columns on here coming down. And if we wanted to do it a different way, we could also do A dot T plus B dot T. Remember that T flips them. And so if we do that, we now get them, we now have 30, 24 going the other way. We could also do something kind of fun. There's a lot of different ways to do this. As far as A plus B, I can also do A plus B dot T, and you're going to see that that will come out the same, the 30, 24, whether I transpose A and B or transpose them both at the end. And likewise, we can very easily subtract two vectors. I can go A minus B, and we run that, and we get minus 10, 6. Now remember, this is the last line in this particular section, so I don't have to put the print around it. And just like we did before, we can transpose either the individual or we can transpose the main setup, and then we get a minus 10, 6 going the other way. Now, we didn't mention this in our notes, but you can also do a scalar multiplication. Let me just put down scalar so you can remember that. And what we're talking about here is I have this array here, U, and if I go A times U, we'll take the value 2, we'll multiply it by every value in here. So 2 times 30 is 60, 2 times 15. And just like we did before, this happens a lot because when you're doing matrices, you do need to flip them. You get 60, 30 coming this way. So in NumPy, we have what they call dot product. And with this is in a two-dimensional vectors. It is the equivalent to matrix multiplication. Remember, we were talking about matrix multiplication, where it is the, well, let's walk through it. We'll go ahead and start by defining two NumPy arrays. We'll have 10, 20, 25, 6, or our U and our V. And then we're going to go ahead and do, if we take the values, and if you remember correctly, an array like this would be 10 times 25 plus 20 times 6. We'll go ahead and print that. There we go. And then we'll go ahead and do the np dot of U comma V. And we'll find when we do this, we go ahead and run this, we're going to get 370, 370. So this is a strain multiplication where they use it to solve linear algebra when you have multiple numbers going across. And so this could be very complicated. We could have a whole string of different variables going in here. But for this, we get a nice value for our dot multiplication. And we did addition earlier, which was just your basic addition. And of course, the matrix, you can get very complicated on these, or in this case, we'll go ahead and do, let's create two complex matrices. This one is a matrix of 12, 10, 4, 6, 4, 31. We'll just print out A so you can see what that looks like. Here's print A. When we print A out, you can see that we have a 2 by 3 layer matrix for A. And we can also put together, always kind of fun when you're playing with print values, we could do something like this. We could go in here. There we go. We could print A, we have it end with equals A, run, and this kind of gives it a nice look. Here's your matrix. That's all this is. Comma end means it just tags it on the end. That's all that is doing on there. And then we can simply add in what is A plus B, and you should already guess because this is the same as what we did before. There's no difference. When we do a simple vector addition, we have 12 plus 2 is 14, 10 plus 8 is 18, and so on. And just like we did the matrix addition, we can also do A minus B and do our matrix subtraction. And we look at this, we have what? 12 minus 2 is 10, 10 minus 8, where are we? Oh, there we go. 8 minus, confusing what I'm looking at. I should have reprinted out the original numbers. But we can see here 12 minus 2 is, of course, 10. 10 minus 8 is 2. 4 minus 46 is minus 42, and so forth. So same as the subtraction as before, we just call it matrix subtraction. It's identical. Now, if you remember up here, we had scalar addition, where we're adding just one number to a matrix. You can also do scalar multiplication. And so simply if you have a single value A and you have B, which is your array, we can also do A times B. When we run that, you can see here we have 2 times 4 is 8, 5 times 4 is 20, and so forth. You're just multiplying the 4 across each one of these values. And this is an interesting one that comes up. A little bit of a brain teaser is matrix and vector multiplication. And so when we're looking at this, we are, just do a regular arrays. It doesn't necessarily have to be a NumPy array. We have A, which has our array of arrays, and B, which is a single array. And so we can, from here, do the dot AB, and this is going to return 2 values. And the first value is that, you could say it's like we're doing this array, B array, first with A and then with a second one. And so it splits it up. So you have a matrix of vector multiplication, and you can mix and match. When you get into really complicated back-end stuff, this becomes more common because you've got layers upon layers of data, and so you'll end up with a matrix and a set of vector matrices that you want to multiply. Now, keep in mind that if you're doing data science, a lot of times you're not looking at this. This is what's going on behind the scenes. So if you're in the scikit looking at sklearn, where you're doing linear regression models, this is some of the math that's hidden behind the scenes that's going on. Other times, you might find yourself having to do part of this and manipulate the data around so it fits right, and then you go back in and you run it through the scikit. And if we can do, up here where we did a matrix and vector multiplication, we can also do matrix to matrix multiplication. And if we run this where we have the 2 matrices, you can see we have a very complicated array that, of course, comes out on there for our dot. And just to reiterate it, we have our transpose a matrix, which is your dot T. And so if we create a matrix A and then we do transpose it, you can see how it flips it from 5, 10, 15, 20, 25, 30 to 5, 15, 25, 10, 20, 30, rows and columns. And certainly with the math, this comes up a lot. It also comes up a lot with XY plotting. When you put it into PyPlot, you have one format where they're looking at pairs of numbers, and then they want all of X's and all Y's. So, the transpose is an important tool both for your math and for plotting and all kinds of things. Another tool that we didn't discuss is your identity matrix. And this one is more definition. The identity matrix, we have here one where we just did 2. So it comes down as 1, 0, 0, 1, 1, 0, 0, 0, 1, 0. It creates a diagonal of 1. And what that is when you're doing your identities, you can be comparing all your different features to the different features and how they correlate. And of course, when you have feature 1 compared to feature 1 to itself, it is always 1, where usually it's between 0 and 1, depending on how well it correlates. So when we're talking about identity matrix, that's what we're talking about right here, is that you create this preset matrix and then you might adjust these numbers depending on what you're working with and what the domain is. And then another thing we can do to kind of wrap this up, we'll hit you with the most complicated piece of this puzzle here, is an inverse A matrix. And let's just go ahead and put the, it's a lengthy description. Let's go ahead and put the description. This is straight out of the website for NumPy. So given a square matrix A, here's our square matrix A, which is 2, 1, 0, 0, 1, 0, 1, 2, 1. Keep in mind, 3 by 3, it's square. It's got to be equal. It's going to return the matrix A inverse satisfying dot A inverse. So here's our matrix multiplication. And then, of course, it equals the dot, A inverse of A with an identity shape of A dot shape 0. This is just reshaping the identity. That's a little complicated there. So we go and have here's our array. We'll go ahead and run this. And you can see what we end up with is we end up with an array 0.5 minus 0.5 and so forth, with our 2, 1, 1 going down, 2, 1, 0, 0, 1, 0, 1, 2, 1. Getting into a little deep on the math, understanding when you need this is probably is what's really important when you're doing data science versus handwriting this out and looking up the math and handwriting all the pieces out. You do need to know about the linear algorithm inverse of A. So if it comes up, you can easily pull it up, or at least remember where to look it up. We took a look at the algebra side of it. Let's go ahead and take a look at the calculus side of what's going on here with the machine learning. So calculus, oh my goodness, and differential equations, you got to throw that in there because that's all part of the bag of tricks, especially when you're doing large neural networks, but it also comes up in many other areas. The good news is most of it's already done for you in the back end. So when it comes up, you really do need to understand from the data science, not data analytics. Data analytics means you're digging deep into actually solving these math equations. And a neural network is just a giant differential equation. So when we talk about calculus, we're going to go ahead and understand it by talking about cars versus time and speed. So it helps to calculate the spontaneous rate of change. So suppose we plot a graph of the speed of a car with respect to time. So as you can see here, going down the highway, probably merged into the highway from an on-ramp. So I had to accelerate, so my speed went way up. Stuck in traffic, merged into the traffic opens up, and I accelerate again up to the speed limit, and maybe it peters off up there. So you can look at this as the speed versus time. I'm getting faster and faster because I'm continually accelerating, and if I hit the brakes, it'd go the other way. So the rate of change of speed with respect of time is nothing but acceleration. How fast are we accelerating? The acceleration is the area between the start point of x and the end point of delta x. So we can calculate a simple, if you had x and delta x, we could put a line there, and that slope of the line is our acceleration. Now, that's pretty easy when you're doing linear algebra, but I don't want to know it just for that line and those 2 points. I want to know it across the whole of what I'm working with. That's where we get into calculus. So when we talk about the distance between x and delta x, it has to be the smallest possible near to 0 in order to approximate the acceleration. So the idea is that instead of, if you ever took a basic calculus class, they would draw bars down here and you would divide this area up. Let's go back up a screen. You divide this area of this time period up into maybe 10 sections, and you'd use that and you could calculate the acceleration between each one of those 10 sections kind of thing. And then we just keep making that space smaller and smaller until delta x is almost infinitesimally small. And so we get a function of a equals a limit as h goes to 0 of a function of a plus h minus a function of a over h. And that is you're computing the slope of the line. We're just computing that slope under smaller and smaller and smaller samples. And that's what calculus is. Calculus is the integral. You can see down here we have our nice integral sign. Looks like a giant S. And that's what that means, is that we've taken this down to as small as we can for that sampling. So we're talking about calculus. We're finding the area under the slope is the main process in the integration. Similar, small intervals are made of the smallest possible length of x plus delta x, where delta x approaches almost an infinitesimally small space. And then it helps to find the overall acceleration by summing up all the lengths together. So we're summing up all the accelerations from the beginning to the end. And so here's our integral. We sum of a of x times d of x equals a plus c. That is our basic calculus here. So when we talk about multivariate calculus deals with functions that have multiple variables. And you can see here we start getting into some very complicated equations. Change in w over change of time equals change of w over change of z. The differential of z to dx, differential of x to dt. It gets pretty complicated. And it really translates into the multivariate integration using double integrals. And so you have the sum of f of x of y of d of a equals the sum from c to d and a to b of f of x of y dx dy equals the sum of a to b, sum of c to d of f x of y dy dx. Understanding the very specifics of everything going on in here and actually doing the math is usually calculus 1, calculus 2, and differential equations. So you're talking about 3 full-length courses to dig into and solve these math equations. What we want to take from here is when we're talking about calculus, we're talking about summing of all these different slopes. And so we're still solving a linear expression. We're still solving y equals mx plus b. But we're doing this for infinitesimally small x's, and then we want to sum them up. That's what this integral sign means. The sum of a of x d of x equals a plus c. And when you see these very complicated multivariate differentiation using the chain rule, when we come in here and we have the change of w to the change of t equals the change of w dz, and so forth. That's what's going on here. That's what these means. We're basically looking for the area under the curve, which really comes to how is the change changing? Speed's going up. How is that changing? And then you end up with a multiple layer. So if I have 3 layers of neural networks, how is the third layer changing based on the second layer changing, which is based on the first layer changing? And you get the picture here that now we have a very complicated multivariate integration with integrals. The good news is we can solve this mathematically, and that's what we do when you do neural networks and reverse propagation. So the nice thing is that you don't have to solve this on paper unless you're data analysis and you're working on the back end of integrating these formulas and building the script to actually build them. So we talk about applications of calculus. It provides us the tools to build an accurate predictive model. So it's really behind the scenes. We want to guess at what the change of the change of the change is. That's a little goofy. I know. I just threw that out there. It's kind of a meta term. But if you can guess how things are going to change, then you can guess what the new numbers are. Multivariate calculus explains the change in our target variable in relation to the rate of change in the input variables. So there's our multiple variables going in there. If one variable is changing, how does it affect the other variable? And then in gradient descent, calculus is used to find the local and global maxima. And this is really big. We're actually going to have a whole section here on gradient descent because it is really, I talked about neural networks and how you can see how the different layers go in there, but gradient descent is one of the most key things for trying to guess the best answer to something. So let's take a look at the code behind gradient descent. And before we open up the code, let's just do real quick gradient descent. Let's say we have a curve like this. And most common is that this is going to represent your error. Oops. Error. There we go. Error. Hard to read there. And I want to make the error as low as possible. And so when I'm looking at it is I want to find this line here, which is the minimum value. So we're looking for the minimum. And it does that by sampling there. And then based on this, it guesses it might be someplace here. And it goes, hey, this is still going down. It goes here, and then goes back over here, and then goes a little bit closer. And it's just playing a high-low until it gets to that spot, that bottom spot. And so we want to minimize the error. On the flip note, you could also want to be maximizing something. You want to get the best output of it. That's simply minus the value. So if you're looking for where the peak is, this is the same as a negative for where the valley is. I'm looking for that valley. That's all that is, and this is a way of finding it. So the cool thing is all the heavy lifting's done. I actually ended up putting together one of these a while back when I didn't know about Sidekick, and I was just starting. Boy, it's a long while back. And is playing high-low. How do you play high-low, not get stuck in the valleys, figure out these curves and things like that? Well, you do that, and the back end is all the calculus and differential equations to calculate this out. The good news is you don't have to do those. So instead, we're going to put together the code. And let's go ahead and see what we can do with that. So, guys in the back put together a nice little piece of code here, which is kind of fun. Some things we're going to note, and this is really important stuff, because when you start doing your data science and digging into your machine learning models, you're going to find these things are stumbling blocks. The first one is current x. Where do we start at? Keep in mind, your model that you're working with is very generic. So whatever you use to minimize it, the first question is, where do we start? And we started at this because the algorithm starts at x equals 3. So we arbitrarily picked 5. Learning rate is how many bars to skip going one way or the other. In fact, I'm going to separate that a little bit because these two are really important. If we're dealing with something like this where we're talking about, well, here's the function we're going to use. Our gradient of our function, 2 times x plus 5, keep it simple. So that's the function we're going to work with. So if I'm dealing with increments of 1,000, 0.1 is going to be a very long time. And if I'm dealing with increments of 0.001, 0.1 is going to skip over my answer. So I won't get a very good answer. And then we look at precision. This tells us when to stop the algorithm. So again, very specific to what you're working on. If you're working with money and you don't convert it into a float value, you might be dealing with 0.01, which is a penny. That might be your precision you're working with. And then, of course, the previous step size, max iterations. We want something to cut out at a certain point. Usually that's built into a lot of minimization functions. And then here's our actual formula we're going to be working with. And then we come in and we go, while previous step size is greater than precision and iters is less than max iters. Say that 10 times fast. We're just saying if we're still greater than our precision level, we still got to keep digging deeper. And then we also don't want to go past 1,000 or whatever this is, 1,000,000 or 10,000 running. That's actually pretty high. We almost never do max iterations more than like 100 or 200. Rare occasions you might go up to 400 or 500 if it's depending on the problem you're working with. So we have our previous equals our current. That way we can track time-wise. The current now equals the current minus the rate times the formula of our previous x. So now we've generated our new version. Previous step size equals the absolute current previous. So we're looking for the change in x. Iters equals iterations plus 1. That's so we know to stop if we get too far. And then we're just going to print the local minimum occurs at x on here. And if we go ahead and run this, you can see right here it gets down to this point and it says, hey, local minimum is minus 3.3222 for this particular series we created. And this is created off of our formula here, lambda x2 times x plus 5. Now, when I'm running this stuff, you'll see this come up a lot with the sklearn kit. And one of the nice reasons of breaking this down the way we did is I could go over those top pieces. Those top pieces are everything when you start looking at these minimization toolkits and built-in code. And so from we'll just do, it's actually docs.scipy.org, and we're looking at the scikit. There we go. Optimize, minimize. You can only minimize one value. You have the function that's going in. This function can be very complicated. So we used a very simple function up here. It could be, there's all kinds of things that could be on there. And there's a number of methods to solve this as far as how they shrink down. And your x naught, there's your start value. So your function, your start value, there's all kinds of things that come in here that we can look at, which we're not going to. Optimization automatically creates, constraints, bounds. Some of this it does automatically, but the big thing I want to point out here is you need to have a starting point. You want to start with something that you already know is mostly the answer. If you don't, then it's going to have a heck of a time trying to calculate it out. Or you can write your own little script that does this and does a high-low guessing and tries to find the max value. That brings us to statistics. What this is kind of all about is figuring things out. A lot of vocabulary in statistics. So statistics, well, I guess it's all relative. It's definitely not an EDL class. So a bunch of stuff going on in statistics. Statistics concerns with the collection, organization, analysis, interpretation, and presentation of data. That is a mouthful. So we have from end to end, where does it come from? Is it valid? What does it mean? How do we organize it? How do we analyze it? And then you got to take those analyses and interpret it into something that people can use, kind of reduce it to understandable. And nowadays you have to be able to present it. If you can't present it, then no one else is going to understand what the heck you did. So when we look at the terminologies, there's a lot of terminologies depending on what domain you're working in. So clearly if you're working in a domain that deals with viruses and T cells and how does, where does it come from, and you're studying the different people, then you're going to have a population. If you are working with mechanical gear, a little bit different. If you're looking for the wobbling statistics to know when to replace a rotor on a machine or something like that, that can be a big deal. We have these huge fans that turn in our sewage processing systems. And so those fans, they start to wobble and hum and do different things that the sensors pick up. At one point, do you replace them instead of waiting for it to break, in which case it costs a lot of money. Instead of replacing a bushing, you're replacing the whole fan unit. An interesting project that came up for our city a while back. So population. All objects or measurements whose properties are being observed. So that's your population, all the objects. It's easy to see it with people because we have our population in large. But in the case of the sewer fans, we're talking about the fan units. That's the population of fans that we're working with. You have a parameter, a metric that is used to represent a population or characteristic. You have your sample, a subset of the population studied. You don't want to do them all because then you don't have if you come up with a conclusion for everyone, you don't have a way of testing it. So you take a sample. Sometimes you don't have a choice. You can only take a sample of what's going on. You can't study the whole population. And a variable, a metric of interest for each person or object in a population. Types of sampling. We have a probabilistic approach, selecting samples from a larger population using a method based on the theory of probability. And we'll go into a little bit more deeper on these. We have random, systematic, stratified. And then you have a non-probabilistic approach, selecting samples based on the subjective judgment of the researcher rather than random selection. It has to do with convenience, trying to reach a quota, or snowball. And they're very biased. That's one of the reasons you'll see this big stamp on it that says biased. So you got to be very careful on that. So probabilistic sampling. When we talk about a random sampling, we select random size samples from each group or category. So it's as random as you can get. When we talk about systematic sampling, we're selecting random size samples from each group or category with a fixed periodic interval. So we kind of split it up. This would be like a time setup or our different categories. And you might ask your question, well, what is a category or a group? If you look at, I'm going to go back a window. let's say we're studying economics of an area, we know pretty much that based on their culture and where they came from, they might need to be separated. And so, and when I say separated, I don't mean separated from their place where they live. I mean, as far as the analysis, we want to look at the different groups and make sure they're all represented. So if we had like an 80% of a group that is, say, Hispanic or Indian, and also in that same area, we have 20% who are, let's call her expatriates. They left America and they're nice, and your Caucasian group. We might want to sample a group that is representative of both. So we're talking about stratified sampling, and we're talking about groups. Those are the groups we're talking about. And that brings us to stratified sampling, selecting approximately equal size samples from each group or category. This way we can actually separate the categories and give us an insight into the different cultures and how that might affect them in that area. So you can see these are very, very different, kind of depends on what you're working with as far as your data and what you're studying. And so we can see here, just to go a little bit more, we'd have selecting 25 employees from a company of 250 employees randomly. Don't care anything about them, what groups they're in, which office they're in, nothing. And we might be selecting one employee from every 50 unique employees in a company of 250 employees. And then we have selecting one employee from every branch in the company office. So we have all the different branches. There's our group, or our categories by the branch. And the category could depend on what you're studying. So it has a lot of variation on there. You see this kind of grouping and categorizing is also used to generate a lot of misinformation. So if you only study one group and you say, this is what it is, then everybody assumes that's what it is for everybody. And so you got to be very careful of that, and it's a very unethical thing to kind of do. So types of statistics. When we talk about statistics, we're going to talk about descriptive and inferential statistics. There are so many different terms in statistics to break it up. So we're talking about a particular setup. So we're talking about descriptive and inferential statistics. The base of the word describe is pretty solid. You're describing the data. What does it look like? With inferential statistics, we're going to take that from the small population to a large population. So if you're working with a drug company, you might look at the data and say, these people were helped by this drug. They did 80% better as far as their health, or 80% better survival rate than the people who did not have the drug. So we can infer that that drug will work in the greater populace and will help people. So that's where you get your inferential. So we are predicting how it's going to affect the greater population. So descriptive statistics. It is used to describe the basic features of data and form the basis of quantitative analysis of data. So we have a measure of central tendencies. We have your mean, median, and mode. And then we have a measure of spread, like your range, your interquartile range, your variance, and your standard deviation. And we're going to look at all these a little deeper here in a second. But one of them you can think of is how the data differences, what's the max, min range, all that stuff is your spread. And anything that's just a single number is usually your central tendencies, measure of central tendencies. So we talk about the mean. It is the average of the set of values considered. What is the average outcome of whatever's going on? And then your median separates the higher half and the lower half of data. So where's the center point of all your different data points? So your mean might have a couple really big numbers that skew it so that the average is much higher than if you took those outliers out, where the median would, by separating the high from the low, might give you a much lower number. You might look at it and say, oh, that's odd. Why is the average so much higher than the median? Well, it's because you have some outliers. Or why is it so much lower? And then the mode is the most frequent appearing value. This is really interesting if you're studying economics and how people are doing. You might find that the most common income, like in the U.S., was at one point $24,000 a year, where the average was closer to $80,000. And it's like, wow, what a difference. Well, there's some people who have a lot of money, and so that skews that way up. So the average person is not making that kind of money. And then you look at the median income, and you're like, well, the median income is a little bit closer to the average. So it does create a very interesting way of looking at the data. Again, these are all central tendencies, single numbers you can look at for the whole spread of the data. And we look at the measure of central tendencies. The mean is the average marks of a student in a classroom. So here we have the mean, sum of the marks of the students, total number of students. And as we talked about the median, if we have 0 through 10, and we take half the numbers and put them on one side of the line, half the numbers on the other side of the line, we end up with 5 in the middle. And then the mode. What mark was scored by most of the students in a test? In a simple case where most people scored like an 82% and got certain problems wrong, easy to figure out. Not so easy when you have different areas where like you have like the, let's go back to economy. A little bit more difficult to calculate if you have a large group that makes 30,000 and a slightly bigger group that makes 26,000. So what do you put down for the mode? Certainly there's a number of ways to calculate that, and there's actually different variations depending on what you're doing. So now we're looking at a measure of spread, range. What's the difference between the highest and the lowest value? First thing you want to look at, it's we had everybody in the test scored between 60 and 100%. Somebody got 100%, or maybe 60 to 90%. It was so hard that a lot of people could not get 100%. Then you have your interquartile range. Quartiles divide a rank-ordered data set into 4 equal parts. Very common thing to do as part of all the basic packages, whether you're working in data frames with pandas, whether you're working in Scala, whether you're working in R. You'll see this come up where they have range, your min, your max, and then it'll have your interquartile range. How does it look like in each quarter of data? Variance measures how far each number in the set is from the mean and therefore from every other number in the set. So you have like how much turbulence is going on in this data. And then the standard deviation. It is the measure of the variance or the dispersion of a set of values from the mean. And you'll usually see, if I'm doing a graph, I might have the value graphed, and then based on the error, I might graph the standard deviation and the error on the graph as a background, so you can see how far off it is. So standard deviation is used a lot. So measurement of spread. Marks of a student out of 100. We have here from 50 to 63 or 50 to 90. So the range, maximum marks, minimum marks, we have 90 to 45, and the spread of that is 45, 90 minus 45. And then we have the interquartile range using the same marks over there. You can see here where the median is, and then there's the first quarter, the second quarter, and the third quarter based on splitting it apart by those values. And to understand the variance and standard deviation, we first need to find out the mean. So here's our calculating the average there. We end up at approximately 66 for the average. And then we look at that and the variance. Once we know the means, we can do equals the marks minus the mean squared. Why is it squared? Because one, you want to make sure you don't have like if you're putting all this stuff together, you end up with an error as far as one's negative, one's positive, one's a little higher, one's a little lower. So you always see the squared value and over the total observations. And so the standard deviation equals the square root of the variance, which is approximately 16. And if you were looking at a predictable model, you would be looking at the deviation based on the error. How much error does it have? And that's, again, really important to know. If your prediction is predicting something, what's the chance of it being way off or just a little bit off? Now that we've looked at the tools as far as some of the basics for doing your statistics and what we're talking about, let's go ahead and pull up a little demo and show you what that looks like in Python code so you can get some little hands-on here. For that, let's go back into our Jupyter Notebook in Python. Now, almost all of this you can do in NumPy. Last time we worked in NumPy. This time we're going to go ahead and use pandas. And if you remember from pandas on here, this is basically a data frame, rows, columns. Let's just go ahead and do a print df.head and run that. And you can see we have the name Jane, Michael, William, Rosie, Hannah, and their salaries on here. And of course, instead of having to do all those hand calculations and add everything together and divide by the total, we can do something very simple on this, like use the command mean in pandas. And so if I go ahead and do this, print df, pick our column, salary, because we want to find the means of that column. We want to find the means of that column. And we go ahead and print this out, and you can see that the average income on here is 71,000. And let's just go ahead and do this. We'll go ahead and put in means. And if we're going to do that, we also might want to find the median. And the median is very similar, except it actually is just median. We're used to means and average. It's kind of interesting that they use the two different words. There can be, in some computations, slight differences, but for the most part, the means is the average. And then the median, whoops, let's put a median here, df salary, that way it displays a little better. We can see the median is 54,000. So the halfway mark is significantly below the average. Why? Because we have somebody in here who makes 189,000. Darn you, Rosie, for throwing off our numbers. But that's something you'd want to notice. This is the difference between these is huge, and so is what is the meaning behind that when you're studying a populace and looking at the different data coming in. And of course, we also want to find out, hey, what's the most common income that people make in this little tiny sample. And so we'll go ahead and do the mode. And you can see here with the mode, it's at 50,000. So this is very telling that most people are making 50,000. The middle point is at 54,000. So half the people are making more than that. What that tells me is that if the most common income is below the median, then there's a lot of high salaries going up, but there's some really low salaries in there. And so this trend, which is very common in statistics, when you're analyzing the economy and different people's income, is pretty common. And the bigger difference between these is also very important when we're studying statistics. And when you hear someone just say, hey, the average income was, you might start asking questions at that point. Why aren't you talking about the median income? Why aren't you talking about the mode, the most common income? What are you hiding? And if you're doing these analyses, you should be looking at these saying, hey, why are these discrepancies? Why are these so different? And of course, with any analysis, it's important to find out the minimum and the maximum. So we'll go ahead. It's just simply dot min will pull up your minimum, and then dot max pulls up the maximum. Pretty straightforward on as far as translating it and knowing what your lowest value and what your highest value is here, which you'll use to generate like a spread later on. And real quick on mode, note that it puts mode 0. Like I said, there's a couple different ways you can compute the mode. Although the standard one's pretty good. We can of course do the range, which is your max minus your min. So now we have a range of 149,000 between the upper end and the lower end. And you might want to be looking up the individual values on all of these. But it turns out there is a describe feature in pandas. And so in pandas, we can actually do df salary describe. And if we do this, you can see we have that there's 7 setups. Here's our mean, our standard deviation, which we didn't compute yet, which would just be a .std. And you got to be a little careful because when it computes it, it looks for axes and things like that. We have our minimum value, and here's our quartiles, our maximum value, and then of course the name salary. So these are the basic statistics. You can pull them up and just describe. This is a dictionary, so I could actually do something like in here I could actually go count and run, and now it just prints the count. So because this is a dictionary, you can pull any one of these values out of here. It's kind of a quick and dirty way to pull all the different information and then split it up depending on what you need. Now, if I just walked in and gave you this information in a meeting, at some point you would just kind of fall asleep. That's what I would do anyway. So we want to go ahead and see about graphing it here. And we'll go ahead and put it into a histogram and plot that graph on it of the salaries. And let's just go ahead and put that in here. So we do our matplot inline. Remember, that's a Jupyter's Notebook thing. A lot of the new version of the matplot library does it automatically, but just in case, I always put it in there. Import matplot library, pyplot is PLT, that's my plotting. And then we have our data frame. I guess I really don't need to respell the data frame. Maybe we could just remind ourselves what's in it. So we'll go ahead and just print df. That way we still have it. And then we have our salary, df salary, salary.plot history title, salary distribution, color gray, plot AXV line, salary, the mean value. So we're going to take the mean value, color violet, line style dash. This is just all making it pretty. What color, dash line, line width of 2, that kind of thing. And the median. And let's go ahead and run this just so you can see what we're talking about. And so up here we are taking on our plot. So here's the data. Here's our data frame printed out so you can see it with the salaries. And we're looking at the salary distribution. And just look at this, the way the salary is distributed. You have our, in this case we did, let's see, we had red for the median. We have violet for our average or mean. And you can just see how it really, I mean, here's our outlier. Here's our person who makes a lot of money. Here's the average, and here's the median. And so as you look at this, you can say, wow, based on the average, it really doesn't tell you much about what people are really taking home. All it does is tell you how much money is in this, what the average salary is. So some of the things you want to take away in addition to this is that it's very easy to plot an AXV line. These are these up and down lines for your markers. And as you display the data, I mean, you can add all kinds of things to this and get really complicated. Keeping it simple is pretty straightforward. I look at this and I can see we have a major outlier out here. We can definitely do a histogram and stuff like that. But picture's worth 1,000 words. What you really want to make sure you take away is that we can do a basic describe, which pulls all this information out, and we can print any of the individual information from the describe, because this is a dictionary. And so if we want to go ahead and look up the mean value, we can also do describe mean. So if you're doing a lot of statistics, being able to, doesn't have the print on there, so it's only going to print the last one, which happens to be the mean. You can very easily reference any one of these. And then you can also, if you're doing something a little bit more complicated and you don't need just the basics, you can come through and pull any one of the individual references from the pandas on here. So now we've had a chance to describe our data. Let's get into inferential statistics. Inferential statistics allows you to make predictions or inferences from data. And you can see here we have a nice little picture of movie ratings, and if we took this group of people and said, hey, how many people like the movie, dislike it, can't say, and then you ask just a random person who comes out of the movie who hasn't been in this study, you can infer that 55% chance of saying liked, 35% chance of saying disliked, or a 10 or 11% chance of can't say. So that's real basics of what we're talking about, is you're going to infer that the next person is going to follow these statistics. So let's look at point estimation. It is a process of finding an approximate value for a population's parameter, like mean or average, from random samples of the population. Let's take an example of testing vaccines for COVID-19. Vaccines and flu bugs, all of that, it's a pretty big thing of how do you test these out and make sure they're going to work on the populace. A group of people are chosen from the population. Medical trials are performed. Results are generalized for the whole population. So here's our small group up here where we've selected them. We run medical trials on them, and then the results work for the population. Nice diagram with the arrows going back and forth and the very scary COVID virus in the middle of one. And let's take a look at the applications of inferential statistics. Very central is what they call hypotheses testing, and the confidence interval, which go with that. And then as we get into probability, we get into our binomial theorem, our normal distribution, and central limit theorem. Hypothesis testing. Hypothesis testing is used to measure the plausibility of a hypothesis. assumption by using sample data. Now, when we talk about theorems, theory, hypothesis, keep in mind that if you are in a philosophy class, theory is the same as hypothesis, where theorem is a scientific statement that is something that has been proven, although it is always up for debate, because in science we always want to make sure things are up to debate. So a hypothesis is the same as a philosophical class calling a theory, where theory in science is not the same. Theory in science says this has been well proven. Gravity is a theory. So if you want to debate the theory of gravity, try jumping up and down. If you want to have a theory about why the economy is collapsing in your area, that is a philosophical debate. Very important. I've heard people mix those up, and it is a pet peeve of mine. When we talk about hypotheses testing, the steps involved in hypotheses testing is first we formulate a hypothesis. We figure out the right test to test our hypothesis. We execute the test, and we make a decision. And so when you're talking about hypothesis, you're usually trying to disprove it. If you can't disprove it, and it works for all the facts, then you might call that a theorem at some point. So in a use case, let's consider an example. We have 4 students who are given a task to clean a room every day. Sounds like working with my kids. They decided to distribute the job of cleaning the room among themselves. They did so by making 4 chits, which has their names on it, and the name that gets picked up has to do the cleaning for that day. Rob took the opportunity to make chits and wrote everyone's name on it. So here's our 4 people: Nick, Rob, Imlia, and Summer. Now Rick, Imlia, and Summer are asking us to decide whether Rob has done some mischief in preparing the chits, i.e. whether Rob has written his name on one of the chit. For that, we will find out the probability of Rob getting the cleaning job on first day, second day, third day, and so on till 12 days. The probability of Rob getting the job decreases every day, i.e. his turn never comes up, then definitely he has done some mischief while making the chits. So the probability of Rob not doing work on day 1 is 3 out of 4. There's a 0.75 chance that he didn't do work. 2 days, 3/4 times 3/4 equals 0.56. 3 days, you have 3/4, 3/4, 3/4, which equals 0.42. When you get to day 12, it's 0.032, which is less than 0.05. Remember this 0.05. That comes up a lot when we're talking about certain values, when we're looking at statistics. Rob is cheating as he wasn't chosen for 12 consecutive days. That's a very high probability when on day 12 he still hasn't gotten the job cleaning the room. So we come up to our important terminologies. We have null hypothesis, a general statement that states that there is no relationship between 2 measured phenomena or no association among the groups. Alternative hypothesis. Contrary to the null hypothesis, it states whenever something is happening, a new theory is preferred instead of an old one. And so the 2 hypotheses go hand in hand. So your null, this is always interesting in when we're talking about data science and the math behind it, it's about proving that the things have no correlation. Null hypothesis says these 2 have 0 relation to each other. Where the alternative hypothesis says, hey, we found a relation, this is what it is. We have p-value. The p-value is the probability of finding the observed or more extreme results when the null hypothesis of a study question is true. And the t-value. It is simply the calculated difference represented in units of standard error. The greater the magnitude of t, the greater the evidence against the null hypothesis. And you can look at the t-value as being specific to the test you're doing, where the p-value is derived from your t-value, and you're looking for what they call the 5% or the 0.05, showing that it has a high correlation. So digging in deeper, let's assume that a new drug is developed with the goal of lowering the blood pressure more than the existing drug. And this is a good one because the null value here isn't that you don't have any drug. The null value here is that it's better than the existing drug. The new drug doesn't lower the blood pressure more than the existing drug. Now, if we get that, that says our null hypothesis is correct. There is no correlation, and the new drug is not doing its job. The alternative hypothesis, the new drug does significantly lower the blood pressure more than the existing drug. Yay, we got a new drug out there. And that's our alternative hypothesis, or the H1 or HA. And we look at the p-value, results from the evidence like medical trials showing positive results which will reject the null hypothesis. And again, they're looking for a 0.05 or 5%. And the t-value, comparing all the positive test results and finding means of different samples in order to test hypothesis. So this is specific to the test. What percentage of increase did they have? And this leads us to the confidence intervals. A confidence interval is a range of values we are sure our true values of observations lie in. Let's say you asked a dog owner around you and asked them, how many cans of food do you buy for your per year for your dog? Through calculations, you got to know that on an average, around 95% of the people bought around 200 to 300 cans of food. Hence, we can say that we have a confidence interval of 300, where 95% of our values lie in that data spread. And the graph really helps a lot, so you can start seeing what you're looking at here, where you have the 95%. You have your peak. In this case, it's a normal distribution, so you have the nice bell curve equal on both sides. It's not asymmetrical. And 95% of all the values lie within a very small range. And then you have your outliers, the 2.5% going each way. So we touched upon hypothesis, and we're going to move into probability. So you have your hypothesis. Once you've generated your hypothesis, we want to know the probability of something occurring. Probability is a measure of the likelihood of an event to occur. Any event can be predicted with total certainty and can only be predicted as a likelihood of its occurrence. So any event cannot be predicted with total certainty. It can only be predicted as a likelihood of its occurrence. Score prediction, how good you're going to do in whatever sport you're in, weather prediction, stock prediction. If you've studied physics and chaos theory, even the location of the chair you're sitting on has a probability that it might move 3 feet over. Granted, that probability is 1 in I think we calculated it as under 1 in trillions upon trillions. So it's the better the probability, the more likely it's going to happen. There are some things that have such a low probability that we don't see them. So we talk about a random variable. Random variable is a variable whose possible values are numerical outcomes of a random phenomena. So we have the coin toss. How many heads will occur in the series of 20 coin flips? Probably, on average they're 10, but you really can't know because it's very random. How many times a red ball is picked from a bag of balls, if there's equal number of red balls and blue balls and green balls in there. How many times the sum of digits on 2 dice result are 5 each. There's how often you're going to roll 2 5s on your pair of dice. So in a use case, let's consider the example of rolling 2 dice. We have a random variable outcome equals y. You can take values 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So we have a random variable and a combination of dice. And instead of looking at how many times both dice will roll 5, let's go ahead and look at total sum of 5. And you have, as far as your random variables, you can have a 1, 4 equals 5, 4, 1, 2, 3, 3, 2. So 4 of those rolls can be 4. If you look at all the different options you have, 4 of those random rolls can be a 5. And if we look at the total number, which happens to be 36 different options, you can see that we have 4 out of 36 chance every time you roll the dice that you're going to roll a total of 5. You're going to have an outcome of 5. And we'll look a little deeper as to what that means. But you could think of that at what point, if someone never rolls a 5 or they always roll a 5, can you say, hey, that person's probably cheating? We'll look a little closer at the math behind that. But let's just consider this as one of the cases is rolling 2 dice and gambling. There's also a binomial distribution. It is the probability of getting success or failure as an outcome in an experiment or trial that is repeated multiple times. And the key is bi, meaning 2, binomial. So passing or failing an exam, winning or losing a game, and getting either head or tails. So if you ever see binomial distribution, it's based on a true-false kind of setup. You win or lose. Let's consider a use case, and let's consider the game of football between 2 clubs, Barcelona and Dortmund. The teams will have to play a total of 4 matches, and we have to find out the chances of Barcelona winning the series. So we look at the total games, and we're looking at 5 different games or matches. Let's say that the winning chance for Barcelona is 75% or 0.75. That means that each game, they have a 75% chance that they're going to win that game. And losing chances are 25% or 0.25. Clearly 0.75 plus 0.25 equals 1. So that accounts for 100% of the game. Probability for getting K wins in matches is calculated. And we're talking like, so if you have 5 games and you want to know if I play, how many wins in those 5 games should I get? What's a percentage on those? And the probability for getting K wins in matches is calculated by Px equals K equals NCK, P to the K, Q to the N minus K. Here, P is the probability of success and Q is the probability of failure. And so we can do total games of N equals 5, where K equals 0, 1, 2, 3, 4, 5. P, which is the chance of winning, is 0.75. Q, the chance of losing, equals 1 minus P, which equals 1 minus 0.075, which equals 0.25. The probability that Barcelona will lose all of the matches can then just plug in the numbers, and we end up with a 0.0009765,625. So a very small chance they're going to lose all their matches. And we can plug in the value for 2 matches. Probability that Barcelona will win at least 2 matches is 0.0878. And of course we can go on to the probability that Barcelona will win 3 matches, the 0.26, and of course 4 matches, and so on. And it's always nice to take this information and let's find the cumulative discrete probabilities for each of the outcomes. Where Barcelona has won 3 or more matches, x equals 3, x equals 4, x equals 5. And we end up with the P equals 0.264 plus 0.395 plus 237, which equals 0.89. In reality, the probability of Barcelona winning the series is much higher than 0.75. And it's always nice to put out a nice graph so you can actually see the number of wins to the probability and how that pans out with our binomial case. Continuing in our important terminology, location. The location of the center of the graph depends on the mean value. And this is some very important things. So much of the data we look at, and when you start looking at probabilities, almost always has a normalized look, like the graph in the middle. But you do have left skewed, where the data is skewed off to the left, and you have more stuff happening off to the left, and you have right skewed data. And so when this comes up and these probabilities come up where they're skewed, it's really important to take a closer look at that. Mostly you end up with a normalized set of data, but you got to also be aware that sometimes it's a skewed data. And then the height. Height of the slope inversely depends upon the standard deviation. So you can see down here the standard deviation is really large. It kind of squishes it out. And if the standard deviation is small, then most of your data is going to hit right there in the middle. You're going to have a nice peak. And so being aware of this, that you might have a probability that fits certain data, but it has a lot of outliers. So if you have a really high standard deviation, if you're doing stock market analysis, this means your predictions are probably not going to make you much money. Where if you have a very small deviation, you might be right on target and set to become a millionaire. Which leads us to the z-score. Z-score tells you how far from the mean a data point is. It is measured in terms of standard deviations from the mean. Around 68% of the results are found between 1 standard deviation. Around 95% of the results are found between 2 standard deviations. And you read the symbols. Of course, they love to throw some Greek letters in there. We have mu minus 2 sigma. Mu is just a quick way. It's a kind of funky U. It just means the mean. And then the sigma is the standard deviation, and that's the O with the little arrow off to the right, or the little waggly tail going up, the O with a line on it. So mu minus 2 sigma is your 95% of the results are found between 2 standard deviations. Central limit theorem. This goes back to the skew. If you remember, we were looking at the skew values on this previous slide. Have left skewed, normalized, and right skewed. When we're talking about it being skewed or not skewed, the distribution of the sample means will be approximately normally distributed, evenly distributed, not skewed, if you take large random samples from the population with the mean, mu, and the standard deviation, sigma with replacement. And you can see here, of course, we have our mu minus 2 sigma and the spread down here, the mean, the median, and the mode. And so when you're talking about very large populations, these numbers should come together and you shouldn't have a skewed value. If you do, that's a flag that something's wrong. That's why this is so important to be aware of what's going on with your data, where your samples are coming from, and the math behind it. And if we're going to do all this, we got to jump into conditional probability. The conditional probability of an event A is a probability that the event will occur given the knowledge that an event B has already occurred. And you'll see this as Bayes' theorem, B-A-Y-E-S, Bayes. And this is read, I mean, you have these funky looking little P brackets, A, B. This is the probability of A being true while B is already true. And you have the probability of B being true when A is already true, so P, B of A. The probability of A being true divided by the probability of B being true. And we talk about Bayes' theorem, which occurred back in the 1800s when he discovered this. This is such an important formula. And it's really, it's not, if you actually do the math, you could just kind of do xy equals jk, and then you divide them out, and you're going to see the same math. But it works with probabilities, which makes it really nice. And so if you have you might have 8 or 9 different studies going on in different areas. Different people have done the studies, they brought them together. If we look at today's COVID virus, the virus spread, certainly the studies done in China versus the studies the way they're done in the US, that data is different in each of those studies. But if you can find a place where it overlaps, where they're studying the same thing together, you can then compute the changes that you need to make in one study to make them equal. And this is also true if you have a study of one group and you want to find out more about it. So this formula is very powerful, and it really has to do with the data collection part of the math and data science, and understanding where your data is coming from and how you're going to combine different studies in different groups. And we'll go ahead and go into a use case. Let's find out the chance of a person getting lung disease due to smoking. And this is kind of interesting the way they word this. Let's say that according to medical report provided by the hospital, states that around 10% of all patients they treated suffered lung disease. So we have kind of a generic medical report. They further found out by a survey that 15% of the patients that visit them smoke. So we have 10% that are lung disease, and 15% of the patients smoke. And finally, 5% of the people continued smoke even when they had lung disease. Not the brightest choice, but you know, it is an addiction, so it can be really difficult to kick. And so we can look at the probability of A. Prior probability of 10% people having lung disease. And then probability B. Probability that a patient smokes is 15%. And the probability of B, if B then A, the probability of a patient smokes even though they have lung disease is 5%. And probability of A is B, probability that the patient will have lung disease if they smoke. And then when you put the formulas together, you get a nice solution here. You get the probability of A of B, probability that the patient will have lung disease if they smoke. And you can just plug the numbers right in, and we get a 3.33% chance. Hence, there is a 3.33% chance that a person who smokes will get a lung disease. So we're going to pull up a little Python code. Always my favorite. Roll up the sleeves. Keep in mind, we're going to be doing this kind of like the back-end way, so that you can see what's going on. And then later on, we're going to create, we'll get into another demo which shows you some of the tools that are already pre-built for this. Let's start by creating a set. So we're going to create a set with curly braces. This means that our set has only unique values. So you have a list, you have your tuples, which can never change, and then you have, in this case, the set. So 4, 7, you can't create a 4, 7, comma 4. It'll delete the 4 out. So it's only unique values. And if you use dictionaries, quick reminder, this should look familiar because it is a dictionary where you have a value, and that value is assigned to, or that key is assigned to a value. So you could have a key value set up as a dictionary. So it's like a dictionary without the value. It's just the keys, and they all have to be unique. And if we run this, we have a set of 4, 7. We can also take a list, a regular setup, and I'm going to go ahead and just throw in another number in here, 4, and run it. And you can see here, if I take my list 1, 2, 3, 4, 4, and I convert it to a set, and here it is, my set from list equals set, my list. The result is 1, 2, 3, 4. So it just deletes that last 4 right out of there. And with the sets, you can also go in there and print, here is my set, 3 is in the set, and then if you do 3 in my set, that's going to be a logic function. And 1 in my set, 6 is not in the set, and so forth. If we run this, we get 3 is in the set true, 1 is in the set false, because 3, 5, 7 is another 1. 6 is in the set, 6 is not in the set, so not in my set. You can also use this with a list. We could have just used 3, 5, 7, and it would have the same response on there. Is 3 in? Usually you do if 3 is in, but 3 in my set still works on just a regular list. And we'll go ahead and do a little iteration. We're going to do kind of the dice one. Remember 1, 2, 3, 4, 5, 6. And so we're going to bring in an iteration tool and import product as product. And I'll show you what that means in just a second. So we have our 2 dice. We have dice A, and it's going to be a set of values. You can only have 1 value for each one. That's why they put it in a set. And if you remember from range, it is up to 7. So this is going to be 1, 2, 3, 4, 5, 6. It will not include the 7. And the same thing for our dice B. And then what we're going to do is we're going to create a list, which is the product of A and B. So what's A plus B? And if we go ahead and run this, it'll print that out, and you'll see, in this case, when they say product, because it's an iteration tool, we're talking about creating a tuple of the 2. So we've now created a tuple of all possible outcomes of the dice, where dice A is 1, 2, 3, 1 to 6, and dice B is 1 to 6. And you can see 1 to 1, 1 to 2, 1 to 3, and so forth. And you remember we had a slide on this earlier, where we talked about all the different outcomes of a dice. We can play around with this a little bit. We can do in dice equals 2, dice faces 1, 2, 3, 4, 5, 6. Another way of doing what we did before, and then we can create an event space where we have a set, which is the product of the dice faces, repeat equals in dice. And we'll go ahead and just run this. And you can see here, it just again puts it through all the different possible variables we can have. And then if we wanted to take the same set on here and print them all out like we had before, we can just go through for outcome and event space, outcome and equals. So the event space is creating a sequence, and as you can see here, when we print it out, it stacks them versus going through and putting them in a nice line. And we'll go ahead and do something, let's go print. Since we have the end printing with a comma, that just means it's not going to hit the return going down to the next line. And we'll go ahead and do the length of our event space. That'll be an important variable we're going to want to know in a minute. And of course, if I get carried away with my typing of length, we'll print it twice and it'll give me an error. So we have 36 different possible variations here. And we might want to calculate something like, what about the multiple of 3? What if we want to have the probability of the multiple of 3 in our setup? And so we can put together the code for the outcome and event space of x, y equals outcome. If x plus y remainder 3, so we're going to divide by 3 and look at the remainder, and it equals 0, then it's a favorable outcome. And we're going to pop that outcome on the end there. And we'll turn it into a set. So the favorable outcome equals a set. Not necessary because we know it's not going to be repeating itself, but just in case, we'll go ahead and do that. And if we want to print out the outcome, we can go ahead and see what that looks like. And you can see here, these are all multiples of 3. 1 plus 2 is 3, 5 plus 4 is 9, which divided by 3 is 3, and so forth. And just like we looked up the length of the one before, let's go ahead and print the length of our F outcome so we can see what that looks like. There we go. And of course I did forget to add the print in the middle because we're looping through and putting an end on the setup on there, so we're going to put the print in there. And if I run this, you can see we end up with 12. So we have 36 total options. We have 12 that are multiple that add up to a multiple of 3. And we can easily compute the probability of this by simply taking the length of our favorable outcome over the length of the event space. And if we print it out, let me put that in there, probability, last line, so we can just type it in, we end up with a 0.3333 chance. And it's roughly a third. And we might want to make this look nice, so let's go ahead and put in another line there. The probability of getting the sum, which is a multiple of 3, is 0.3333. We can compute the same thing for 5 dice. And if we do this for 5 dice and go ahead and run it, you can see we just have a huge amount of choices. So it just goes on and on down here. And we can look at the length of the event space. And we have over 7,776 choices. That's a lot of choices. And if we want to ask the question like we did above, what is the sum, where the sum is a multiple of 5 but not a multiple of 3, we can go through all of these different options, and then you can see here D1, D2, D3, D4, D5 equals the outcome. And if you add these all together and the division by 5 does not have a remainder of 0, but the remainder is also of a division by 3 is not equal to 0. So the multiple of 5 is equal to 0, but the multiple of 3 is not. We can just append that on here, and then we can look at that favorable outcome. We'll go ahead and set that, and we'll just take a look at this. What's our length of our favorable outcome? It's always good to see what we're working with. And so we have 904 out of 776. And then, of course, we can just do a simple division to get the probability on here. What's the probability that we're going to roll a multiple of 5 when you add them together, but not a multiple of 3? And so we're just going to divide those two numbers, and you can see here we get 0.116255, or 11.62%. And so you can really have a nice visual that this is not really complicated math right here on probabilities. It's just how many options do you have, and how many of those are you possibly going to be able to come up with the solution you're looking for. And this leads us to a confusion matrix. A confusion matrix is a table which is used to describe the performance of a classification model on a set of test data for which the true values are known. And so you'll see on the left we have the predicted and the actual. And we have a negative, false negative, positive, true positive, and then we have false positive and true negative. And you can think of this as your predicted model. What does that mean? That means if you divided your data and you used 2/3 of it to create the model, you might then test it against an actual case for the last third to see how well it comes out. How many times was it true positive versus false positive? It gave a false positive response. And you can imagine in medical situations, this is a pretty big deal. You don't want to give a false positive. So you might adjust your model accordingly so you don't have a false positive. Say with a COVID virus test, it'd be better to have a false negative and they go back and get retested than to have 30% false positives where then the test is pretty much invalid. So in a use case like cancer prediction, let's consider an example where a cancer prediction model is put to the test for its accuracy and precision. Actual result of a person's medical report is compared with the prediction made by the machine learning model. And so you can see here, here's our actual predicted, whether they have cancer or not. You know, cancer, a big one. You don't want to have a false positive. I mean, a false negative. In other words, you don't want to have it tell you that you don't have cancer when you do. So that would be something you'd really be looking for in this particular domain. You don't want a false negative. And this is, again, you know, you've created a model. You have hundreds of people or thousands of pieces of data that come in. There's a real famous case study where they have the imagery and all the measurements they take. And there's about 36 different measurements they take. And then if you run a basic model, you want to know just how accurate it is. How many negative results do you have that are either telling people they have cancer that don't, or telling people that don't have cancer that they do. And then we can take these numbers and we can feed them into our accuracy, our precision, and our recall. So accuracy, precision, and recall. Accuracy metric to measure how accurately the results are predicted. And this is your total true, where you got the right results, you add them together, the true positive, the true negative, over all the results. So what percentage of them were accurate versus what were wrong. When we talk about precision, is a metric to measure how many of the correctly predicted cases are actually turned out to be positive. So we have a precision on true positive. Again, if you're talking about like COVID testing, with the viruses, you really want this to be a high number. You want this that to be the center point, where you might have the opposite if you're dealing with cancer, where you want no false negatives. So this is your metric on here. Precision is your test positive, true positive plus false positive. And then your recall, how many of the actual positive cases we were able to predict quickly with our model. So test positive is the test positive plus the false negative on there. And we'll want to go ahead and do a demo on the naive Bayes classifier. Before I get too far into naive Bayes classifier, because we're going to pull it from the sklearn or the scikit, let's go ahead. Kind of an interesting page here for classifiers. When you go into the sklearn kit, there's a lot of ways to do classification. And I'll just zoom up in here so you can see some of the titles. There's everything from the nearest neighbor, linear, but we're going to be focusing on the naive Bayes over here. And this is just a sample data set that they put together, and you can see how some of these have a very different output. The naive Bayes, remember, is set up as probably the most simplified calculator or set of predictions out there. And so what we've been talking about with the true false and stuff like that, where there's a belief that there is a independent assumption between the features, where the features are very assumed to have some kind of connection, then we can go ahead and use that for the prediction. And so that's what we're using as a naive Bayes classifier versus many of the other classifiers that are out there. For this, we're going to use the social network ads. It's a little data set on here. And let me go ahead and just open that up, the file. Here we go. It has user ID, gender, age, estimated salary, purchased. And so we have, you can see the user ID, male, 19, estimated salary, 19,000, and purchased 0. So it's either going to make a purchase or not. So look at that last one, 0, 1. We should be thinking of binomials. We should be thinking of simple naive Bayes classifier kind of setup. So if we close this out, we're going to go ahead and import our NumPy as NP. We're going to nice to have a good visual of our data, so we'll put in our matplot library. Here's our pandas, our data frame. And then we're going to go ahead and import the data set. And the data set's going to be, we're going to read it from the social network ads.csv. Then we're going to print the head just so you can see it again, even though I showed you it in the file. And x equals the data set iLocation, 2, 3 values, and y is going to be the 4, column 4. Let me just run this so it's a little easier to go over that. You can see right here we're going to be looking at 0, 1, 2 is age and estimated salary, so 2, 3. And that's what iLocation just means, that we're looking at the number versus a regular location. Regular location, you'd actually say age and estimated salary. And then column 4 is, did they make a purchase? They purchased something. So those are the 3 columns we're going to be looking at when we do this. And we've gone ahead and imported these and imported the data. So now our data set is all set with this information in it. And we'll need to go ahead and split the data up. So we need from the sklearn model selection, we can import train test split. This does a nice job. We can set the random state so it randomly picks the data. And we're just going to take 25% of it's going to go into the test, our X test and our Y test, and the 75% will go to X train and Y train. That way, once we create our model, we can then have data to see just how accurate or how well it has performed with our prediction. The next step in pre-processing our data is to go ahead and do feature scaling. Now, a lot of this will start to look familiar. If you've done a number of the other modules and setup, you should start noticing that we bring in our data, we take a look at what we're working with, we go ahead and split it up into training and testing. In this case, we're going to go ahead and scale it. Scale it means we're putting it between a value of -1 and 1, or someplace in the middle ground there. This way, if you have any huge you don't have this huge setup. If we go back up to here where salary is 20,000 versus age 35. Well, there's a good chance with a lot of the back-end math that 20,000 will skew the results and the estimated salary will have a higher impact than the age, instead of balancing them out and letting the calculations weigh them properly. And finally, we get to actually create our naive Bayes model. And then we're going to go ahead and import the Gaussian naive Bayes. And the Gaussian is the most basic one. That's what we're looking at now. It turns out, though, if you go to the sklearn kit, they have a number of different ones you can pull in there. There's Bernoulli, I've never used that one. Categorical, complement, and here's our Gaussian. So there's a number of different options you can look at. Gaussian, when you come to the naive Bayes, is the most commonly used. So we're talking about the naive Bayes. That's usually what people are talking about when they're pulling this in. And one of the nice things about the Gaussian, if you go to their website, to sklearn, the naive Bayes Gaussian, there's a lot of cool features. One of them is you can do partial fit on here. That means if you have a huge amount of data, you don't have to process it all at once. You can batch it into the Gaussian NB model, and there's many other different things you can do with it as far as fitting the data and how you manipulate it. We're just doing the basics, so we're going to go ahead and create our classifier. We're going to equal the Gaussian NB, and then we're going to do a fit. We're going to fit our training data and our training solution, so X train, Y train. And we'll go ahead and run this. It's going to tell us that it ran the code right there. And now we have our trained classifier model. So the next step is we need to go ahead and run a prediction. We're going to do our Y predict equals the classifier.predict X test. So here we fit the data, and now we're going to go ahead and predict. And now we get to our confusion matrix. So from the sklearn metrics, you can import your confusion matrix. Just as saves you from doing all the simple math, it does it all for you. And then we'll go ahead and create our confusion metrics with the Y test and the Y predict. So we have our actual and we have our predicted value. And you can see from here, this is the chart we looked at. Here's predicted, so true positive, false negative, true negative. And if we go ahead and run this, there we have it, 65, 3, 7, 25. And in this particular prediction, we had 65 were predicted the truth as far as a purchase. They're going to make a purchase. And we guessed 3 wrong. And then we had 25 we predicted would not purchase, and 7 of them did. So there's our confusion matrix. At this point, if you were with your shareholders or a board meeting, you would start to hear some snoozing if they were looking at the numbers. And you say, hey, here's my confusion matrix. So let's go ahead and visualize the results. We're going to pull from the Matplot library colors, import listed color map. And this is actually, my machine's going to throw an error because this is being, because of the way the setup is. I have a newer version on here than when they put together the demo. And we need our X set and our Y set, which is our X train and Y train. And then we'll create our X1, X2, and we'll put that into a grid. And we set our X set minimum stop and our X set max stop. And if you come all the way over here, we're going to step 0.01. This is going to give us a nice line, is what that's doing. And then we're going to plot the contour, plot the X limit, plot the Y limit, and put the scatter plot in there. And let's go ahead and run this. To be honest, when I'm doing these graphs, there's so many different ways to do that. There's so many different ways to put this code together. To show you what we're doing, it's a lot easier to pull up the graph and then go back up and explain it. So the first thing we want to note here when we're looking at the data is this is the training set. And so we have those who didn't make a purchase. We've drawn a nice area for that. That's defined by the naive Bayes setup. And then we have those who did make a purchase, the green. And you can see that some of the green dots fall into the red area and some of the red dots fall into the green. So even our training set isn't going to be 100%. We couldn't do that. And so when we're looking at our different data coming down, we can kind of arrange our X1, X2 so we have a nice plot going on, and then we're going to create the contour. That's that nice line that's drawn down the middle on here with the red-green. That's what this is doing right here with the reshape. And notice that we had to do the dot T. If you remember from NumPy, if you did the NumPy module, you end up with pairs, X1, X2, X1, X2, next row, and so forth. You have to flip it so it's all one row. You have all your X1s and all your X2s. So this is what we're kind of looking for right here on this setup. And then the scatter plot is, of course, your scattered data across there. We're just going through all the points. That puts these nice little dots onto our setup on here. And we have our estimated salary and our age. And then, of course, the dots are, did they make a purchase or not? And just a quick note, this is kind of funny. You can see up here where it says X set, Y set equals X train, Y train, which seems kind of a little weird to do. This is because this is probably originally a definition. So it's its own module that could be called over and over again. And which is really a good way to do it, because the next thing we're going to want to do is do the exact same thing, but we're going to visualize the test set results. That way we can see what happened with our test group, our 25%. And you can see down here we have the test set, and if you look at the two graphs next to each other, this one obviously has 75% of the data, so it's going to show a lot more. This is only 25% of the data. You can see that there's a number that are kind of on the edge as to whether they could guess by age and income they're going to make a purchase or not. But that said, it still is pretty clear. It's pretty good as far as how much the estimate is and how good it does. Now, graphs are really effective for showing people what's going on, but you also need to have the numbers. And so we're going to do from sklearn, we're going to import metrics, and then we're going to print our metrics classification report from the y-test and the y-predict. And you can see here we have precision. Precision of zeros is 90. There's our recall, 0.96. We have an F1 score and a support. And we have our precision, the recall on getting it right. And then we can do our accuracy, the macro average, and the weighted average. So you can see that it pulls in pretty good as far as how accurate it is. You could say it's going to be about 90% is going to guess correctly that they're not going to purchase. And we had an 89% chance that they are going to purchase. And then the other numbers as you get down have a little bit different meaning, but it's pretty straightforward on here. Here's our accuracy, and here's our micro average and the weighted average and everything else you might need. And if you forgot the exact definition of accuracy, it is the true positive, true negative over all of the different setups. Precision is your true positive over all positives, true and false. And recall is a true positive over true positive plus false negative. And we can just real quick flip back there so you can see those numbers on here. Here's our precision, here's our recall, and here's our accuracy on this.
My name is Richard Kirschner. I'm with the Simplilearn team. What's in it for you? Well, today we're going to cover what is a neural network, what can neural networks do, how does a neural network work, types of neural networks, and then we're going to jump into a use case to classify between the photos of dogs and cats. And we'll do that on the Keras with the TensorFlow in the back, but it's a Python script, so that's always my favorite part is when we dive into the actual script. So what is a neural network? So hi guys, I heard you want to know what a neural network is. Here we have, looks like you just went shopping at a red tag sale. My robot's back. So as a matter of fact, you have been using neural network on a daily basis. In today's world, it's just amazing how much we use our new technology. We're not even aware of it. When you ask your mobile assistant to perform a search for you, like saying your Google or Siri or whoever you use, Amazon Web. Self-driving cars, so that's the newest thing coming out. They're just now trying to make those legal in different states in the US and around the world. Even in the UK, they now have self-driving cars going up and down the streets. Pretty amazing. These are all neural network driven. Computer games use it. So a lot of computer games are driven by neural networks in the back end as part of the game system and how it adjusts to the players. And it's also used in processing the map images on your phone. So every time you do a navigation someplace and it opens it up, they now use neural networks to help you find the quickest way to get there. Neural network. A neural network is a system or hardware that is designed to operate like a human brain. In today's development, this is so important to understand because we don't have anything else to compare it to. I'm sure someday in the future, the computer will redefine, or the neural network, or the AI, artificial intelligence, will redefine what these mean. But as far as we can today's world, in today's commercial development, we have to compare it to what humans do. So we want to compare how it operates to a human brain and how it solves problems like a human does. What can a neural network do? And really, we're just going to dive in deeper to what we just covered and look at other examples. So what can a neural network do? Well, let's list out the things neural networks can do for you. Translate text. Boy, we got Google Translate, and Microsoft has their own Translate. They have some really cool, they actually have an earpiece that's supposed to start translating as you talk. What a cool technology. What a cool time to live. Identify faces. Can you imagine all the uses for facial identification? In the case of our sample, or our code that we're going to look at later, we'll be identifying dogs and cats, so not quite as detailed as understanding whose face belongs to who. I'm waiting for the Google glasses to come out so I can see who's who and identify faces as I'm walking around, have a little name tag over them. Not out there yet, but boy, we are close. We can identify the faces, and they have all kinds of technologies to bring that information back to us. Recognize speech goes along with the translate text. So now as you're talking into your assistant, it can use that to do commands, turn lights on, all kinds of things you can do with recognizing speech. Read handwritten text. They're starting to translate all these old text documents that they've had in storage. Instead of doing it individually where somebody's going through each text by themselves in a room, you can picture like an old Raiders of the Lost Ark theme where he's in the back, archaeologists studying the text. Now it's fed into a computer. They take a picture. They even use neural networks to take a scroll that is so messed up that they can't undo the scroll, and they x-ray it, and then they use that x-ray to translate the text off of it without ever opening the scroll. I mean, just way cool stuff they're starting to do with all this. And of course, control robots. What would be a neural network without bringing in the robots? And we have our own favorite robot in the middle who goes to our red tag cell and goes shopping for us. So, these are just a few of the wonderful things that neural networks are being applied to. It's such an infant stage technology. What a wonderful time to jump in. And there are a lot of other things it goes into. I mean, we could spend just forever talking about all the different applications from business to whatever you could even imagine. They're now applying neural networks to help us understand. So now that we talked a little bit about all the cool things you can do with a neural network, let's dive in and say, how does a neural network work? So now we've come far enough to understand how neural network works. Let's go ahead and walk through this in a nice graphical representation. They usually describe a neural network as having different layers. And you'll see that we've identified a green layer, an orange layer, and a red layer. The green layer is the input. So you have your data coming in. It picks up the input signals and passes them to the next layer. The next layer does all kinds of calculations and feature extraction. It's called the hidden layer. A lot of times there's more than one hidden layer. We're only showing one in this picture, but we'll show you how it looks like in a more detail in a little bit. And then finally we have an output layer. This layer delivers the final result. So the only two things we see is the input layer and the output layer. Now let's make use of this neural network and see how it works. Wonder how traffic cameras identify vehicles' registration plate on the road to detect speeding vehicles and those breaking the law? They got me going through a red light the other day, well, last month. That's like the horrible thing. They send you this picture of you and all your information because they pulled it up off of your license plate and your picture. I shouldn't have gone through the red light. So here we are, and we have an image of a car, and you can see the license plate on there. So let's consider the image of this vehicle and find out what's on the number plate. The picture itself is 28 by 28 pixels, and the image is fed as an input to identify the registration plate. Each neuron has a number called activation that represents the grayscale value of the corresponding pixel range. And we range it from 0 to 1. 1 for a white pixel and 0 for a black pixel. And you can see down here we have an example where one of the pixels is registered as like 0.82, meaning it's probably pretty dark. Each neuron is lit up when its activation is close to 1. So as we get closer to black on white, we can really start seeing the details in there. And you can see again the pixel shows us one up there. It's like part of the car, and so it lights up. So pixels in the form of arrays are fed to the input layer. And so we see here the pixel of a car image fed as an input, and you're going to see that the input layer, which is green, is 1 dimension, while our image is 2 dimension. Now when we look at our setup that we're programming in Python, it has a cool feature that automatically does the work for us. If you're working with an older neural network pattern package, you then convert each one of those rows so it's all one array. So you'd have like row 1 and then just tack row 2 onto the end. You can almost feed the image directly into some of these neural networks. The key is though is that if you're using a 28 by 28 and you get a picture of this 30 by 30, shrink the 30 by 30 down to fit the 28 by 28. So you can't increase the number of input, in this case green dots. It's very important to remember when you work on neural networks. And let's name the inputs x1, x2, x3 respectively. So each one of those represents one of the pixels coming in. And the input layer passes it to the hidden layer. And you can see here we now have 2 hidden layers in this image, in the orange, and each one of those pixels connects to each one of those hidden layers. And the interconnections are assigned weights at random. So they get these random weights that come through. If x1 lights up, then it's going to be x1 times this weight going into the hidden layer. And we sum those weights. The weights are multiplied with the input signal, and a bias is added to all of them. So as you can see here, we have x1 comes in, and it actually goes to all the different hidden layers nodes, or in this case whatever you want to call them, network setup, the orange dots. And so you take the value of x1, you multiply it by the weight for the next hidden layer. So x1 goes to hidden layer 1, x1 goes to hidden layer 2, x1 goes to hidden layer 1 node 2, hidden layer 1 node 3, and so on. And the bias, a lot of times they just put the bias in as like another green dot or another orange dot, and they give the bias a value 1, and then all the weights go in from the bias into the next node. So the bias can change. We always just remember that you need to have that bias in there. There's things that can be done with it. Generally, most of the packages out there control that for you, so you don't have to worry about figuring out what the bias is. But if you ever dive deep into neural networks, you got to remember there's a bias, or the answer won't come out correctly. The weighted sum of the input is fed as an input to the activation function to decide which nodes to fire and for feature extraction. As the signal flows within the hidden layers, the weighted sum of inputs is calculated and is fed to the activation function in each layer to decide which nodes to fire. So here's our feature extraction of the number plate. And you can see these are still hidden nodes in the middle. And this becomes important. We're going to take a little detour here and look at the activation function. So we're going to dive just a little bit into the math, so you can start to understand where some of the games go on when you're playing with neural networks and you're programming. So let's look at the different activation functions before we move ahead. Here's our friendly red tag shopping robot. And so one is a sigmoid function. And the sigmoid function, which is 1 over 1 plus e to the minus x, takes the x value, and you can see where it generates almost a 0 and almost a 1 with a very small area in the middle where it crosses over. And we can use that value to feed into another function. So if it's really uncertain, it might have a 0.1 or 0.2 or 0.3, but for the most part it's going to be really close to 1 and really close to, in this case, 0 to 1. The threshold function. So if you don't want to worry about the uncertainty in the middle, you just say, oh, if x is greater than or equal to 0, if not, then x is 0. So it's either 0 or 1. Really straightforward. There's no in between in the middle. And then you have what they call the ReLU function. And you can see here where it puts out the value, but then it says, well, if it's over 1, it's going to be 1. And if it's less than 0, it's 0. So it kind of just dead ends it on those two ends, but allows all the values in the middle. And again, this, like the sigmoid function, allows that information to go to the next level. So it might be important to know if it's a 0.1 or a minus 0.1. The next hidden layer might pick that up and say, oh, this piece of information is uncertain, or this value has a very low certainty to it. And then the hyperbolic tangent function. And you can see here it's 1 minus e to the minus 2x over 1 plus e to the minus 2x. And it's very much along the same theme. A little bit different in here in that it goes between minus 1 and 1. So you'll see some of these, they go 0 to 1, but this one goes minus 1 to 1. And if it's less than 0, it's, it doesn't fire. And if it's over 0, it fires. And it also still puts out a value. So you still have a value that you can get off of that, just like you can with the sigmoid function and the ReLU function. Very similar in use. And I believe originally used to be everything was done in the sigmoid function. That was the most commonly used. And now they just kind of use more the ReLU function. The reason is, one, it processes faster because you already have the value and you don't have to add another compute the 1 over 1 plus e to the minus x for each hidden node. And the data coming off works pretty good as far as putting it into the next level if you want to know just how close it is to 0. How close is it not to functioning? Is it minus 0.1, minus 0.2? Usually they're float values. You get like minus 0.00138 or something. So, important information, but the ReLU is most commonly used these days as far as the setup we're using. But you'll also see the sigmoid function very commonly used also. Now that you know what an activation function is, let's get back to the neural network. So finally, the model would predict the outcome of applying a suitable activation function to the output layer. So we go in here, we look at this, and we have the optical character recognition, OCR, is used on the images to convert it into a text in order to identify what's written on the plate. And as it comes out, you'll see the red node, and the red node might actually represent just a letter A. So there's usually a lot of outputs when you're doing text identification. We're not going to show that on here, but you might have it even in the order. It might be what order the license plate's in. So you might have A, B, C, D, E, F, G, the alphabet plus the numbers, and you might have the 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 places. So it's a very large array that comes out. It's not a small amount of, we show 3 dots coming in, 8 hidden layer nodes, 2 sets of 4. We just show 1 red coming out. A lot of times this is, 28 times 28. If you did 30 times 30, that's 900 nodes. So 28 is a little bit less than that just on the input. And so you can imagine the hidden layer is just as big. Each hidden layer is just as big, if not bigger. And the output is going to be, there's so many digits. It's a lot. It's a huge amount of input and output. But we're only showing you just, it'd be hard to show in one picture. And so it comes up, and this is what it finally gets out on the output, is it identifies a number on the plate. And in this case, we have 08-D-03858. Error in the output is back propagated through the network, and weights are adjusted to minimize the error rate. This is calculated by a cost function. When we're training our data, this is what's used. And we'll look at that in the code when we do the data training. So we have stuff we know the answer to, and then we put the information through, and it says, yes, that was correct, or no. Because remember, we randomly set all the weights to begin with. And if it's wrong, we take that error. How far off are you? Are you off by, if it was like -1, you're just a little bit off. If it's like -300 was your output, remember when we're looking at those different options? Hyperbolic or whatever, and we're looking at the REL. The REL doesn't have a limit on top or bottom. It actually just generates a number. So if it's way off, you're going to have to adjust those weights a lot. But if it's pretty close, you might adjust the weights just a little bit. And you keep adjusting the weights until they fit all the different training models you put in. So you might have 500 training models, and those weights will adjust using the back propagation. It sends the error backward. The output is compared with the original result, and multiple iterations are done to get the maximum accuracy. So not only does it look at each one, but it goes through it and just keeps cycling through the data, making small changes in the network until it gets the right answers. With every iteration, the weights at every interconnection are adjusted based on the error. We're not going to dive into that math because it is a differential equation and it gets a little complicated. But I will talk a little bit about some of the different options they have when we look at the code. So we've explored a neural network. Let's look at the different types of artificial neural networks. And this is like the biggest area growing, is how these all come together. Let's see the different types of neural network. And again, we're comparing this to human learning. So here's a human brain. I feel sorry for that poor guy. So we have a feed-forward neural network. Simplest form of they call it an ANN, a neural network. Data travels only in one direction, input to output. This is what we just looked at. So as the data comes in, all the weights are added, it goes to the hidden layer, all the weights are added, it goes to the next hidden layer, all the weights are added, and it goes to the output. The only time you use the reverse propagation is to train it. So when you actually use it, it's very fast. When you're training it, it takes a while because it has to iterate through all your training data. And you start getting into big data because you can train these with a huge amount of data. The more data you put in, the better trained they get. The applications, vision and speech recognition, actually they're pretty much everything we talked about. Almost all of them use this form of neural network at some level. Radio basis function neural network. This model classifies the data point based on its distance from a center point. What that means is that you might not have training data, so you want to group things together and you create central points, and it looks for all the things, some of these things are just like the other. If you've ever watched the Sesame Street as a kid, that dates me. So it brings things together, and this is a great way. If you don't have the right training model, you can start finding things that are connected you might not have noticed before. Applications, power restoration systems. They try to figure out what's connected, and then based on that, they can fix the problem if you have a huge power system. Cohonen self-organizing neural network. Vectors of random dimensions are input to discrete map comprised of neurons. So they basically find a way to draw, and they say dimensions, or vectors, or planes, because they actually chop the data in 1 dimension, 2 dimension, 3 dimension, 4, 5, 6. They keep adding dimensions and finding ways to separate the data and connect different data pieces together. Applications used to recognize patterns in data, like in medical analysis. The hidden layer saves its output to be used for future prediction. Recurrent neural networks. So the hidden layers remember its output from last time, and that becomes part of its new input. You might use that especially in robotics or flying a drone. You want to know what your last change was and how fast it was going to help predict what your next change you need to make is to get to where the drone wants to go. Applications, text-to-speech, conversation model. So, I talked about drones, but, just identifying on Lex or Google Assistant or any of these, they're starting to add in, I'd like to play a song on my Pandora and I'd like it to be at volume 90%. So you now can add different things in there and it connects them together. The input features are taken in batches like a filter. This allows a network to remember an image in parts. Convolution neural network. Today's world in photo identification and taking apart photos and trying to, have you ever seen that on Google where you have 5 people together? This is the kind of thing separates all those people so that it can do a face recognition on each person. Applications used in signal and image processing. In this case, I use facial images or Google picture images as one of the options. Modular neural network. It has a collection of different neural networks working together to get the output. So, wow, we just went through all these different types of neural networks, and the final one is to put multiple neural networks together. And I mentioned that a little bit when we separated people in a larger photo, individuals in the photo, and then do the facial recognition on each person. So one network is used to separate them, and the next network is then used to figure out who they are and do the facial recognition. Applications still undergoing research. This is the cutting edge. You hear the term pipeline, and there's actual in Python code and in almost all the different neural network setups out there, they now have a pipeline feature usually. And it just means you take the data from one neural network and maybe another neural network, or you put it into the next neural network, and then you take 3 or 4 other neural networks and feed them into another one. So how we connect the neural networks is really just cutting edge, and it's so experimental. I mean, it's almost creative in its nature. There's not really a science to it because each specific domain has different things it's looking at. So if you're in the banking domain, it's going to be different than the medical domain, than the automatic car domain. And suddenly figuring out how those all fit together is just a lot of fun and really cool. So we have our types of artificial neural network. We have our feed-forward neural network. We have our radial basis function neural network. We have our Cohennon self-organizing neural network, recurrent neural network, convolution neural network, and modular neural network, where it brings them all together. And the colors on the brain do not match what your brain actually does, but they do bring it out that most of these were developed by understanding how humans learn. And as we understand more and more of how humans learn, we can build something in the computer industry to mimic that, to reflect that. And that's how these were developed. So, exciting part, use case, problem statement. So this is where we jump in. This is my favorite part. Let's use the system to identify between a cat and a dog. If you remember correctly, I said we're going to do some Python code, and you can see over here my hair is kind of sticking up over the computer, a cup of coffee on one side, and then a little bit of old school, a pencil and a pen on the other side. Yeah, most people now take notes. I love the stickies on the computer. That's great. That is my computer. I have sticky notes on my computer in different colors. So not too far from today's programmer. So the problem is we want to classify photos of cats and dogs using a neural network. And you can see over here we have quite a variety of dogs in the pictures and cats, and just sorting out it is a cat is pretty amazing. And why would anybody want to even know the difference between a cat and a dog? Okay, why? Well, I have a cat door. It'd be kind of fun that instead of having like a little collar with a magnet on it, which is what my cat has, the door would be able to see, oh, that's the cat. That's our cat coming in. Oh, that's the dog. We have a dog too. That's the dog I want to let in. Maybe I don't want to let this other animal in because it's a raccoon. So you can see where you could take this one step further and actually apply this. You could actually start a little startup company idea, a self-identifying door. So this use case will be implemented on Python. I am actually in Python 3.6. It's always nice to tell people the version of Python because that does affect sometimes which modules you load and everything. And we're going to start by importing the required packages. I told you we're going to do this in Keras. So we're going to import from Keras models, a sequential from the Keras layers, conversion 2D or CONV 2D, max pooling 2D, flatten, and dense. And we'll talk about what each one of these do in just a second. But before we do that, let's talk a little bit about the environment we're going to work in. And in fact, let me go ahead and open the website, Keras's website, so we can learn a little bit more about Keras. So here we are on the Keras website, and it's keras.io. That's the official website for Keras. And the first thing you'll notice is that Keras runs on top of either TensorFlow, CNTK, and I think it's pronounced Thano or Theano. What's important on here is that TensorFlow, and the same is true for all these, but TensorFlow is probably one of the most widely used currently packages out there with the Keras. And of course, tomorrow this is all going to change. It's all going to disappear and they'll have something new out there. So make sure when you're learning this code that you understand what's going on and also know the code. I mean, when you look at the code, it's not as complicated once you understand what's going on. The code itself is pretty straightforward. And the reason we like Keras, and the reason that people are jumping on it right now and it's such a big deal is if we come down here, let me just scroll down a little bit, they talk about user friendliness, modularity, easy extensibility, work with Python. Python's a big one because a lot of people in data science now use Python, although you can actually access Keras other ways. If we continue down here is layers. And this is where it gets really cool. When we're working with Keras, you just add layers on. Remember those hidden layers we were talking about? And we talked about the ReLU activation. You can see right here. Let me just up that a little bit in size. There we go. That's big. I can add in an ReLU layer, and then I can add in a softmax layer in the next instance. We didn't talk about softmax. So you can do each layer separate. Now, if I'm working in some of the other kits I use, I take that and I have one setup, and then I feed the output into the next one. This one I can just add hidden layer after hidden layer with the different information in it, which makes it very powerful and very fast to spin up and try different setups and see how they work with the data you're working on. And we'll dig a little bit deeper in here. And a lot of this is very much the same, so when we get to that part, I'll point that out to you also. Now, just a quick side note, I'm using Anaconda with Python in it, and I went ahead and created my own package, and I called it the Keras Python 3.6 because I'm in Python 3.6. 36. Anaconda is cool that way. You can create different environments real easily. If you're doing a lot of different experimenting with these different packages, you probably want to create your own environment in there. And the first thing is you can see right here, there's a lot of dependencies. A lot of these you should recognize by now if you've done any of these videos. If not, kudos for you for jumping in today. Pip install numpy, scipy, the scikit-learn. Pillow and h5py are both needed for the TensorFlow and then putting the Keras on there. And then you'll see here, and pip is just a standard installer that you use with Python. You'll see here that we did pip install TensorFlow since we're going to do Keras on top of TensorFlow. And then pip install, and I went ahead and used the GitHub. So git plus git, and you'll see here github.com. This is one of their releases, one of the most current release on there that goes on top of TensorFlow. And you can look up these instructions pretty much anywhere. This is for doing it on Anaconda. Certainly you'd want to install these if you're doing it in Ubuntu server setup. You'd want to get, I don't think you need the h5py in Ubuntu, but you do need the rest in there because they are dependencies in there, and it's pretty straightforward. And that's actually in some of the instructions they have on their website. So you don't have to necessarily go through this. Just remember their website on there. And then when I'm under my Anaconda Navigator, which I like, you'll see where I have environments, and on the bottom I created a new environment and I called it Keras Python 36, just to separate everything. You can say I have Python 30.5 and Python 3.6. I used to have a bunch of other ones, but I kind of cleaned house recently. And of course, once I go in here, I can launch my Jupyter Notebook, making sure I'm using the right environment that I just set up. This, of course, opens up my, in this case I'm using Google Chrome, and in here I could go and just create a new document in here. And this is all in your browser when you use the Anaconda. Do you have to use Anaconda in Jupyter Notebook? No. You can use any kind of Python editor, whatever setup you're comfortable with and whatever you're doing in there. So let's go ahead and go in here and paste the code in. And we're importing a number of different settings in here. We have import sequential. That's under the models because that's the model we're going to use as far as our neural network. And then we have layers, and we have conversion 2D, max pooling 2D, flatten, dense, and you can actually just kind of guess at what these do. We're working in a 2D photograph, and if you remember correctly, I talked about how the actual input layer is a single array. It's not in 2 dimensions, it's 1 dimension. All these do is these are tools to help flatten the image, so it takes a 2-dimensional image and then it creates its own proper setup. You don't have to worry about any of that. You don't have to do anything special with the photograph. You let the Keras do it. We're going to run this, and you'll see right here they have some stuff that is going to be depreciated and changed because that's what it does. Everything's being changed as we go. You don't have to worry about that too much. If you have warnings, if you run it a second time, the warning will disappear. And this is just imported these packages for us to use. And Jupyter's nice about this that you can do each thing step by step. And I'll go ahead and also zoom in there. A little Control plus. That's one of the nice things about being in a browser environment. So here we are back. Another sip of coffee. If you're familiar with my other videos, you notice I'm always sipping coffee. I always have in my case, latte next to me, an espresso. So the next step is to go ahead and initialize, we're going to call it the CNN, or classifier neural network. And the reason we call it a classifier is because it's going to classify it between 2 things. It's going to be cat or dog. So when you're doing classification, you're picking specific objects. You're specific, it's a true or false, yes, no, it is something or it's not. So first thing, we're going to create our classifier, and it's going to equal sequential. So their sequential setup is the classifier. That's the actual model we're using. That's the neural network. So we call it a classifier. And the next step is to add in our convolution. And let me just do let me shrink that down in size so you can see the whole line. And let's talk a little bit about what's going on here. I have my classifier and I add something. What am I adding? Well, I'm adding my first layer. This first layer we're adding in is probably the one that takes the most work to make sure you have it set correct. And the reason I say that is this is your actual input. And we're going to jump here to the part that says input shape equals 64 by 64 by 3. What does that mean? Well, that means that our picture's coming in, and there's these pictures. Remember we had like the picture of the car was 128 by 128 pixels? Well, this one is 64 by 64 pixels. And each pixel has 3 values. that's where these numbers come from. And it is so important that this matches. I mentioned a little bit that if you have like a larger picture, you have to reformat it to fit this shape. If it comes in as something larger, there's no input nodes. There's no input neural network there that will handle that extra space. So you have to reshape your data to fit in here. Now, the first layer is the most important, because after that, Keras knows what your shape is coming in here, and it knows what's coming out. And so that really sets the stage. Most important thing is that input shape matches your data coming in. And you'll get a lot of errors if it doesn't. You'll go through there and picture number 55 doesn't match it correctly. And guess what it does? It usually gives you an error. And then the activation, if you remember, we talked about the different activations on here. We're using the RELU model. Like I said, that is the most commonly used now because, one, it's fast. It doesn't have the added calculations in it. It just says, here's the value coming out based on the weights and the value going in, and from there, you know, it's if it's over 1, then it's good, or over 0, it's good. If it's under 0, then it's considered not active. And then we have this conversion 2D. What the heck is conversion 2D? I'm not going to go into too much detail in this because this has a couple of things it's doing in here. A little bit more in depth than we're ready to cover in this tutorial. But this is used to convert from the photo, because we have 64 by 64 by 3, and we're just converting it to two-dimensional kind of setup. So it's very aware that this is a photograph and that different pieces are next to each other. And then we're going to add in a second convolutional layer. That's what the CONV stands for, 2D. So these are hidden layers. So we have our input layer and our two hidden layers, and they are two-dimensional because we're dealing with a two-dimensional photograph. And you'll see down here that on the last one we add a max pooling 2D, and we put a pool size equals 2, 2. And so what this is that as you get to the end of these layers, one of the things you always want to think of is what they call mapping and then reducing. Wonderful terminology from the big data. We're mapping this data through all these layers, and now we want to reduce it to only 2 sets. In this case, it's already in 2 sets because it's a 2D photograph. But we had, 2 dimensions we actually have 64 by 64 by 3. So now we're just getting it down to a 2 by 2, just the two-dimensional instead of having the third dimension of colors. And we'll go ahead and run these. We're not really seeing anything on our run script because we're just setting up. This is all set up. And this is where you start playing, because maybe you'll add a different layer in here to do something else to see how it works and see what your output is. That's what makes Keras so nice, is I can, with just a couple flips of code, put in a whole new layer that does a whole new processing and see whether that improves my run or makes it worse. And finally, we're going to do the final setup, which is to flatten. Classifier add a flatten setup, and then we're going to also add a layer, a dense layer, and then we're going to add in another dense layer, and then we're going to build it. We're going to compile this whole thing together. So let's flip over and see what that looks like. And we've even numbered them for you. So we're going to do the flattening. And flatten is exactly what it sounds like. We've been working in a two-dimensional array of picture, which actually is in 3 dimensions because of the pixels. The pixels have a whole other dimension to it of 3 different values. And we've kind of resized those down to 2 by 2. But now we're just going to flatten it. I don't want to have multiple dimensions being worked on by Tensor and by Keras. I want just a single array, so it's flattened out. And then step 4, full connection. So we add in our final 2 layers, and you could actually do all kinds of things with this. You could actually leave out this some of these layers and play with them. You do need to flatten it. That's very important. Then we want to use the dense. Again, we're taking this and we're taking whatever came into it. So once we take all those the 2 dimensions or 3 dimensions as they are, and we flatten it to 1 dimension, we want to take that and we're going to pull it into units of 128. They got that. You can say, where did they get 128 from? You could actually play with that number and get all kinds of weird results. But in this case, we took the 64 plus 64 is 128. You could probably even do this with 64 or 32. Usually you want to keep it in the same multiple of whatever the data shape you're already using is in. And we're using the activation, the RELU, just like we did before. And then we finally filter all that into a single output. And it has how many units? 1. Why? Because we want to know whether true or false. It's either a dog or a cat. You could say 1 is dog, 0 is cat. Or maybe you're a cat lover and it's 1 is cat and 0 is dog. And if you love both dogs and cats, you're going to have to choose. And then we use the sigmoid activation. If you remember from before, we had the RELU and there's also the sigmoid. The sigmoid just makes it clear it's yes or no. We don't want any kind of in-between number coming out. And we'll go ahead and run this, and you'll see it's still all in setup. And then finally we want to go ahead and compile. And let's put the compiling our classifier neural network, and we're going to use the optimizer Atom. And I hinted at this just a little bit before. Where does Atom come in? Where does an optimizer come in? Well, the optimizer is the reverse propagation. When we're training it, it goes all the way through and says error, and then how does it readjust those weights? There are a number of them. Atom is the most commonly used, and it works best on large data. Most people stick with the Atom because when they're testing on smaller data, see if their model is going to go through and get all their errors out before they run it on larger data sets. They're going to run it on Atom anyway, so they just leave it on Atom, most commonly used. But there are some other ones out there. You should be aware of that you might try them if you're stuck in a bind, or you might explore that in the future. But usually Atom is just fine on there. And then you have two more settings. You have loss and metrics. We're not going to dig too much into loss or metrics. These are things you really have to explore Keras because there are so many choices. This is how it computes the error. There's so many different ways on your back propagation and your training. So we're using the Atom model, but you can compute the error by standard deviation squared. They use binary cross entropy. I'd have to look that up to even know what that is. There's so many of these. A lot of times you just start with the ones that look correct, that are most commonly used, and then you have to go read the Keras site and actually see what these different losses and metrics and what different options they have. So we're not going to get too much into them other than to reference you over to the Keras website to explore them deeper. But we are going to go ahead and run them, and now we've set up our classifier. So we have an object classifier, and if you go back up here you'll see that we've added in step 1, we added in our layer for the input. We added a layer that comes in there and uses the RELU for activation, and then it pulls the data. So this is, even though these are two layers, the actual neural network layer is up here, and then it uses this to pull the data into a 2x2. So into a two-dimensional array from a three-dimensional array with the colors. Then we flatten it. So there's our add or flatten. And then we add another dense, what they call dense layer. This dense layer goes in there and it downsizes it to 128. It reduces it. So you can look at this as we're mapping all this data down the two-dimensional setup, and then we flatten it. So we map it to a flattened map, and then we take it and reduce it down to 128. And we use the RELU again. And then finally we reduce that down to just a single output, and we use a sigmoid to do that, to figure out whether it's yes, no, true, false, in this case cat or dog. And then finally, once we put all these layers together, we compile them. That's what we've done here. And we've compiled them as far as how it trains to use these settings for the training, back propagation. So if you remember, we talked about training our setup. And when we go into this, you'll see that we have two data sets. We have one called the training set and the testing set. And that's very standard in any data processing, is you need to have, that's pretty common in any data processing, is you need to have a certain amount of data to train it, and then you got to know whether it works or not. Is it any good? And that's why you have a separate set of data for testing it, where you already know the answer, but you don't want to use that as part of the training set. So in here we jump into part 2, fitting the classifier neural network to the images. And then from Keras, and let me just zoom in there. I always love that about working with Jupyter Notebooks. You can really see. We're going to come in here. We do the Keras pre-processing an image, and we import image data generator. It's so nice of Keras. It's such a high-end product right now going out. And since images are so common, they already have all this stuff to help us process the data, which is great. And so we come in here. We do train data gen, and we're going to create our object for helping us train it, for reshaping the data so that it's going to work with our setup. And we use an image data generator, and we're going to rescale it. And you'll see here we have 1 point, which tells it it's a float value on the rescale over 255. Where does 255 come from? Well, that's the scale in the colors of the pictures we're using. Their value from 0 to 255. So we want to divide it by 255, and it'll generate a number between 0 and 1. They have shear range and zoom range. Horizontal flip equals true. And this, of course, has to do with if the photos are different shapes and sizes. Like I said, it's a wonderful package. You really need to dig in deep to see all the different options you have for setting up your images. For right now, though, we're going to just stick with some basic stuff here. And let me go ahead and run this code. And again, it doesn't really do anything because we're still setting up the pre-processing. Let's take a look at this next set of code. And this one is just huge. We're creating the training set. So the training set is going to go in here and it's going to use our train data gen we just created, .flow from directory. It's going to access, in this case, the path, data set, training set. That's a folder. So it's going to pull all the images out of that folder. Now, I'm actually running this in the folder that the data set's in. So if you're doing the same setup and you load your data in there and you're doing this, make sure wherever your Jupyter Notebook is saving things to that you create this path, or you can do the complete path if you need to, C:/, etc. And the target size, the batch size, and class mode is binary. So the classes, we're switching everything to a binary value. Batch size, what the heck is batch size? Well, that's how many pictures we're going to batch through the training each time. And the target size, 64 by 64. A little confusing, but you can see right here that this is just a general training, and you can go in there and look at all the different settings for your training set. And of course, with different data, we're doing pictures. There's all kinds of different settings depending on what you're working with. Let's go ahead and run that and see what happens. And you'll see that it found 800 images belonging to one classes. So we have 800 images in the training set. And if we're going to do this with the training set, we also have to format the pictures in the test set. Now, we're not actually doing any predictions. We're not actually programming the model yet. All we're doing is preparing the data. So we're going to prepare a training set and the test set. So any changes we make to the training set at this point also have to be made to the test set. So we've done this thing, we've done a train data generator, we've done our training set, and then we also have, remember, our test set of data. So I'm going to do the same thing with that. I'm going to create a test data gen, and we're going to do this image data generator. We're going to rescale 1/255. We don't need the other settings, just the single setting for the test data gen. And we're going to create our test set. We're going to do the same thing we did with the test set, except that we're pulling it from the test set folder. And we'll run that, and you'll see in our test set we found 2,000 images. That's about right. We're using 20% of the images as test and 80% to train it. And then finally we've set up all our data. We've set up all our layers, which is where all the work is cleaning up that data and making sure it's going in there correctly. And we are actually going to fit it. We're going to train our data set. And let's see what that looks like. And here we go. Let's put the information in here. And let's just take a quick look at what we're looking at with our fit generator. We have our classifier.fit generator. That's our back propagation. So the information goes through forward with a picture, and it says, oh, you're either right or you're wrong, and then the error goes backward and reprograms all those weights. So we're training our neural network. And of course we're using the training set. Remember, we created the training set up here. And then we're going steps per epoch. So it's 8,000 steps. Epoch means that's how many times we go through all the pictures. So we're going to rerun each of the pictures, and we're going to go through the whole data set 25 times. But we're going to look at each picture during each epoch 8,000 times. So we're really programming the heck out of this and going back over it. And then they have validation data equals test set. So we have our training set, and then we're going to have our test set to validate it. So we're going to do this all in one shot. And we're going to look at that, and they're going to do 200 steps for each validation. And we'll see what that looks like in just a minute. Let's go ahead and run our training here. And we're going to fit our data. And as it goes, it says epoch 1 of 25. You start realizing that this is going to take a while. On my older computer, it takes about 45 minutes. I have a dual processor. We're processing 10,000 photos. That's not a small amount of photographs to process. So if you're on your laptop, which I am, it's going to take a while. So let's go ahead and go get our cup of coffee and a sip and come back and see what this looks like. So I'm back. You didn't know I was gone. That was actually a lengthy pause there. I made a couple changes, and let's discuss those changes real quick and why I made them. So the first thing I'm going to do is I'm going to go up here and insert a cell above, and let's paste the original code back in there. And you'll see that the original thing was steps per epoch 8,000, 25 epochs, and validation steps 2,000. And I changed these to 4,000 epochs, or 4,000 steps per epoch, 10 epochs, and just 10 validation steps. And this will cause problems if you're doing this as a commercial release. But for demo purposes, this should work. And if you remember, our steps per epoch, that's how many photos we're going to process. In fact, let me go ahead and get my drawing pen out. And let's just highlight that right here. Well, we have 8,000 pictures we're going through. So for each epoch, I'm going to change this to 4,000. I'm going to cut that in half. So it's going to randomly pick 4,000 pictures each time it goes through an epoch. And the epoch is how many processes. So this is 25, and I'm just going to cut that to 10. So instead of doing 25 runs through 8,000 photos each, which you can do the math of 25 times 8,000, I'm only going to do 10 through 4,000. So I'm going to run this 40,000 times through the processes. And the next thing I noted you'll want to notice is that I also changed the validation step. And this would cause some major problems in releasing because I dropped it all the way down to 10. What the validation step does is it says we have 2,000 photos in our trainings or in our testing set. And we're going to use that for validation. Well, I'm only going to use a random 10 of those to validate. So not really the best settings, but let me show you why we did that. Let's scroll down here just a little bit. And let's look at the output here and see what's going on there. So I've got my drawing tool back on, and you'll see here it lists a run. So each time it goes through an epoch, it's going to do 4,000 steps. And this is where the 4,000 comes in. So that's where we have epoch 1 of 10, 4,000 steps. So it's randomly picking half the pictures in the file and going through them. And then we're going to look at this number right here. That is for the whole epoch. And that's 2,411 seconds. And if you remember correctly, you divide that by 60, you get minutes. If you divide that by 60, you get hours. Or you can just divide the whole thing by 60 times 60, which is 3,600. If 3,600 is an hour, this is roughly 45 minutes right here. And that's 45 minutes to process half the pictures. So if I was doing all the pictures, we're talking an hour and a half per epoch times 36. Or no, 25. They had 25 up above. 25. So that's roughly a couple days of processing. Well, for this demo, we don't want to do that. I don't want to come back the next day. Plus, my computer did a reboot in the middle of the night. So we look at this and we say, okay, we're just testing this out. My computer that I'm running this on is a dual core processor, runs 0.9 gigahertz per second. For a laptop, it was good about 4 years ago, but for running something like this, it's probably a little slow. So we cut the times down, and the last one was validation. We're only validating it on a random 10 photos. And this comes into effect because you're going to see down here where we have accuracy, value loss, value accuracy, and loss. Those are very important numbers to look at. So the 10 means I'm only validating across 10 pictures. That is where, here we have value, this is ACC is for accuracy. Value loss, we're not going to worry about that too much, and accuracy. Now accuracy is while it's running, it's putting these two numbers together. That's what accuracy is. And value accuracy is at the end of the epoch. What's our accuracy at the end of the epoch? What is it looking at? In this tutorial, we're not going to go so deep, but these numbers are really important when you start talking about these two numbers reflect bias. That is really important. I'll just put that up there. And bias is a little bit beyond this tutorial, but the short of it is if this accuracy, which is being our validation per step, is going down, and the value accuracy continues to go up, that means there's a bias. That means I'm memorizing the photos I'm looking at. I'm not actually looking for what makes a dog, what makes a cat. I'm just memorizing them. And so the more this discrepancy grows, the bigger the bias is. And that is really the beauty of the Keras neural network. It has a lot of built-in features like this that make that really easy to track. So let's go ahead and take a look at the next set of code. So here we are into part 3. We're going to make a new prediction. And so we're going to bring in a couple tools for that, and then we have to process the image coming in and find out whether it's an actual dog or cat, if we can actually use this to identify it. And of course the final step of part 3 is to print prediction. We'll go ahead and combine these, and of course you can see me there adding more sticky notes to my computer screen, hidden behind the screen, and last one was don't forget to feed the cat and the dog. So let's go ahead and take a look at that and see what that looks like in code and put that in our Jupyter notebook. All right, and let's paste that in here. And we'll start by importing NumPy as NP. NumPy is a very common package. I pretty much import it on any Python project I'm working on. Another one I use regularly is pandas. They're just ways of organizing the data. And then NP is usually the standard in most machine learning tools as the return for the data array. Although, you can use a standard data array from Python. And we have Keras pre-processing, import image. This should all look familiar because we're going to take a test image and we're going to set that equal to, in this case, cat or dog 1, as you can see over here. And you know what, let me get my drawing tool back on. So let's take a look at this. We have our test image we're loading, and in here we have test image 1, and this one data hasn't seen this one at all, so this is all new. Oh, let me shrink the screen down. Let me start that over. So here we have my test image, and we went ahead and the cross processing has this nice image setup. So we're going to load the image and we're going to alter it to a 64 by 64 print. So right off the bat, we're going to cross is nice that way. It automatically sets it up for us so we don't have to redo all our images and find a way to reset those. And then we use all those to set the image to an array. So again, we're all in pre-processing the data, just like we pre-processed before with our test information and our training data. And then we use the NumPy. Here's our NumPy. That's from our right up here, import NumPy as in P. Expand the dimensions test image axes equals 0. So it puts it into a single array. And then finally, all that work, all that pre-processing, and all we do is we run the result. We click on here and we go result equals classifier predict test image, and then we find out, well, what is the test image? And let's just take a quick look and just see what that is. And you can see when I ran it, it comes up dog, and if we look at those images, there it is, cat or dog, image number 1. That looks like a nice floppy-eared lab, friendly with his tongue hanging out. It's either that or a very floppy-eared cat. I'm not sure which. But according to our software, it says it's a dog. And we have a second picture over here. Let's just see what happens when we run the second picture. We can go up here and change this from dog image 1 to 2. We'll run that, and it comes down here and says cat. You can see me highlighting it down there as cat. So our process works. We are able to label a dog and a cat just from the pictures. There we go, cleared my drawing tool. And the last thing I want you to notice, when we come back up here to when I ran it, you'll see it has an accuracy of 1 and the value accuracy of 1. Well, the value accuracy is the important one, because the value accuracy is what it actually runs on the test data. Remember, I'm only validating it on a random 10 photos. And those 10 photos just happen to come up 1. Now, when they ran this on the server, it actually came up about 86%. This is why cutting these numbers down so far for a commercial release is bad. So you want to make sure you're a little careful of that when you're testing your stuff, that you change these numbers back when you run it on a more enterprise computer other than your old laptop that you're just practicing on or messing with. And we come down here and again, we had the validation of cat. And so we have successfully built a neural network that could distinguish between photos of a cat and a dog. Imagine all the other things you could distinguish. Imagine all the different industries you could dive into with that, just being able to understand those two different pictures. What about mosquitoes? Could you find the mosquitoes that bite versus the mosquitoes that are friendly? It turns out the mosquitoes that bite us are only 4% of the mosquito population, if even that, maybe 2%. There's all kinds of industries that use this, and there's so many industries that are just now realizing how powerful these tools are. Just in the photos alone, there is a myriad of industries sprouting up. And I said it before, I'll say it again, what an exciting time to live in with these tools that we get to play with. So, key takeaways. Well, we covered what is a neural network. We use all kinds of processing, the map images on your phone. We talked about things that a neural network can do. Translate text, identify faces, all the way to control robots. Lots of exciting things. How does a neural network work? So we discussed that with the different layers, going from the picture to the input layer, to the hidden layers and their weights to the final output layer. We also talked about how it does the math and computing the output as yes or no, categorically true, false. We discussed types of artificial neural networks. A lot of vocabulary there from the feed-forward neural network, which is the most commonly used. That's the neural network we used is a feed-forward neural network that does backward propagation to train. And there's a lot of other ones out there. There's the radial biases, the Cohennon self-organizing recurrent neural network, convolution neural network, modular neural network. The big one was modular because it incorporates pieces of all the other ones so that whatever you're working on now is a huge conglomerate of multiple networks. Just all cutting edge. All of it's new. People even working on it don't even know where it's going. Again, very exciting times. And finally, we dug through my favorite part. You can see with my latte on one side, my old school pens and pencil and all my sticky notes working away. That's not actually me, by the way. You probably guessed that. And we walked through and actually did a cat and dog photo. A simple cat and dog photo. And you could see where some of the problems are in processing large amounts of photographs and data, where that starts to become going from a single machine on my laptop with its lower amount of resources all the way to big data. How if you're processing hundreds and thousands of these photos, This now needs to be set up on an enterprise machine or even on a cluster of computers. Again, significantly past the scope of this. The neat part about it, though, is once you write this code, most of this code, they now have tools that you can almost take the same ideas, if not the actual code, and push it right onto a cluster computation. So really cool times for this. Welcome to Machine Learning Tutorial Part 2. My name is Richard Kirshner with the Simplilearn team. That is www.simplilearn.com. Get certified, get ahead. Today in our second tutorial we're going to cover k-means and linear regression, along with going over the quiz questions we had during our first tutorial. What's in it for you? We're going to cover clustering. What is clustering? K-means clustering, which is one of the most common used clustering tools out there, including a flowchart to understand k-means clustering and how it functions. And then we'll do an actual Python live demo on clustering of cars based on brands. Then we're going to cover logistic regression. What is logistic regression? Logistic regression curve and sigmoid function. And then we'll do another Python code demo to classify a tumor as malignant or benign based on features. And let's start with clustering. Suppose we have a pile of books of different genres. Now we divide them into different groups like fiction, horror, education, and as we can see from this young lady, she definitely is into heavy horror. You can just tell by those eyes and the maple Canadian leaf on her shirt. But we have fiction, horror, and education, and we want to go ahead and divide our books up. Well, organizing objects into groups based on similarity is clustering. And in this case, as we're looking at the books, we're talking about clustering things with known categories. But you can also use it to explore data. So you might not know the categories, you just know that you need to divide it up in some way to conquer the data and to organize it better. But in this case, we're going to be looking at clustering in specific categories. And let's just take a deeper look at that. We're going to use k-means clustering. K-means clustering is probably the most commonly used clustering tool in the machine learning library. K-means clustering is an example of unsupervised learning. If you remember from our previous thing, it is used when you have unlabeled data. So we don't know the answer yet. We have a bunch of data that we want to cluster into different groups. Define clusters in the data based on feature similarity. So we've introduced a couple terms here. We've already talked about unsupervised learning and unlabeled data. So we don't know the answer yet. We're just going to group stuff together and see if we can find an answer of how things connect. We've also introduced feature similarity. Features being different features of the data. Now with books, we can easily see fiction and horror and history books, but a lot of times with data, some of that information isn't so easy to see right when we first look at it. And so k-means is one of those tools where we can start finding things that connect, that match with each other. Suppose we have these data points and want to assign them into a cluster. Now when I look at these data points, I would probably group them into two clusters just by looking at them. I'd say two of these group of data kind of come together. But in k-means, we pick k-clusters and assign random centroids to clusters, where the k-clusters represents two different clusters. We pick k-clusters and assign random centroids to the clusters, then we compute distance from objects to the centroids. Now we form new clusters based on minimum distances and calculate the centroids. So we figure out what the best distance is for the centroid, then we move the centroid and recalculate those distances. Repeat previous two steps iteratively till the cluster centroids stop changing their positions and become static. Repeat previous two steps iteratively till the cluster centroids stop changing and the positions become static. Once the clusters become static, then k-means clustering algorithm is said to be converged. And there's another term we see throughout machine learning is converged. That means whatever math we're using to figure out the answer has come to a solution, or it's converged on an answer. Shall we see the flow chart to understand? Make a little bit more sense by putting it into a nice, easy step-by-step. So we start, we choose k. We'll look at the elbow method in just a moment. We assign random centroids to clusters. And sometimes you pick the centroids, because you might look at the data in a graph and say, oh, these are probably the central points. Then we compute the distance from the objects to the centroids. We take that and we form new clusters based on minimum distance and calculate their centroids. Then we compute the distance from objects to the new centroids. And then we go back and repeat those last two steps. We calculate the distances. So as we're doing it, it brings into the new centroid. And then we move the centroid around and we figure out which objects are closest to each centroid. So the objects can switch from one centroid to the other as the centroids are moved around. And we continue that until it is converged. Let's see an example of this. Suppose we have this data set of 7 individuals and their score on 2 topics, A and B. So here's our subject, in this case referring to the person taking the test. And then we have subject A, where we see what they've scored on their first subject, and we have subject B, and we can see what they score on the second subject. Now let's take 2 farthest apart points as initial cluster centroids. Now remember, we talked about selecting them randomly, or we can also just put them in different points and pick the furthest one apart so they move together. Either one works okay, depending on what kind of data you're working on and what you know about it. So we took the 2 furthest points, 1 and 1, and 5 and 7. And now let's take the 2 farthest apart points as initial cluster centroids. Each point is then assigned to the closest cluster with respect to the distance from the centroids. So we take each one of these points in there, we measure that distance, and you can see that if we measured each of those distances, and you use the Pythagorean theorem for a triangle in this case, because you know the x and the y, and you can figure out the diagonal line from that. Or you can just take a ruler and put it on your monitor. That'd be kind of silly, but it would work if you're just eyeballing it. You can see how they naturally come together in certain areas. Now we again calculate the centroids of each cluster. So cluster 1 and then cluster 2, and we look at each individual dot. There's 1, 2, 3, we're in one cluster. The centroid then moves over. It becomes 1.8, 2.3. So remember, it was at 1 and 1. Well, the very center of the data we're looking at would put it at the roughly 2, 2, but 1.8 and 2.3. And the second one, if we wanted to make the overall mean vector, the average vector of all the different distances to that centroid, we come up with 4, 1 and 5, 4. So we've now moved the centroids. We compare each individual's distance to its own cluster, mean, and to that of the opposite cluster, and we find, we can build a nice chart on here, that as we move that centroid around, we now have a new different kind of clustering of groups, and using Euclidean distance between the points and the mean, we get the same formula. You see new formulas coming up. So we have our individual dots, distance to the mean, centroid of the cluster, and distance to the mean, centroid of the cluster. Only individual 3 is nearer to the mean of the opposite cluster, cluster 2, than its own cluster 1. And you can see here in the diagram where we've kind of circled that 1 in the middle. So when we've moved the centroids of the clusters over, one of the points shifted to the other cluster because it's closer to that group of individuals. Thus, individual 3 is relocated to cluster 2, resulting in a new partition. And we regenerate all those numbers of how close they are to the different clusters. For the new clusters, we will find the actual cluster centroids. So now we move the centroids over. And you can see that we've now formed 2 very distinct clusters on here. On comparing the distance of each individual's distance to its own cluster mean and to that of the opposite cluster, we find that the data points are stable. Hence, we have our final clusters. Now, if you remember, I brought up a concept earlier, on the k-means algorithm. Choosing the right value of k will help in less number of iterations. And to find the appropriate number of clusters in a data set, we use the elbow method. And within sum of squares, WSS, is defined as the sum of the squared distance between each member of the cluster and its centroid. And so you see what we've done here is we have the number of clusters. And as you do the same k-means algorithm over the different clusters, and you calculate what that centroid looks like, and you find the optimal, you can actually find the optimal number of clusters using the elbow. The graph is called as the elbow method. And on this, we guessed at 2 just by looking at the data. But as you can see, the slope, you actually just look for right there where the elbow is in the slope, and you have a clear answer that we want 2 different, to start with k-means equals 2. A lot of times people end up computing k-means equals 2, 3, 4, 5 until they find the value which fits on the elbow joint. Sometimes you can just look at the data, and if you're really good with that specific domain, remember domain, I mentioned that last time, you'll know that where to pick those numbers or where to start guessing at what that k value is. So let's take this, and we're going to use a use case using k-means clustering to cluster cars into brands using parameters such as horsepower, cubic inches, make, year, etc. So we're going to use the dataset cars data, having information about 3 brands of cars, Toyota, Honda, and Nissan. We'll go back to my favorite tool, the Anaconda Navigator with the Jupyter Notebook. And let's go ahead and flip over to our Jupyter Notebook. And in our Jupyter Notebook, I'm going to go ahead and just paste the basic code that we usually start a lot of these off with. We're not going to go too much into this code because we've already discussed NumPy, we've already discussed Matplotlib library, and pandas. NumPy being the number array, pandas being the pandas data frame, and matplot for the graphing. And don't forget, since if you're using the Jupyter Notebook, you do need the Matplotlib library inline so that it plots everything on the screen. If you're using a different Python editor, then you probably don't need that because it'll have a pop-up window on your computer. And we'll go ahead and run this just to load our libraries and our setup into here. The next step is, of course, to look at our data, which I've already opened up in a spreadsheet. And you can see here we have the miles per gallon, cylinders, cubic inches, horsepower, weight pounds, how heavy it is, time it takes to get to 60. My card is probably on this one at about 80 or 90. What year it is. So this is, you can actually see this is kind of older cars, and then the brand, Toyota, Honda, Nissan. So the different cars are coming from all the way from 1971, if we scroll down, to the 80s. We have between the 70s and 80s a number of cars that they've put out. And let's, when we come back here, we're going to do importing the data. So we'll go ahead and do dataset equals. And we'll use pandas to read this in, and it's from a CSV file. Remember, you can always post this in the comments and request the data files for these, either in the comments here on the YouTube video or go to simplilearn.com and request that. The cars CSV, I put it in the same folder as the code that I've stored. So my Python code is stored in the same folder, so I don't have to put the full path. If you store them in different folders, you do have to change this and double check your name variables. And we'll go ahead and run this, and we've chosen dataset arbitrarily because it's a dataset we're importing, and we've now imported our cars CSV into the dataset. As you know, you have to prep the data, so we're going to create the X data. This is the one that we're going to try to figure out what's going on with. And then there's a number of ways to do this, but we'll do it in a simple loop so you can actually see what's going on. So we'll do for I in X dot columns. So we're going to go through each of the columns, and a lot of times it's important. I'll make lists of the columns and do this because I might remove certain columns, or there might be columns that I want to be processed differently. But for this, we can go ahead and take X of I, and we want to go fill NA, and that's a pandas command. But the question is, what are we going to fill the missing data with? We definitely don't want to just put in a number that doesn't actually mean something. And so one of the tricks you can do with this is we can take X of I, and then in addition to that, we want to go ahead and turn this into an integer, because a lot of these are integers. So we'll go ahead and keep it integers. And we add the bracket here. And a lot of editors will do this. They'll think that you're closing one bracket. Make sure you get that second bracket in there if it's a double bracket. That's always something that happens regularly. So once we have our integer of X of I, this is going to fill in any missing data with the average. And I was so busy closing one set of brackets, I forgot that the mean also has brackets in there for the pandas. So we can see here we're going to fill in all the data with the average value for that column. So if there's missing data, it's in the average of the data it does have. And then once we've done that, we'll go ahead and loop through it again and just check and see to make sure everything is filled in correctly. And we'll print, and then we take X is null, and this returns a set of the null value, or the how many lines are null, and we'll just sum that up to see what that looks like. And so when I run this, and so with the X, what we want to do is we want to remove the last column because that had the models. That's what we're trying to see, if we can cluster these things and figure out the models. There is so many different ways to sort the X out. For one, we could take the X and we could go dataset, our variable we're using, and use the iLocation, one of the features that's in pandas. And we could take that and then take all the rows and all but the last column of the data set. And at this time we could do values. We just convert it to values. So that's one way to do this. And if let me just put this down here and print X, it's a capital X we chose, and I run this, you can see it's just the values. We could also take out the values and it's not going to return anything because there's no values connected to it. What I like to do with this is, instead of doing the iLocation, which does integers, more common is to come in here and we have our data set, and we're going to do dataset dot columns. And remember, that lists all the columns. So if I come in here, let me just mark that as red, and I print dataset dot columns, You can see that I have my index here. I have my MPG, cylinders, everything, including the brand, which we don't want. So the way to get rid of the brand would be to do data columns of everything but the last one, -1. So now if I print this, you'll see the brand disappears. And so I can actually just take dataset columns -1, and I'll put it right in here for the columns we're going to look at. And let's unmark this and unmark this. And now if I do an x.head, I now have a new data frame, and you can see right here we have all the different columns except for the brand at the end of the year. And it turns out when you start playing with the data set, you're going to get an error later on, and it'll say cannot convert string to float value. And that's because for some reason these things, the way they recorded them, must have been recorded as strings. So we have a neat feature in here on pandas to convert. And it is simply convert objects. And for this we're going to do convert underscore numeric equals true. And yes, I did have to go look that up. I don't have it memorized, the convert numeric in there. If I'm working with a lot of these things, I remember them, but depending on where I'm at, what I'm doing, I usually have to look it up. And we run that. Oops, I must have missed something in here. Let me double check my spelling. And when I double check my spelling, you'll see I missed the first underscore in the convert objects. And when I run this, it now has everything converted into a numeric value, because that's what we're going to be working with, is numeric values down here. And the next part is that we need to go through the data and eliminate null values. Most people, when they're doing small amounts, working with small data pools, discover afterwards that they have a null value and they have to go back and do this. So, be aware, whenever we're formatting this data, things are going to pop up, and sometimes you go backwards to fix it. And that's fine. That's just part of exploring the data and understanding what you have. And I should have done this earlier, but let me go ahead and increase the size of my window 1 notch. There we go. Easier to see. So we'll do for I in working with x dot columns. We'll page through all the columns. And we want to take x of I, and we're going to change that, and we're going to alter it. And so with this, we want to go ahead and fill in x of I. Pandas has the fill in a, and that just fills in any non-existent missing data. And we'll put my brackets up, and there's a lot of different ways to fill this data. If you have a really large data set, some people just void out that data and then look at it later in a separate exploration of data. One of the tricks we can do is we can take our column and we can find the means. And the means is in our quotation marks. So when we take the columns, we're going to fill in the non-existing one with the means. The problem is that returns a decimal float. So some of these aren't decimals. Certainly, we need to be a little careful of doing this, but for this example, we're just going to fill it in with the integer version of this. It keeps it on par with the other data that isn't a decimal point. And then what we also want to do is we want to double check. A lot of times you do this first part first to double check, then you do the fill, and then you do it again just to make sure you did it right. So we're going to go through and test for missing data. And one of the ways you can do that is simply go in here and take our x of I column. So it's going to go through the x of I column. It says is null. So it's going to return any place there's a null value. It actually goes through all the rows of each column is null, and then we want to go ahead and sum that. So we take that and we add the sum value, and these are all pandas. So is null is a panda command, and so is sum. And if we go through that and we go ahead and run it, and we go ahead and take and run that, you'll see that all the columns have 0 null values. So we've now tested and double checked, and our data is nice and clean. We have no null values. Everything is now a number value. We turned it into numeric. And we've removed the last column in our data. And at this point, we're actually going to start using the elbow method to find the optimal number of clusters. So we're now actually getting into the sklearn part, the k-means clustering on here. I guess we'll go ahead and zoom it up one more notch so you can see what I'm typing in here. And then from sklearn, we're going to our sklearn cluster. We're going to import k-means. I always forget to capitalize the K and the M when I do this. So it's capital K, capital M, k-means. And we'll go ahead and create a array, WCSS equals, we'll make it an empty array. If you remember from the elbow method from our slide, within the sum of squares, WSS is defined as the sum of square distance between each member of the cluster and its centroid. So we're looking at that change in differences as far as a square distance. And we're going to run this over a number of k-mean values. In fact, let's go for I in range, we'll do 11 of them. Range 0 of 11. And the first thing we're going to do is we're going to create the actual, we'll do it all lowercase. And so we're going to create this object from the k-means that we just imported. And the variable that we want to put into this is in clusters. And we're going to set that equals to I. That's the most important one because we're looking at how increasing the number of clusters changes our answer. There are a lot of settings to the k-means. Our guys in the back did a great job just kind of playing with some of them. The most common ones that you see in a lot of stuff is how you init your k-means. So we have k-means plus plus. This is just a tool to let the model itself be smart how it picks its centroids to start with, its initial centroids. We only want to iterate no more than 300 times. We have a max iteration we put in there. We have the nth init, the random state equals 0. You really don't need to worry too much about these when you're first learning this. As you start digging in deeper, you start finding that these are shortcuts that will speed up the process as far as the setup. But the big one that we're working with is the in clusters equals I. So we're going to literally train our k-means 11 times. We're going to do this process 11 times. And if you're working with big data, you know the first thing you do is you run a small sample of the data so you can test all your stuff on it. And you can already see the problem that if I'm going to iterate through a terabyte of data 11 times, and then the k-means itself is iterating through the data multiple times, that's a heck of a process. So you got to be a little careful with this. A lot of times, though, you can find your elbow, using the elbow method, find your optimal number on a sample of data, especially if you're working with larger data sources. So we want to go ahead and take our k-means, and we're just going to fit it. If you're looking at any of the sklearn, very common, you fit your model. And if you remember correctly, our variable we're using is the capital X. And once we fit this value, we go back to the array we made, and we want to go ahead and just append that value on the end. And it's not the actual fit we're pinning in there, it's when it generates the value you're looking for is inertia. So k-means.inertia will pull that specific value out that we need. And let's get a visual on this. We'll do our PLT plot, and what we're plotting here is first the x-axis, which is range 0, 11, so that will generate a nice little plot there, and the WCSS for our y-axis. It's always nice to give our plot a title, and let's see, we'll just give it the elbow method for the title, and let's get some labels. So let's go ahead and do PLT X label, and what we'll do number of clusters for that, and PLT Y label. And for that we can do, oops, there we go, WCSS, since that's what we're doing on the plot on there. And finally we want to go ahead and display our graph, which is simply PLT dot show. There we go. And because we have it set to inline, it'll appear inline. Hopefully I didn't make a type error on there. And you can see we get a very nice graph. You can see a very nice elbow joint there at 2, and again right around 3 and 4, and then after that there's not very much. Now, as a data scientist, if I was looking at this, I would do either 3 or 4, and I'd actually try both of them to see what the output looked like. And they've already tried this in the back, so we're just going to use 3 as a setup on here. And let's go ahead and see what that looks like when we actually use this to show the different kinds of cars. And so let's go ahead and apply the k-means to the cars data set. And basically we're going to copy the code that we looped through up above, where k-means equals k-means number of clusters, and we're just going to set the number of clusters to 3, since that's what we're going to look for. And you could do 3 and 4 on this and graph them just to see how they come up differently. It'd be kind of curious to look at that. But for this, we're just going to set it to 3. Go ahead and create our own variable, y k-means, for our answers. And we're going to set that equal to, whoops, a double equal there, to k-means, but we're not going to do a fit. We're going to do a fit predict is the setup you want to use. And when you're using untrained models, you'll see a slightly different, because usually you see fit and then you see just the predict. But we want to both fit and predict the k-means on this. And that's fit underscore predict, and then our capital X is the data we're working with. And before we plot this data, we're going to do a little pandas trick. We're going to take our x value and we're going to set x as matrix. So we're converting this into a nice rows and columns kind of setup, but we're going to have columns equals none, so it's just going to be a matrix of data in here. And let's go ahead and run that. A little warning. You'll see these warnings pop up because things are always being updated. So there's like minor changes in the versions and future versions. Instead of matrix, now it's more common to set it dot values instead of doing as matrix. But as matrix works just fine for right now, and you'll want to update that later on. But let's go ahead and dive in and plot this and see what that looks like. And before we dive into plotting this data, I always like to take a look and see what I am plotting. So let's take a look at y k-means. I'm just going to print that out down here. And we see we have an array of answers. We have 2, 1, 0, 2, 1, 2. So it's clustering these different rows of data based on the 3 different spaces it thinks it's going to be. And then let's go ahead and print x and see what we have for x. And we'll see that x is an array, it's a matrix, so we have our different values in the array. And what we're going to do, it's very hard to plot all the different values in the array. So we're only going to be looking at the first 2, or positions 0 and 1. And if you were doing a full presentation in front of the board meeting, you might actually do a little different and dig a little deeper into the different aspects, because this is all the different columns we looked at. But we'll only look at columns 1 and 2 for this to make it easy. So let's go ahead and clear this data out of here, and let's bring up our plot. And we're going to do a scatter plot here. So PLT scatter, and this looks a little complicated, so let's explain what's going on with this. We're going to take the x values, and we're only interested in y of k-means equals 0, the first cluster. Okay? And then we're going to take value 0 for the x-axis, and then we're going to do the same thing here. We're only interested in k-means equals 0, but we're going to take this second column. So we're only looking at the first 2 columns in our answer, or in the data. And then the guys in the back played with this a little bit to make it pretty. And they discovered that it looks good if it has a size equals 100. That's the size of the dots. We're going to use red for this one. And when they were looking at the data and what came out, it was definitely the Toyota on this. We're just going to go ahead and label it Toyota. Again, that's something you really have to explore in here as far as playing with those numbers and see what looks good. We'll go ahead and hit enter in there. And I'm just going to paste in the next 2 lines, which is the next 2 cars. And this is our Nissan and Honda. And you'll see with our scatter plot, we're now looking at where y underscore k-means equals 1. And we want the 0 column, and y k-means equals 2. Again, we're looking at just the first 2 columns, 0 and 1. And each of these rows then corresponds to Nissan and Honda. And I'll go ahead and hit enter on there. And finally, let's take a look and put the centroids on there. Again, we're going to do a scatter plot. And on the centroids, you can just pull that from our k-means, the model we created, dot cluster centers, and we're going to just do all of them in the first number and all of them in the second number, which is 0, 1, because you always start with 0 and 1. And then they were playing with the size and everything to make it look good. We'll do a size of 300. We're going to make the color yellow, and we'll label them. It's always good to have some good labels, centroids. And then we do want to do a title, PLT title, and pop up there. PLT title, because you always want to make your graphs look pretty, and we'll call it clusters of car make. And one of the features of the plot library is you can add a legend. It'll automatically bring in it since we've already labeled the different aspects of the legend with Toyota, Nissan, and Honda. And finally, we want to go ahead and show, so we can actually see it. And remember, it's inline, so if you're using a different editor that's not the Jupyter Notebook, you'll get a pop-up of this. And you should have a nice set of clusters here. So we can look at this, and we have clusters of Honda in green, Toyota in red, Nissan in purple. And you can see where they put the centroids to separate them. Now, when we're looking at this, we can also plot a lot of other different data on here because we only looked at the first two columns. This is just column 1 and 2, or 0, 1 as you label them in computer scripting. But you can see here we have a nice clusters of car make, and we were able to pull out the data, and you can see how just these two columns form very distinct clusters of data. So if you were exploring new data, you might take a look and say, well, what makes these different? Almost going in reverse, you start looking at the data and pulling apart the columns to find out why is the first group set up the way it is. Maybe you're doing loans and you want to go, well, why is this group not defaulting on their loans? And why is the last group defaulting on their loans? And why is the middle group 50% defaulting on their bank loans? And you start finding ways to manipulate the data and pull out the answers you want. So now that you've seen how to use k-mean for clustering, let's move on to the next topic. Now let's look into logistic regression. The logistic regression algorithm is the simplest classification algorithm used for binary or multi-classification problems. And we can see we have our little girl from Canada who's into horror books is back. That's actually really scary when you think about that with those big eyes. In the previous tutorial, we learned about linear regression, dependent and independent variables. So, to brush up, y equals mx plus c. Very basic algebraic function of y and x. The dependent variable is the target class variable we are going to predict. The independent variables, x1 all the way up to xn, are the features or attributes we're going to use to predict the target class. We know what a linear regression looks like, but using the graph we cannot divide the outcome into categories. It's really hard to categorize 1.5, 3.6, 9.8. For example, a linear regression graph can tell us that with increase in number of hours studied, the marks of a student will increase, but it will not tell us whether the student will pass or not. In such cases where we need the output as categorical value, we will use logistic regression. And for that, we're going to use the sigmoid function. So you can see here we have our marks, 0 to 100, number of hours studied. That's going to be what they're comparing it to in this example. And we usually form a line that says y equals mx plus c. And when we use the sigmoid function, we have p equals 1 over 1 plus e to the minus y. It generates a sigmoid curve. And so you can see right here when you take the ln, which is the natural logarithm. I always thought it should be nl, not ln. That's just the inverse of e, or e to the minus y. And so when we do this, we get ln of p over 1 minus p equals m times x plus c. That's the sigmoid curve function we're looking for. And we can zoom in on the function, and you'll see that the function, as it derives, goes to 1 or to 0, depending on what your x value is. And the probability, if it's greater than 0.5, the value is automatically rounded off to 1, indicating that the student will pass. So if they're doing a certain amount of studying, they will probably pass. Then you have a threshold value at the 0.5. It automatically puts that right in the middle usually. And your probability, if it's less than 0.5, the value rounded off to 0, indicating the student will fail. So if they're not studying very hard, they're probably going to fail. This, of course, is ignoring the outliers of that one student who's just a natural genius and doesn't need any studying to memorize everything. That's not me, unfortunately. Have to study hard to learn new stuff. Problem statement. To classify whether a tumor is malignant or benign. And this is actually one of my favorite data sets to play with because it has so many features, and when you look at them, you really are hard to understand. You can't just look at them and know the answer. So it gives you a chance to kind of dive into what data looks like when you aren't able to understand the specific domain of the data. But I also want you to remind you that in the domain of medicine, if I told you that my probability was really good, it classified things at, say, 90% or 95%, and I'm classifying whether you're going to have a malignant or a benign tumor, I'm guessing that you're going to go get it tested anyways. So you got to remember the domain we're working with. So why would you want to do that if you know you're just going to go get a biopsy because, you know, it's that serious? This is like an all or nothing. Just referencing the domain, it's important. It might help the doctor know where to look just by understanding what kind of tumor it is. So it might help them or aid them in something they missed from before. So let's go ahead and dive into the code, and I'll come back to the domain part of it in just a minute. So use case, and we're going to do our normal imports here, where we're importing NumPy, Pandas, Seaborn, the Matplot library, and we're going to do Matplot library inline since I'm going to switch over to Anaconda. So let's go ahead and flip over there and get this started. So I've opened up a new window in my Anaconda Jupyter Notebook. And by the way, Jupyter Notebook, you don't have to use Anaconda for the Jupyter Notebook. I just love the interface and all the tools that Anaconda brings. So we got our import NumPy as in P for our NumPy number array. We have our Pandas PD. We're going to bring in Seaborn to help us with our graphs as SNS. So many really nice tools in both Seaborn and Matplot library. Then we'll do our Matplot library.pyplot as PLT, and then of course we want to let it know to do it in line. And let's go ahead and just run that so it's all set up. And we're just going to call our data, not creative today, equals PD, and this happens to be in a CSV file. So we'll use the pd.read_CSV, and I happen to name the file, I renamed it, data for p2.csv. You can, of course, write in the comments below the YouTube and request for the data set itself, or go to the Simplilearn website, and we'll be happy to supply that for you. And let's just open up the data before we go any further, and let's just see what it looks like in a spreadsheet. So when I pop it open in a local spreadsheet, and this is just a CSV file, comma separated variables, we have an ID, so I guess they categorize this for reference or what ID, which test was done. The diagnosis, M for malignant, B for benign, so there's two different options on there. And that's what we're going to try to predict is the M and B and test it. And then we have like the radius mean or average, the texture average, perimeter mean, area mean, smoothness. I don't know about you, but unless you're a doctor in the field, most of the stuff, I mean, you can guess what concave means just by the term concave, but I really wouldn't know what that means in the measurements they're taking. So they have all kinds of stuff like how smooth it is, the symmetry, and these are all float values. We can just page through them real quick, and you'll see there's, I believe, 36 if I remember correctly in this one. So there's a lot of different values they take and all these measurements they take when they go in there and they take a look at the different growth, the tumorous growth. So back in our data, and I put this in the same folder as the code. So I saved this code in that folder. Obviously, if you have it in a different location, you want to put the full path in there. And we'll just do Pandas first 5 lines of data with the data.head. When we run that, we can see that we have pretty much what we just looked at. We have an ID, we have a diagnosis. If we go all the way across, you'll see all the different columns coming across displayed nicely for our data. And while we're exploring the data, our Seaborn, which we referenced as SNS, makes it very easy to go in here and do a joint plot. You'll notice very similar to, because it is sitting on top of the plot library, so the joint plot does a lot of work for us. And we're just going to look at the first 2 columns that we're interested in, the radius mean and the texture mean. We'll just look at those 2 columns. And data equals data. So that tells it which 2 columns we're plotting and that we're going to use the data that we pulled in. And let's just run that. And it generates a really nice graph on here. And there's all kinds of cool things on this graph to look at. I mean, we have the texture mean and the radius mean, obviously the axes. You can also see, and one of the cool things on here is you can also see the histogram. They show that for the radius mean. Where is the most common radius mean come up and where the most common texture is. So we're looking at on each growth its average texture, and on each radius its average radius on there. It gets a little confusing because we're talking about the individual object's average, and then we can also look over here and see the histogram showing us the median or how common each measurement is. And that's only 2 columns, so let's dig a little deeper into Seaborn. They also have a heat map. And if you're not familiar with heat maps, a heat map just means it's in color. That's all that means. Heat map. I guess the original ones were plotting heat density on something, and so ever since then it's just called a heat map. And we're going to take our data and get our corresponding numbers to put that into the heat map. And that's simply data.corr. For that, that's a pandas expression. So remember, we're working in a pandas data frame, so that's one of the cool tools in pandas for our data. And let's just pull that information into a heat map and see what that looks like. And you'll see that we're now looking at all the different features. We have our ID, we have our texture, we have our area, our compactness, concave points. And if you look down the middle of this chart, diagonal, going from the upper left to bottom right, it's all white. That's because when you compare texture to texture, they're identical. So they're 100%, or in this case, a perfect 1 in their correspondence. And you'll see that when you look at, say, area, or right below it, it has almost a black on there when you compare it to texture. So these have almost no corresponding data. They don't really form a linear graph or something that you can look at and say how connected they are. They're very scattered data. This is really just a really nice graph to get a quick look at your data. It doesn't so much change what you do, but it changes verifying. So when you get an answer or something like that, or you start looking at some of these individual pieces, you might go, hey, that doesn't match. According to showing our heat map, this should not correlate with each other. And if it is, you're going to have to start asking, well, why? What's going on? What else is coming in there? But it does show some really cool information on here. I mean, we can see from the ID, there's no real one feature that just says, if you go across the top line, that lights up. There's no one feature that says, hey, if the area is a certain size, then it's going to be benign or malignant. It says there's some that sort of add up. And that's a big hint in the data that we're trying to ID this, whether it's malignant or benign. That's a big hint to us as data scientists to go, okay, we can't solve this with any one feature. It's going to be something that includes all the features, or many of the different features, to come up with a solution for it. And while we're exploring the data, let's explore one more area, and let's look at data.isNull. We want to check for null values in our data. And if you remember from earlier in this tutorial, we did it a little differently where we added stuff up and summed them up. You can actually, with pandas, do it really quickly, data.isNull, and sum it, and it's going to go across all the columns. So when I run this, you're going to see all the columns come up with no null data. So we've just to rehash these last few steps, we've done a lot of exploration. We have looked at the first 2 columns and seen how they plot with the Seaborn, with a joint plot which shows both the histogram and the data plotted on the XY coordinates. And obviously you can do that more in detail with different columns and see how they plot together. And then we took and did the Seaborn heat map, the SNS heat map of the data. And you can see right here where it did a nice job showing us some bright spots where stuff correlates with each other and forms a very nice combination or points of scattering points. And you can also see areas that don't. And then finally we went ahead and checked the data. Is the data null value? Do we have any missing data in there? Very important step because it'll crash later on. If you forget to do this step, it will remind you when you get that nice error code that says null values. Okay, so not a big deal if you miss it, but it's no fun having to go back when you're in a huge process and you've missed this step, and now you're 10 steps later and you got to go remember where you were pulling the data in. So we need to go ahead and pull out our x and our y. So we just put that down here, and we'll set the x equal to, and there's a lot of different options here. Certainly we could do x equals all the columns except for the first 2, because if you remember the first 2 is the ID and the diagnosis. So that certainly would be an option. But what we're going to do is we're actually going to focus on the worst radius, the worst texture, parameter, area, smoothness, compactness, and so on. One of the reasons to start dividing your data up when you're looking at this information is sometimes the data will be the same data coming in. So if I have 2 measurements coming into my model, it might overweigh them. it might overpower the other measurements because it's basically taking that information in twice. That's a little bit past the scope of this tutorial. What I want you to take away from this, though, is that we are dividing the data up into pieces, and our team in the back went ahead and said, hey, let's just look at the worst. So I'm going to create an array, and you'll see this array: radius worst, texture worst, perimeter worst. We've just taken the worst of the worst, and I'm just going to put that in my X. So this X is still a pandas data frame, but it's just those columns. And our Y, if you remember correctly, is going to be, oops, hold on one second. It's not X, it's data. There we go. So X equals data, and then it's a list of the different columns, the worst of the worst. And if we're going to take that, then we have to have our answer for our Y, for the stuff we know. And if you remember correctly, we're just going to be looking at the diagnosis. That's all we care about, is what is it diagnosed? Is it benign or malignant? And since it's a single column, we can just do diagnosis. Oh, I forgot to put the brackets. There we go. Okay. So it's just diagnosis on there. And we can also real quickly do like x dot head if you want to see what that looks like. And y dot head. And run this. And you'll see it only does the last one. I forgot about that if you don't do print. You can see that the y dot head is just MMM because the first ones are all malignant. And if I run this, the x dot head is just the first 5 values of radius worst, texture worst, parameter worst, area worst, and so on. I'll go ahead and take that out. So moving down to the next step, we've built our 2 data sets, our answer and then the features we want to look at. In data science, it's very important to test your model. So we do that by splitting the data. And from sklearn model selection, we're going to import train test split. So we're going to split it into 2 groups. There are so many ways to do this. I noticed in one of the more modern ways, they actually split it into 3 groups, and then you model each group and test it against the other groups. So you have all kinds of, and there's reasons for that, which is past the scope of this, and for this particular example isn't necessary. For this, we're just going to split it into 2 groups, one to train our data and one to test our data. And the sklearn model selection, we have train test split. You could write your own quick code to do this where you just randomly divide the data up into 2 groups, but they do it for us nicely. And we can actually do it in one statement with this, where we're going to generate 4 variables: capital X train, capital X test. So we have our training data we're going to use to fit the model, and then we need something to test it. And then we have our Y train, so we're going to train the answer, and then we have our test. So this is the stuff we want to see how good it did on our model. And we'll go ahead and take our train test split that we just imported, and we're going to do X and our Y, our 2 different data that's going in for our split. And then the guys in the back came up and wanted us to go ahead and use a test size equals 0.3. That's test underscore size. Random state. It's always nice to kind of switch your random state around, but not that important. What this means is that the test size is we're going to take 30% of the data and we're going to put that into our test variables, our Y test and our X test. And we're going to do 70% into the X train and the Y train. So we're going to use 70% of the data to train our model and 30% to test it. Let's go ahead and run that and load those up. So now we have all our stuff split up and all our data ready to go. And now we get to the actual logistics part. We're actually going to create our model. So let's go ahead and bring that in from sklearn. We're going to bring in our linear model, and we're going to import logistic regression. That's the actual model we're using. And we'll call it log model. Oops, there we go, model. And let's just set this equal to our logistic regression that we just imported. So now we have a variable log model set to that class for us to use. And with most of the models in the sklearn, we just need to go ahead and do a fit on there. And we use our X train that we separated out with our Y train. And let's go ahead and run this. So once we've run this, we'll have a model that fits this data, that 70% of our training data. And of course it prints this out that tells us all the different variables that you can set on there. There's a lot of different choices you can make. But for what we're doing, we're just going to let all the defaults sit. We don't really need to mess with those on this particular example. And there's nothing in here that really stands out as super important until you start fine-tuning it. But for what we're doing, the basics will work just fine. And then we need to go ahead and test out our model. Is it working? So let's create a variable yPredict, and this is going to be equal to our log model, and we want to do a predict. Again, very standard format for the sklearn library is taking your model and doing a predict on it. And we're going to test yPredict against the yTest. So we want to know what the model thinks it's going to be. That's what our yPredict is. And with that, we want the capital X test. So we have our train set and our test set, and now we're going to do our yPredict. And let's go ahead and run that. And if we print yPredict, let me go ahead and run that, you'll see it comes up and it prints a nice array of B and M for benign and malignant for all the different test data we put in there. So it does pretty good. We're not sure exactly how good it does, but we can see that it actually works and is functional. It was very easy to create. You'll always discover with our data science that as you explore this, you spend a significant amount of time prepping your data and making sure your data coming in is good. There's a saying, good data in, good answers out. Bad data in, bad answers out. That's only half the thing. That's only half of it. Selecting your models becomes the next part as far as how good your models are. And then, of course, fine-tuning it depending on what model you're using. So we come in here, we want to know how good this came out. So we have our yPredict here, logModel.predictXtest. So for deciding how good our model is, we're going to go from the sklearn.metrics, we're going to import classification report. And that just reports how good our model is doing, and then we're going to feed it the model data. And let's just print this out. And we'll take our classification report, and we're going to put into there our test, our actual data. So this is what we actually know is true. And our prediction, what our model predicted for that data on the test side. And let's run that and see what that does. So we pull that up, you'll see that we have a precision for benign and malignant, B and M. And we have a precision of 93 and 91, a total of 92. So it's kind of the average between these two, 92. There's all kinds of different information on here. Your F1 score, your recall, your support coming through on this. And for this, I'll go ahead and just flip back to our slides that they put together for describing it. And so here we're going to look at the precision using the classification report. And you see this is the same printout I had up above. Some of the numbers might be different because it does randomly pick out which data we're using. So this model is able to predict the type of tumor with 91% accuracy. So we look back here, you'll see where we have benign and malignant. It actually is 92 coming up here. But we're looking at about a 92-91% precision. And remember, I reminded you about domains. So when we're talking about the domain of a medical domain with a very catastrophic outcome, at 91 or 92% precision, you're still going to go in there and have somebody do a biopsy on it. Very different than if you're investing money and there's a 92% chance you're going to earn 10% and 8% chance you're going to lose 8%, you're probably going to bet the money. Because at that odds, it's pretty good that you'll make some money. And in the long run, you do that enough, you definitely will make money. And also with this domain, I've actually seen them use this to identify different forms of cancer. That's one of the things that they're starting to use these models for. Because then it helps the doctor know what to investigate. So that wraps up this section. We're going to go in there and let's discuss the answer to the quiz asked in Machine Learning Tutorial Part 1. Can you tell what's happening in the following cases? Grouping documents into different categories based on the topic and content of each document. This is an example of clustering where k-means clustering can be used to group the documents by topics using bag of words approach. So if you've gotten in there that you're looking for clustering, and hopefully you had at least one or two examples like k-means that are used for clustering different things, then give yourself a 2 thumbs up. B. Identifying handwritten digits in images correctly. This is an example of classification. The traditional approach to solving this would be to extract digit-dependent features like curvature of different digits, etc., and then use a classifier like SVM to distinguish between images. Again, if you got the fact that it's a classification example, give yourself a thumb up. And if you're able to go, hey, let's use SVM or another model for this, give yourself those 2 thumbs up on it. C. Behavior of a website indicating that the site is not working as designed. This is an example of anomaly detection. In this case, the algorithm learns what is normal and what is not normal, usually by observing the logs of the website. Give yourself a thumbs up if you got that one. And just for a bonus, can you think of another example of anomaly detection? One of the ones I use it for in my own business is detecting anomalies in stock markets. Stock markets are very fickle and they behave very erratic. So finding those erratic areas and then finding ways to track down why they're erratic. Was something released in social media? Was something released? You can see where knowing where that anomaly is can help you to figure out what the answer is to it in another area. D. Predicting salary of an individual based on his or her years of experience. This is an example of regression. This problem can be mathematically defined as a function between independent, years of experience, and dependent variables, salary of an individual. And if you guessed that this was a regression model, give yourself a thumbs up. And if you're able to remember that it is between independent and dependent variables and that terms, give yourself 2 thumbs up. Summary. So to wrap it up, we went over what is k-means. And we went through also the chart of choosing your elbow method and assigning a random centroid to the clusters, computing the distance, and then going in there and figuring out what the minimum centroids is and computing the distance and going through that loop until it gets the perfect centroid. And we looked into the elbow method to choose k based on running our clusters across a number of variables and finding the best location for that. We did a nice example of clustering cars with k-means, even though we only looked at the first 2 columns to make it simple and easy to graph. You can easily extrapolate that and look at all the different columns and see how they all fit together. And we looked at what is logistic regression. We discussed the sigmoid function, what is logistic regression, and then we went into an example of classifying tumors with logistics. I hope you enjoyed part 2 of machine learning.
So in today's session, we will discuss what RNN model is. Moving ahead, we will see why should we use RNN. After that, we will see how does RNN work, recurrent neural network. After covering these topics, we will move forward and see types of RNN, recurrent neural network, and applications of RNN. At the end, we will do a hands-off live demo of sentiment analysis using RNN. So before starting, let us have a simple question to brush up our knowledge. So question is, what are the application of RNN? Okay, NLP, time series, image captioning, and all of the above. Please answer in the comment section below and we will update the correct answer in the pinned comments, or you can pause this video, give it a thought and answer in the comment section. Before we move on to the programming part, let's discuss what RNN is and proceed further for the same. So what is RNN? Recurrent neural network. So RNN work on the principle of saving output on a particular layer and feeding this back to the input in order to predict the output of the layer. This is how can convert a feed neural network into a recurrent neural network, RNN. The node in different layers of neural network are compressed to form a single layer of recurrent neural network. A, B, and C are the parameters of neural network. Now that you understand what RNN is, let's look at the way why RNN. Okay, so why RNN? RNN were created because there are few issues in the feed-forward neural network. Cannot handle the sequential data, considers only the current input, cannot memorize previous input. Okay, so the solution of these issues is RNN. And RNN can handle sequential data, accepting the current input data and previously received input data. So RNN can memorize previous input due to their internal memory. So moving forward, let's see how does RNN networks work. Okay, so the input layer X takes an input to the neural network and processes it and passes it into the middle layer. The middle layer H can consist of multiple hidden layers, each with its own activation function and weight and biases. If you have a neural network where the various parameters of different hidden layers are not affected by the previous layer, that is, the neural network does not have the memory, then you can use RNN. So the RNN will standardize the different activation function and weights and biases so that each hidden layer has the same parameter. Then instead of creating multiple hidden layers, it will create one and loop over it as many times it has required. So moving forward, let's see types of RNN. So there are 4 types of RNN. One-to-one, one-to-many, many-to-many, and many-to-one. So let's see one-to-one RNN. So this type of neural network is known as the vanilla neural network. It is used for general machine learning problem which has a single input and a single output. Now see one-to-many RNN. This type of neural network has a single input and multiple outputs. An example of this is the image captioning. Now let's see many-to-one RNN. This RNN take a sequence of input and generates a single output. Sentiment analysis is a good example of this kind of neural network, where a given sentence can be classified as expressing positive or negative sentiment. And the last one is many-to-many RNN. This RNN takes a sequence of inputs and generates a sequence of output. Machine translation is the one of the example. So moving forward, let's see application of recurrent neural network. First one is image captioning. RNNs are used to caption an image by analyzing the activities present. The second one is time series prediction. Any time series problem like predicting the prices of stocks in a particular month can be solved using RNN. And the third one is natural language processing. Text mining and sentiment analysis can be carried out using RNN for NLP, natural language processing. The fourth one is machine translation. Given an input in one language, RNNs can be used to translate the input into different language as output. So now let's move to the programming part. First, we will import some libraries, major libraries for the first we will import for the data frame. So I will write import SPD. The second one is import numpy as np. So Pandas is a software library written for the Python programming language for data manipulation and analysis. In particular, it offers a data structure and operations for manipulating numerical tables and the time series. And this NumPy. NumPy is a library for the Python programming language, adding support to four large multi-dimensional array and matrices, along with a large collection of high-level mathematical function to operate on these arrays. Okay, so for plotting, we will import some libraries like Seaborn as SNS. This is nothing, just a short form of, we don't have to write again and again Seaborn. We can write SNS. So then another one is from word cloud port word cloud. Port matplotlib dot pyplot as plt. Okay, so Seaborn is a library that uses matplotlib underneath to plot graphs. It will be used to visualize random distribution. And the word cloud is a visual representation of words. Cloud creators are used to highlight popular words and phrases based on frequency and relevance. They provide you with quick and simple visual insights that can lead to more in-depth analysis. And this Matplotlib. Matplotlib is a plotting library for the Python programming language and its numerical mathematical extension NumPy. It provides an object-oriented API for embedding plots into application using general purpose UI. Okay, like Tinker, WXPython, Qt, or GTK. So let's import some NLTK, Natural Language Toolkit. So I will write import NLTK. Okay, from NLTK dot stem import word net lematizer. Then from NLTK dot corpus import top words. Then from NLTK dot tokenize port word tokenize. So NLTK, the Natural Language Toolkit, or more commonly NLTK, is a suite of libraries and programs for symbolic and statistical natural language processing for English written in Python programming language. And this is stop words. Stop words are words that are so common they are basically ignored by typical tokenizers. And this word tokenize is a function in Python that splits a given sentence into words using the analytical library. Okay, so let's import some scikit-learn library. So for that, I will write from sklearn dot model collection import train test splits. Okay, then from sklearn dot feature extraction dot text import FID vectorizer. Then from sklearn dot matrices matrix import confusion metric classification. Okay, so scikit-learn is a free source software machine learning library for Python programming language. It features various classification, regression, and clustering algorithms, including support vector machine learning, logistic regression, and many others like random forest classifier. And this train test split method is used to split our data into train and test set. First, we need to divide our data into features like x and y labels. And this TF-ID vectorizer converts a collection of raw documents into a matrix of TF or IDF features. The fast text on what to vectorizer, what embedding Python implementation. And this confusion matrix. A confusion matrix is a table that is used to define the performance of a classification algorithm. Okay, then we'll import some libraries like from sklearn dot linear model code logistic regression. So then from sklearn dot pm code then from sklearn dot symbol code random forest classifier. Okay, then from sklearn dot naive code Bernoulli base. Okay, so everything is correct. We will see while running. So logistic regression estimate the probability of an event occurring, such as voted or didn't vote, based on a given dataset of the independent variable. Here SVC, logistic regression estimate, sorry, linear support vector machine, SVC is an algorithm that attempts to find a hyperplane to maximize the distance between classified samples. And this random forest classifier creates a set of decision trees from a randomly selected subset of the training set. And this Bernoulli NB. Bernoulli naive Bayes is a part of the naive Bayes family. It is based on Bernoulli distribution and accept only binary values that is 0 or 1. So let's import some TensorFlow. So import TensorFlow dot compat dot v2 and and import TensorFlow datasets as TFDS. So TensorFlow is a free and open source library for machine learning and artificial intelligence across a range of tasks, but has a particular focus on training and inference of deep neural networks. Okay, let's import warnings. Nothing. Warning. The warnings. Import RE and import string, import pickle. So everything is basic. Just let's see the pickle. Pickle is a Python, is primarily used in serializing and deserializing a Python object structure. Okay, let's run it. Let's see how many errors can come. After that, we will load the data set and we will go through data visualization. Okay, word cloud cannot import name word cloud. Okay, C will be capital here. Random forest class. Okay, it's still loading here. Let's see. Okay, so loading is done. So now let's load the data set. So we'll write data equals to pd dot read underscore csv data set name test one. So you can find this dataset on the description box below. Coding equals to Latin equals to polarity okay. ID comma date comma query. Perhaps you forgot comma where. Equals to polarity. Okay, yeah. Seems fine. Let me change this first. Is using RNN. Okay. So here I will write data equals to data dot sample equals to one data. Okay, so let me like brief tell you that what we are going to, okay. Let me brief you like what we will do in this sentiment analysis using RNN. So in this demo, like you will see text processing on Twitter dataset, and after that we will perform different machine learning algorithms on the data such as logistic regression, random forest classifier, SVC, naive Bayes to classify positive and negative tweets. After that, I will also build a RNN recurrent neural network, which is the best fit for such textual sentiment analysis. Okay, since it's a sequential data set, which is requirement for the RNN network. So let's dive into. So now we will see the data visualization, data set details target like the polarity of the tweets, zero, negative. Okay, then the date, like date of the tweet and the polarity and the user that what tweeted, then the text. Okay, so I will write print data set shape data comma shape. Okay, wait, let me first do like this. Yeah, so there are 20, or you can say 2 lakh rows and 6 number of columns. Okay, so it is a huge data. I will, you can find this data set from the description box below. So here, let's see the data. And why I use head is used for like for showing top 10 rows of the data set. If you will use tail instead of head, it will show the last 10 rows of the data set. Okay, here polarity 0, 0 means negative and 4 means positive. Okay, like you can consider as 0 1. This is id, date, then query, then user, then the text. Okay, so here I will do data polarity dot. Okay, these are the 0 4. Okay, uniqueness. 0 means negative and the 4 means positive. Yeah, replacing the value 4 as 1 for the ease of understanding what I said to you, you can consider as 0 1. So data polarity equals to data polarity 4 to 1. And then data. So now you can see 0 1 0 1 0 1 1 0. Okay. So if you will write only head, it will show the top 5 rows only. Okay. So now let's use one Python function describe. So data dot type. So as you can see here, count is 2 lakh and the mean of the particular row is this, and the ID is this, standard deviation, minimum value, the 25%, the 50%, and the 75%, and the maximum. Okay. So let's see the number of positive versus negative tagged sentence. Okay. So here I will write positives equals to data polarity data dot polarity was equals to 1, then negatives data polarity data dot polarity is equals to 0. Print total length of the data is dot format data dot shape now I will print the total length, the negative and the positives. Okay, so number of positive. Okay, dot format of positives. So I will copy this and paste it here, and here I will do the changes for the negatives. Okay, now let's see. So here polarity is not defined. Comma. So as you can see, the total length of the data is 2 lakh and the number of positive sentences is like 1 lakh 46. And number of negatives, okay, spelling is the number of negative text sentences 99,954. Okay, so now we have a brief data. So now let's get a word count per of text. So for this, I will write count and words. Done. Length of words dot split. Okay. And now let's plot a word count distribution for both positive and negative. So I will create a bar plot. So for that, I will write it word count to data and text dot apply word count. Okay, then I will write p positive equals to data, then count data dot polarity is equals to 1. Then so let me copy this only. Here I will write 0 and okay, then plt dot figure and figure size equals to 12,6. Okay. Then plt dot 45, then plt dot x label word count plt dot y label and frequency. And we'll write g equals to plt dot comma n color equals to alpha equals to 0.5 positive. Okay, then let's make a legend also. Location should be right. False. Where data word count priority equals to. Okay, my bad. So as you can see the positive and the negatives. Okay. So these are the like word count distribution for both positive and negative. Okay. So now let's what we can do the get the common words in training data set for the training data set. So for that I will do from collections import counter all words equals to and for and test data text equals to line dot split for word and words if length of word greater than 2 all words dot append word dot lower. Here I can write counter all words dot most common. Then I need 20. So as you can see, these are the most common word used like in every sentence. The and you for have that I am but just like this out over all. So these are the most common words like it used the is used like 64,000 times and like this your is used for 8,000 times something like that. So now we will do some data processing. Okay, now let's do the data processing. So live and SNS dot count plot data polarity. Okay, these are the negatives and these positives. There is a slight change, I guess. That is why it's not looking so much of different. Like there's a slight 46 different, so that is why it's looking almost same. Okay. So now removing the unnecessary columns like query, user, word count, data dot drop date query and word count. X is equals to 1, comma, place equals to true. Okay. Okay, it will be true. So here I will write data. Word count is no, okay, my bad. So here I will write data dot drop ID, comma, x equals to 1. True. Then data dot head the data. See, we have only the two, the polarity and the text. Okay. So now let's see the null values. So data dot data print. Okay. So there is no null values. So now converting pandas object to a string type. For that we have to write text equals to data text type. Yeah. Object as types. Yeah. So now download the stop words NLTK dot download words words equals to set stop words it's in English. Print stop words. This These are some, stop words. So moving forward, let's download analytic dot download the analytic dot download dot net. So the pre-processing steps taken are like lower casting, each text is converted to lowercase. Then remover of URLs will do this. matlab, we will do. Okay. Links starting with HTTP or HTTPS or www are replaced by like commas. Removing usernames, removing short words, removing stop words. Like lemmatization is the process will do of for the converting a word to its base. Okay. So for that, what I will do, I'll just copy the whole code for you. Will explain you one by one what I've done. Okay. So this is a course for the URL pattern for removing all the www, HTTPS and HTTP type of thing and removing them. And I have used pattern for the lower casting, removing all the URLs. Okay. Then removing all the usernames like at the red and removing punctuations and stop words. Okay, like this. So now what we have to do, data E are processed tweets, then data text dot apply lambda x process, then tweets, okay, then print text pre-processing. So it is taking time. And it will be completed. It will return here. The text pre-processing is done. Okay. So as you can see, the text pre-processing is done. So now let's check data dot add done. As you can see the at the rate and this slices are gone. Okay. So now the text is pre-processed. So now what we will do, we will analyze the data. So now we are going to analyze the pre-processed data to get an understanding of it. We will plot word clouds for positive and negative tweets from our data set and see which what occurs the most. Okay. First we will create for the negative words or negative tweets, you can say. So I will add plt dot figure, then figure size 15 comma 15. Okay. Then word cloud equals to word cloud max words equals to 2000. comma width equals to 1600, comma height equals to 800, and rate dot join the data dot polarity, and I will write here polarity, okay, equals to 0, again, then processed tweets. Okay. Then here I have to write plt dot show, may show wc interpolation equals to bilinear. Okay, perhaps you forget the comma here. So 2000, then comma width dot generate. Okay, what I can do? Let me run now. Let's see. Hope this time it will work. Okay, it's still loading. As you can see, this is okay, like today I am and work, don't wish, they need much. These are the most negative tweets. Okay, words from negative tweets, you can say. Right? So let's see the positive tweets. Okay. So the thing will be same. Let me copy, paste it here. So for this, I will do one. It will take little bit of time to come. Still loading. Like as you can see, hate, can't. Okay. Sorry. These are the negative words. Okay, still loading. So let's wait for like few seconds. Now you can see the positive words like love, okay, good, lol, and awesome, something like that. Okay, so these are some positive words. So now let's do the vectorization and splitting the data, like storing into input variable process tweets to X and output variable polarity to Y. Okay, we'll do that. So X equals to data processed tweets values, and Y equals to data clarity dot values. Okay, now I will write here print x dot shape print y dot shape. Okay, cool. So now what we will do, we will convert text to word frequency vectors. Okay, TF to IDF. So this is an acronym that stands for term frequency to inverse document frequency, which are the components of the resulting scores assigned to each word. Okay, so term frequency, this summarizes how often a given word appears within a document. And inverse document frequency, this downscales word that appear a lot across documents. Okay, so now here we will convert a collection of raw documents to a matrix of TF to IDF features. Okay, then I will write vector equals to TF vectorizer and sublinear x equals to vector dot fit transform and print fitted. Okay, print number of feature comma length vector dot get their names. So number of feature words are like 170321. Okay, now we will do like, now let's print the shape. Yeah. So now we will do the split to train and test. So the preprocessed data is divided into two sets of data, training data and the testing data. So data set upon which the model would be trained on contains 80% data. And the test data is the data set upon which model would be tested again contains 20% of data. So for that I will write x train test, comma y train, comma train test by test size equals to 0.20, random state equals to 101. Okay, random state. So what I will do the, print the shape of x train, y train, x test, y test. Like how many columns are there, rows? Not column exactly, the rows are there. Okay. So I will paste there. So see, x train, like this is a total was like 2 lakh. Okay. So 1,60,000 in training, as we discussed earlier, like 80% in training and 20% in testing. Okay. So now let's do the model building. Okay, model evaluating functions. So now let's make a model. Okay, and first I will write and then I will explain you the whole. Okay, so here what I did it, this will tell you the accuracy of the model of training data and the testing data. Okay, then we will predict the values for test data set and the evaluation for the data set. Then we will compute and plot the confusion matrix. Okay, the both the categories negative positives Okay, group name will be true negative and the false positive. Okay, so this is the thing. Let's run it. So now what we will do first for the logistic regression. So here I will write LG equals to logistic regression. Okay, then history equals to LG dot fit X train, comma Y train. Okay, then model evaluate LG. Now let's see. This is for the logistic regression. Okay, as you can see, the accuracy of the training data is 83%, the testing data is 77%. Okay, so this is the confidence matrix, the predictive value, like these are the categories. Now let's see for the linear SVM. For that, I will write SVM equals to SVC and SVM dot fit train, comma Y train, and model evaluate of SVM. Okay, and after that we will do for random forest and the naive Bayes. Okay, then we will start with the RNN. So as you can see, the accuracy of training data is very pretty good, 93%, and registration is 83%, and the testing is less than regression model. Let's see for the random forest. So I will write here RF equals to random forest classifier emitters equals to 20, criterion equals to entropy more than max depth equals to 50. Then RF dot fit X train, comma Y train, and model evaluate okay. Loading. Let's see the accuracy how it will come. After this, we will do for the naive Bayes, and after that, we will move on to the our main model RNN, recurrent neural networks. Still loading. Yes, it will take little bit of time. So as you can see, the confusion matrix. Okay. So training data accuracy is 75% is very less. So now let's see the last model naive Bayes. Okay. So NB equals to Bernoulli NB NB dot fit Spain, comma Y train. Okay, then model evaluate. So naive-Bayes training 8676. So as far linear SCC has the best test training accuracy, you can say, and the best testing accuracy is 76, 70, 76.45, 77. See logistic regression. So now let's move to the our main model RNN. So what is RNN? Recurrent neural network al- are the state of the art algorithm for sequential data and are used by Apple Siri and Google Search Voice. It is the first algorithm that remembers its input due to an internal memory, which makes it perfectly suited for machine learning problems that involve sequential data. And there is one more thing, embedding layer. Embedding layer is one of the available layers in Keras. This is mainly used in natural language processing related applications such as language modeling, but it can also be used with other tasks that involve neural networks. While dealing with NLP problems, we can use pre-trained word embeddings such as GLOW. Alternatively, we can also train our own embeddings using Keras embedding layer. LSTM layer, long short term memory networks, usually called LSTMs. I have made already many videos, you can check it out, were introduced by Skymeter. These have widely been used for speech recognition, language processing, sentiment analysis, and text prediction. If you are going deep into LSTM, we should first understand the need of LSTM, which can be explained by the drawback of practical use of RNN. So let's start with RNN. Okay, so here I will importing some libraries. Okay, so after that I will write import Keras version 2.110. Okay, fine. So now let's print x test comma y train y test equals to train test with weights comma data dot polarity dot values, then test size equals to 0.2. Test size 0.2 means like 80 and 20% thing, 80 to training and the 20% to testing. Okay. Then let's the model evaluation. Okay. So I will. These are ReLU, sigmoid, all the the layers. So now this epoch, it will run till 5,000. Like count will go till 5,000. Okay. See the 5,000 and it will go to 1 to 10. So it will take time. So I will get back to you after this, completing this. Okay. Now as you can see, the box ran successfully. Okay. So what should I do? For I will give some space here. So now we will see the positive and negative outcome. Okay. This is something like testing. Okay. We will test. We will predict. We will give one a sentence and then we will predict it is coming right or wrong. The accuracy is giving a right or wrong. Okay. So here I will write sequence equals to tokenizer dot text to sequences. Then I will write this data science article is worst. Okay, so here I will write test equals to pad sequences, and here I will write sequence comma max length equals to max length. Then I will write here prediction equals to model we will write model, then we'll write model 12 2 dot predict, then test. Okay, if prediction is greater than 0.5 means 50%, then it should print positive. Okay. Else negative. Okay, let me run this. Okay, sequential object has no. Okay, spell mistake. The negative because here is the word worst. It is showing correct. Now check from the RNN model. So model equals to keras dot models dot load models. Here we will load RNN model. RNN underscore model dot sgf file. It is pre-trained model. Okay, pre-trained RNN model. So sequence equals to tokenizer dot text to sequences. Then I will write here this ML course is best. Okay, best equals to pad underscore sequences sequence max length max underscore length. Okay, then prediction equals to model dot predict, then test if prediction is greater than 0.5 and positive. 0.5 means 50%, more than 50%. Else print negative. Attribute load models. Be positive because this ML course is best. So there is no negative word. Okay. So what we will do now, we will do model saving, loading, and prediction. Okay. So for that, I will write import pickle file equals to open vectorizer pickle, then WB. Okay. And here I will write pickle dot dump vector file vector goes. Okay, so like this I have to write for naive-bayes, logistic regression, SVM, and random forest. So what I will do, right here. Okay, let's run this. Okay, so now what we have to do, we have to predict using saved model. Okay, what we will do here, we will load model first and we will predict. Okay, so first I will write the function name load models, and we will load the vectorizer. So file equals to open vectorizer dot pickle rb and vectorizer equals pickle dot load file, the file dot close. Now I am loading the logistic regression model. So for that we have to write open b lg equals to pickle load file, then file dot close, then run riser lg. Okay, run it. Yeah. So now we will predict the sentiment. So for that I will write df predict riser comma text. Okay. So here we will predict the sentiment. So for that, SSS underscore text equals to process underscore sentiments for sentiment in text. Then text data vectorizer dot transform says then sentiment to model dot predict data. So here I will make a list of text with sentiments. So for that I will let data equals to empty array. Then for text prediction and zip text comma sentiment data dot append text comma prediction. Okay, and we will convert the list into pandas data frames. So for that I will add df equals to pd dot data frame comma columns equals to text comma sentiment then df equals to df dot replace comma 1 negative comma positive and df. Okay. So at last I will write here if equals to then here we will loading the model vectorizer comma lg equals to load. Here we text to classify like what should be in the list. So like text equals to here I will like I love machine learning work is so beyond I feel so. So here df equals to predict vectorizer g comma text then print df dot head. See, I love machine learning positive, work is so active positive, John I feel so good negative. Okay, there is and yeah, see that's coming. Okay, so this is how you can do the sentiment analysis using RNN model. Here we have loaded RNN model, so it is showing right. So let's do them as poses right here at boy. Negative. Okay. RNN model is working so right. Today we are going to explore k-nearest neighbors or KNN, which is one of the most popular algorithms in data science. Python is a powerful tool for data science, and KNN is great for classifying data by predicting the category of sample based on its closest neighbor. This algorithm is used in many fields like healthcare, finance, and agriculture, helping us make decisions based on data. The best part, it is really easy to use. You just need to pick a number for k and choose a distance function to compare data points. However, KNN has its downsides. It doesn't work well with the large data set, and it requires proper scaling of the data to get accurate result. In this video, we will show you how KNN work with real data set, the IRIS dataset. We'll walk you through simple Python code and demonstrate how to find the best k value to maximize your model's accuracy. So stay tuned to see KNN in action.
Before we move forward, unlock the future of AI with comprehensive program in collaboration with ENICT Academy, IIT Guwahati. In just few months, you will master cutting-edge skills in generative AI, large language models, and machine learning. From learning tools like ChatGPT and DALL-E to gaining hands-on experience with Python and TensorFlow. This course will equip you to lead AI projects and qualify for top roles like machine learning engineer and data science. Plus, with an IIT certificate on your resume, you will stand out to the best employers in tech. So don't forget to check out the coursing from the description box below and the pinned comment. So without any further ado, let's get started. So welcome to the demo part. So I am here using Google Colab. So you can use any of your favorite IDE like Jupyter Notebook, IntelliJ, Visual Code Studio, anything. Okay. So let me rename this file as KNN classification. Okay, cool. So let me tell you that KNN can be used for the classification, regression, predictive problems. So KNN falls in the supervised learning family of algorithms. Okay, so we will measure the distance between the k neighbors, and the first step will be we'll choose the number of k of neighbors. Then we'll take the k nearest neighbors of the new data point according to your distance metric, and the step 3 will be among these k neighbors, count the number of data points of each category. Okay, step 4, we will assign the new data points to the category where you counted the most neighbors. Okay, so let's start. First, let's import some library. Import numpy as np, and let's import pandas as pd. So everyone knows what is numpy and the pandas. Okay, so NumPy is a library for the Python programming language, adding support for large multi-dimensional arrays. Okay, along with the large collection of high-level mathematical functions. And whereas Pandas is a software library written for the Python programming language for the data manipulation and analysis, all the data frames and data structure it offers for the manipulating numerical tables. Okay, and the time series, you can say. So moving forward, we'll import our data set. So you can download the data set from the description box below. Okay, data set equals to pd.read underscore csv. The data name is iris.csv. Okay, this is how you read your data in Python. Okay, yeah, data set is loaded. So data set dot shape. Okay, yeah, so data set dot shape is used for how many numbers of rows and columns present in your data set. Okay, 150 rows and 6 columns. So let me tell you brief about data set, this iris data set. So iris data set include 3 iris species with 50 samples each, as well as some properties about each flower. So one flower species is linearly separable from the other 2, you can say, but the other 2 are not linearly separable from each other. Okay, and this shape, I told you, we can get a quick idea of how many instances of rows and columns are present in our data set. So let's see our data set dot head. So head is used for you can see top 5 rows of your data set using head, and if you will use tail instead of head, you can see the last 5 rows of your data set. Cool. Okay, so columns are id, sepal length, sepal width, petal length, petal width, and the species. Cool. Then moving forward, let's describe our data sets. So these are the basic function, okay, of Python, you can say. So data set dot describe, what describes do is it will give you count of all the rows, mean value, standard deviation value, minimum value, what is the 25%, okay, of all the values in the particular row, what is the 50%, what is the 75%, what is the maximum is 150, you can say. Okay, and 25% of 150 is 38.25, this, okay, of all the columns. If it is normal character, so it won't give you any data. Okay, cool. Yeah, So moving forward, let's now take a look at the number of instances row belong to each classes. Okay, so we will write data set dot group by species dot size. Okay, species S is capital, that's why it's showing the error. Yeah, so you can see Iris setosa are 50, Iris versicolor are 50, and Virginica is 50. Okay, and the data type is integer. Cool. So as we can see, dataset contains 6 columns like ID, sepal length, sepal width, and petal length, petal width, and species. The actual features are described by columns 1 to 4. The last columns labels of samples. Okay, so firstly we need to split data into two arrays like X features and Y labels. So how we will do this? By writing code like feature underscore columns equals to sepal length, sepal width, petal length, petal width. Just remember you are writing correct name. Okay. Then X equals to dataset feature underscore columns. Okay. Dot values. Then Y equals to dataset species dot values. Cool. Then let me run it. So this is how we can split the data set, okay, into two arrays, X and the Y. Okay, in X there are feature columns, these 4 columns are there, and in Y species column is there. Okay, and what is the species column? This setosa, virginica, and all this. Cool. Then now we will do label encoding. So as you can see, labels are categorical. K-numbers classifier does not accept string labels. So we need to use label encoder to transform them into numbers. Okay. Then iris setosa correspond to 0, iris versicolor correspond to 1, and iris virginica correspond to 2. Okay. 0, 1, 2. Cool. So how can I from sklearn dot pre-processing import label encoder. Okay, so what we'll do, label encoder transform them into numbers. Okay, so I will write L equals to label encoder. Okay, my bad, label encoder. Okay, then Y equals to elifate dot transform Y. Okay, so now I will run it. Yeah, correct. So splitting data set into training set and the test set now. Okay, so now we'll split data set into training set and test set to check later on whether or not a classifier work correctly or not. Okay, so here I will write from sklearn dot not cross. I will write here sklearn dot model selection import train test split. So what is train test split? Train test split is a model validation procedure that reveals how your model performs on your new data. Okay, and what is xtrain, xtest, ytrain, ytest in Python? Okay, let me first write it and then I will let you know. Okay, then I will write here xtrain comma xtest comma ytrain comma ytest. Okay, equals to train test split, then x comma y comma test size 0.2 and the random is this. Okay, some error came. Okay, underscore model selection. Yeah, cool. So what is xtrain, xtest, ytrain, ytest? Okay, so xtrain and ytrain sets are used for training and fitting the model. Okay, so the xtest and the ytest are the set used for testing the model and it's predicting the right outputs label. Okay, so here you can see test size is 0.2, means 80% is for testing, 80% is for training and 20% is for testing for the new data. Cool. Yeah, So now we will see some, let's do some data visualization. Okay, so here I will write import matplotlib dot pyplot as plt, then import cborn as sns, then here I will write %matplotlib inline. So what is matplotlib? Matplotlib is a plotting library for the Python programming language, and it's numerical mathematics extension. Okay, so NumPy, it provides an object API for embedding plots into application using generating purpose GUI toolkits like Kinter and Python Qt or GTK. Okay, whereas Cborn is a library for making statistical graph in Python. It builds on the top of Matplotlib and integrates closely with Pandas data structure. Okay, Cborn helps us to explore and understand the data. Okay, so I will run it. Here I will write from pandas dot plotting import parallel coordinates, then plt dot figure size should be 15 comma 10. Okay, then parallel coordinates. Okay, then dataset dot drop, I don't need id, comma axis is 1. Okay, then comma species, then plt dot title and let parallel coordinates plot. Okay, and you can give some font size equals to 20, then font weight equals to, okay, let's say bold only, bold, then plt dot x label, then features comma font size equals to 15, then plt dot y label, then I'll write here features values comma font size equals to 15. Okay, then plt dot legend, then loc equals to 1 comma I will write here frame on equals to true comma shadow equals to true comma face color equals to white, T should be capital, and comma edge color equals to okay plt dot show. Okay, some error is there, plt dot figure size, okay, spelling mistake. Okay, one more error, plt dot legend, okay, face color, okay, some spelling mistake. So yeah, let me make it view output in full screen. Yeah, so parallel coordinates is a plotting technique for plotting multivariate data. So it allows one to see clusters in the data and to estimate other stat visually. So using parallel coordinate points are represented as the connected line segments, as you can see. Okay, and each vertical line represent one attribute and one set of connected line segments represent one data point. Okay, and points that tend to cluster will appear closer together. Okay, so this color is iris setosa, and this is iris versicolor, and this purple one is iris virginica, as you can see in the legend. Okay, cool. So moving forward, let's create another graph and curves. Okay, so here I will write from pandas dot plotting import scatter. No, it's plotting import Andrew curves. Okay, then plt dot figure. It's AI based, so it's giving me suggestions. Okay, so sometimes suggestions are good, but not always. Yeah, let's carry on. Figure size is 15 comma 10. Then Andrew curves. Then I will add dataset dot drop idx is species and plt Andrew curves plot. Okay, fine. Okay, let me add. We don't need x label and all. Let me add legend. plt dot legend. Then same loc equals to 1. Then proposition size. Then I will write here size is 15. Frame on equals to 2 comma shadow equals to true. So this is truly based upon you if you want to add legend or not, or you can skip. If you want to skip, you can skip. Okay, face color equals to white. Then edge color equals to black. Okay, then plt dot show. Yeah, so no error is there. So let me first view output in full screen. Okay, so Andrew curves, these are the Andrew curves. Okay, you can see the graph in the curve. So Andrew curve allow one to plot multivariate data as a large number of curves, so that are created using the attributes of samples, okay, as coefficient for Fourier series. Okay, so by coloring these curves differently for each class, it is possible to visualize data clustering. So curves belonging to samples of the same class will usually be closer together and they form large structure. Okay, as you can see here. And this is the legend why we are setting the forecolor is should be white, and yeah, and the edge color should be black. Okay, and frame on shadow should be there. You can see the shadow. Okay, like this. If you want to skip, you can skip this part, legend part. Okay, but oh, like it's good to have. It's good practice to have this. Cool. So let's create one small pair plot. Okay, so I will write here plt dot figure. Then I will write sns dot pair plot. Then I will write dataset dot drop. We'll drop again id. We don't need. Axis is 1. Then I will write hue equals to species, size equals to 3. Then markers equals to OSD. Yeah, cool. Then plt dot show. It's running. Yeah. So first let me make it to full screen. Yeah. So here pairwise is useful when you want to visualize the distribution of the variable or the relationship between the multiple variables separately within subsets of your data set. Okay. So here this blue one is Setosa, versicolor and the Virginica. Okay, so these are some graph you can say, or here you can see sepal length. Okay, so green one is Virginica and versicolor are almost having same sepal length. Okay, and here are the different types of graphs. Okay, if you don't want to let's say if you don't know how to read this graph, you can use this graph, or you can use this graph. Either you can use this graph. Okay, that's the power of pairwise plots, you can say. And the sepal width centimeter. Okay, Setosa, no, okay, Virginica and versicolor again having almost same sepal width. Okay, and here as well. Okay, this Setosa is in different form. Okay, yeah. So we'll create one small pair of one small graph, then we'll move forward. Okay, I will write here plt dot. So now we are creating box plot. Figure. Okay, then dataset dot drop. Then again id comma axis should be 1 dot box plot. Okay, then figure size I chose this. Yeah, let's run it. Yeah, again see, this is the box plot. Petal length same, petal width, sepal length, sepal width. Okay, according to width it is showing, like from this to this width we have the versicolor, and from this to this width, this length, sorry, sepal length, we have that virginica lies here, iris virginica, and from here to here iris setosa lies. Okay, the sepal length. Cool. And like you can use 3D models, you can use different types of charts. Okay, I did 4, and 4 are enough to read the data set. Okay, so now we will do some KNN classification. Okay, we will make prediction and we will see the accuracy of our data set. Okay, so now what I will do, I will write here from sklearn dot neighbors import k neighbors. Okay, write from sklearn dot neighbors import k neighbor classifier. Okay, then I will write here from sklearn dot matrix import confusion matrix comma accuracy score. Okay, then I will write from sklearn dot model selection import cross value score. Okay, so here what I did, we are fitting the classifier to the training set and the loading the libraries basically. Okay, then we'll initiate a learning model k equals to 3. Okay, so here I will write classifier, let me give one space, classifier equals to neighbors classifier and neighbors equals to 3. Okay, then fitting the model, I will write here classifier dot fit xtrain comma ytrain. Okay, then now we will predicting the test set results. Okay, so y prediction equals to classifier dot predict x test. Cool. Okay, spelling mistake. Okay, yeah, I guess fine now. So now let's evaluate the prediction. So here I will build the confusion matrix. Okay, so here I will write cm confusion matrix equals to confusion underscore matrix y test comma y prediction. Okay, then here I will write cm. Okay, so what is confusion matrix basically? So confusion matrix is a table that shows how well a model performs by comparing its prediction to the actual values. Okay, so what it shows, a confusion matrix displays the number of correct and incorrect prediction of each class in models. Cool. Either it can give you true positive, true negative, false positive, false negative. Either it can give you 0 or 1. Okay, so yeah, moving forward, let's calculate the model accuracy. This is the main part. If the model accuracy is low, it means your analysis of classification is not good. Okay, so accuracy, it should be more than 80 at least. Accuracy equals to accuracy underscore score y test comma y prediction into 100, otherwise it will give me in points. So I will write print model Canon model accuracy is, I will write plus str, I will round it. Okay, accuracy I will add the percent. So why I wrote this accuracy to round? So I don't want after points, I need only two numbers. Okay, I don't want like 6, 7, 8, 9, 10, 11, 12 like this. Okay, I need only like 80.20 like this. Cool. Let's run it. See, our KNN model accuracy is 96.67. That's why I wrote 2 here, and the percent should be there. So 96, which is very, very, very good. Okay, so this is how you can find the accuracy. So now let's find the optimal number of neighbors in K. Okay, basically finding the best K. So we will use using cross validation parameter. Okay, tuning. So first I will create the list of K for Canon. Okay, so here I will write K underscore list equals to list range 1 comma 50 comma 2. Here I will create the list of CV score. Okay, so here I will write CV scores. Okay, I have to give the brackets. Yeah. So we'll here perform the tenfold cross validation. Okay, I will explain you what is cross validation. Don't worry. First, let me write for K and K list KNN equals to K neighbor classifier, and here I will write n neighbors equals to K. Then scores equals to cross value score KNN, then X train comma Y train. Okay, comma I will write here cross validation equals to 10 comma scoring equals to, I will write here accuracy. Okay, and then here CV underscore scores dot append to scores dot mean. Okay, so now yeah, let me run it. Okay, comma some error came. Okay, the error is the scoring parameter. Yeah, why? Because here accuracy you can see, and I did the spelling mistake. Okay, so now what is cross validation? Of course, cross validation determine the accuracy of your machine learning model by partitioning the data into two different groups. Okay, called training set and testing set. You can see test and the testing set. Okay, X and Y. So the data is randomly separated into a certain number of groups or subsets called folds. Okay, you can see the 10 folds we have wrote. Each fold contains about the same amount of. Okay, and there is one more thing, validation. So validation is a technique for assessing the accuracy of the model on dataset. Okay, and this cross validation we did on new dataset. Cool. So now let's find the best K. Okay, so here I will write best K equals to K list. Okay, before that I will write one thing. I will write here MSE was changing to misclassification error. Okay, so equals to 1 as X for X in CV scores. Okay, list I will write MSE dot index minimum MSE. I will use this bracket, square bracket. Okay, so then I will write print the best optimal number of neighbors is person T, person best underscore K. Okay, let's run it. See, the best optimal number of neighbors, okay, neighbors is 9. Okay, so in the K nearest neighbor KNN algorithms, okay, so K represent the number of neighbors that are considered when classifying a query point. Okay, see, if we'll classify this particular point, you will get the 6. Okay, 1 2 3 4 5 6. Okay, and let me show you. If you will classify this portion only, so you will get 1 2 3 4 5 6 points like this. Okay, so the best optimal number of neighbor is 9.
My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get certified, get ahead. Although deep learning has been around for a while, it is just in its infant stages of development as far as exploding on the market. I mean, it is. Right now, they're building robots with it. Deep learning is used to train robots to perform human tasks. Music composition. Deep neural nets can be used to produce music by making computers learn the patterns involved in composing music. Image colorization. Neural network recognizes objects and uses information from the images to color them. Machine translation. Given a word, phrase, or a sentence in one language, neural networks automatically translate them into another language. Google Translate is one such popular machine translator you may have come across. And you'll notice in here we didn't show any examples of straight numbers, like projective cells in a business, tracking your favorite stock. You can certainly do those with machine languages, but this is the next level. Save that for your regression models, your linear regression, where you're actually processing and crunching just straight numbers. With machine learning and deep learning, we're going to a whole new level as far as what we can figure out on the computer. What's in it for you? We're going to cover what is deep learning. We're going to take a look at the biological versus artificial intelligence. What is neural network? Activation function in your neural network, and the cost function, and how do neural networks work? How do neural networks learn? So there's you'll see a switch right there. We just went from how are they working in the math in the background to exactly how are they learning. We'll be implementing the neural network. We'll do a gradient descent, deep learning platforms, and we'll give an introduction to TensorFlow and implementation in TensorFlow. That's Google's platform that they open sourced recently, and it's probably one of the most cutting edges in deep learning. And even it is still in the infant stage, which is one of the reasons they released it to open source. What is deep learning? Deep learning is a subfield of machine learning that deals with algorithms inspired by the structure and function of the brain. And you can see we have a nice picture here. We have artificial intelligence, which is kind of the big bubble that encompasses all these different things we're talking about. This is the ability of machine to imitate intelligent human behavior. And in there we have machine learning, application of AI that allows a system to automatically learn and improve from experience. And if you looked at any of our other videos, you'll know that machine learning covers a lot. So deep learning is a subcategory of that, but don't forget machine learning has all kinds of other tools that people use to do very basic descriptive and predictive and postscriptive analytics. And then you have deep learning, application of machine learning that uses complex algorithms and deep neural nets to train a model. Let's take a look at the biological neuron versus the artificial neuron. Now remember, in the human brain, and this is true for most animals, there are a lot of different neurons going on. So this is a very basic one. I mean, there's hundreds of different cells involved. So when we talk about neural networks, and this is why I say it's in a very infant stage, they're really basing it on just the most basic thing that we're able to figure out going on in the neural networks. And you can see right here we have dendrites fetch information from an adjacent neurons and pass them on as inputs. So you have your data coming in and your data going out. Any computer model should be looking at that. What's coming in, what's going out. The data is fed as an input to the neuron. So when we look at the artificial neuron, you can see we have our inputs. They come in, each one is specially weighted into the neuron, and then the neuron has an output. The cell nucleus processes the information received from the dendrites, and the neuron processes the information provided as inputs. Axons are the cables over which the information is transmitted, and the information is transferred over weighted channels. So you can look at that. I mentioned weights weights briefly, but you alter the data coming in. So those weights are what causes different information coming in to be weighted differently and processed differently. And the synapses receive the information from the axons and transmit it to the adjacent neurons. That's in your biological model. And then when we look at the artificial neuron, the output is a final value predicted by the artificial neuron. So as we dig deeper into looking at the theory behind the neural network, and we kind of flip back and forth between these because there's two huge aspects of it. One is from the outside, what are you seeing, and what's going on from the inside, so you can find to do what you need to do and give the best results you can. And we start off with what do we feed? We feed an unlabeled image to a machine which identifies it without any human intervention. And so you can see here we have a circle that comes in at 784 pixels, and it comes in by 28 by 28. And you can see how it colors in the circle on there. And we put a triangle in. The triangle in also comes in as 28 by 28, and it has 784 pixels. So you'll see between these two, both of them are 784 pixels. This machine is intelligent enough to differentiate between the various shapes. So that's what we want to use our neural network to do, is to say, hey, this is a circle, this is a triangle. And that's more of a categorical. You can also do a regression model where you're actually putting out a float value or a numerical value. We'll be looking at the true-false or the categorical model mostly, because that's where you usually start at. There is no real difference when you, as far as the way the internal functioning goes, when you start flipping between them, other than, well, we'll talk about that in just a minute. So you can actually go between the two quite easily. And the neural network provides this capability. So we're going to use this capability to look between those two. One of the things I want you to note in here is that we're looking at 784 pixels. We're looking at 784 inputs. That's very different than stock with a high-low or last year's cells based on date, where we're looking at just a couple of numbers, and they're very clear. They're numbers. They're very clear what they are, which is something you'd put into a machine learning linear regression model. This is a step up from that in that we're looking at complex patterns, and how do you figure those complex patterns out? So a neural network is a system modeled on the human brain. And we looked at that, comparing the two. Let's go ahead and look deeper into the neural network itself. We have our inputs coming in. So the inputs are fed to a neuron that processes the data and gives us an output. Input and output. This is the most basic structure of a neural network known as a perceptron. So if you see the term perceptron, that's what we're talking about. We're talking about this single node that has inputs and an output. However, neural networks are usually much more complex. Let's start with visualizing a neural network as a black box. And I always love that symbol. It's a black box. It's kind of magical. We have our inputs coming in, and we want certain outputs. The box takes inputs, processes them, and gives an output. Let's have a look at what happens within this box. And you can see me there in my secret agent getup. I got my hidden hood and everything. I guess I'm part of the Black Skull or something like that group. So let's take a look at what happens within this magic box. And remember, we're skipping back and forth between the theory of what's going on in the box, which you have to know how to fine-tune and how to build, versus looking at it from the outside. We're programming this box, and we have an input and an output to the box as a whole. Within the box exists a network that is a core of deep learning. And you can see here we're showing one layer, and we have our grid coming in. The network consists of layers of neurons. Each neuron is associated with a number called the bias. And you can think of the bias, if you overly simplify this, and we're doing a linear regression model, this is your y-intercept in your Euclidean geometry. You have to have something that offsets it, and so you always have a bias in these cells. Neurons of each layer transmit information to neurons of the next layer over channels. And so you can see each of our layers going through from left to right. These channels are associated with numbers called weights. These weights, along with the biases, determine the information that is passed over from the neuron to neuron. So just like the bias is your y-intercept in Euclidean geometry, you could look at the one weight. Remember, this is very complicated, so we're not looking at just one weight. You could look at the weight as your slope of the line. Or if you're doing x equals my plus c, it would be the m value. Neurons of each layer transmit information to neurons of the next layer. And you can see here as they light up going across into the final layer, and then to the output. And in this case, the output is going to be either a square in this one, or it might light up the other one, which is a circle. The output layer emits a predicted output. So in this case, we're looking at a classification, true, false. Is it a circle? Is it a triangle? Is it a square? Let's now go deeper what happens within the neuron. So we're going to dig deeper and start getting a little bit closer to some of the math. Don't worry, you don't have to be a calculus expert or know your differential equations. Even though this is one giant differential equation, you don't need to understand those to understand what's going on. Within each neuron, the following operations are performed. The product of each input and the weight of the channel it's passed over is found. This is simply addition. We're going to sum up the weight times the output from the previous channel, and plus the bias. Sum of the weighted products is computed. This is called the weighted sum. Bias, unique to the neuron, is added to the weighted sum. The final sum is then subjected to the particular function. And we'll discuss that particular function. That part is really important because those functions have a huge impact on how well your model performs under different conditions. The final sum is then subjected to a particular function. This is the activation function. So if you ever hear the term activation function, that's what we're talking about. What activates this cell and what doesn't. As we dig deeper into activation function, an activation function takes the weighted sum of the input as its input, adds a bias, and provides an output. And a lot of times you'll actually see one formula for the sum of the weighted sum and the bias. You'll just see that as a single line of everything added together. In here we've broken it apart because it makes it clear that this bias is not computed the same as the weighted sums. Here are the most popular types of activation function. And I always find these interesting because at one point I was sitting at a table with a gentleman who was finishing his PhD. He was in his last year, and he said he went through all this stuff and he ended up just trying the 4 different activation functions on this particular problem he was working on. So knowing the math behind it doesn't necessarily mean you're going to know it right away. So even somebody who might have a PhD and be doing the calculations on this comes back out of it and ends up just trying the different activation functions to see what's going to make a difference. And a lot of times that's a final step. That's the kind of thing where you built your whole model, you've come back and you're like, wait a minute, can I do a better deal with the sigmoid function or the threshold or the rectifier? Knowing what they're doing is important so you can explain it to somebody else. And again, you probably do this on a small set of data. If you're working with big data, you don't want to take down the full server farm just to test out your 3 different series. You take a small portion of that data, test it, and then you put it through to the big data. So let's take a look at this. We have the sigmoid function, and it's used for models where we have to predict the probability as an output. It exists between 0 and 1. And you'll see that's true of all of our activation functions we're working with. Either the cell's on or off. It's true or false. And there might be a little variation in there, which as an output could be used to compute uncertainty in your solution. So if you're getting a 0.7 with this activation function, it might be, well, I'm not sure if that's really a square, or I'm not sure that's really a triangle. And that might be a flag for it to be looked at by a human observer, at least in today's models where we're at right now. And you can see here where we have the formula is simply equals 1 over 1 plus e to the minus x, where x is your value coming in, and it's going to give you a result that looks very similar to the graph on there, which is somewhere between 0 and 1, and right in the middle you can see that there's a huge you can go through all the different values and uncertainties involved. So the sigmoid function is probably the default on most of them. The next one is the threshold function. It is a threshold-based activation function. If x value is greater than a certain value, the function is activated and fired, else not. Pretty straightforward. Yes, no, true, false. I don't want to test for improbabilities. I just want a straight answer. I don't want to know if there's a partial value on there. It either is true or it's false. And the rectifier function, it is the most widely used activation function. I would debate that. Rectifier is a pretty common one, although I see the sigmoid function used to be the basic one, but it's up there. The rectifier function is very commonly used. It gives the output of x if x is positive and 0 otherwise. And you can see here, again, just like it's either kind of get a value going up there. So max of x of 0. So it's like the threshold function. Yes, no, true, false. It's either 0 or it's some kind of progressive value. And then we have the rectifier function. I would argue with this because the sigmoid function used to be the most common one, but with the rectifier function, it now says it is the most commonly used or widely used activation function and gives an output of x if x is positive and 0 otherwise. This is kind of nice because it now says absolutely not, or it gives you a value of probability. Now when I say a value of probability, be very careful there. I'm not saying that it's going to tell you this is 75% chance of being a circle. I'm going to tell you that it says, hey, if this says 0.1, it probably needs to be looked at, or 0.2. 0.2 or 0.3. It's going to depend on your data as to what that value means. In general, that just means it's flagging it that if it's not a 1, then chances are it needs to be looked at by a person and reevaluated. And there's a hyperbolic tangent function. This function is similar to sigmoid function, is bound to a range of -1 to 1. So you can see there's our 1 minus e to the minus 2x and 1 plus over 1 plus e to the minus 2x. Again, it's very similar to the sigmoid function. The bonus of the hyperbolic function is you have that variable coming through the middle. So again, you can look at it and you have a little bit more weight as far as you can process that down the line. That's a little bit more advanced than what we're looking at right now, and a lot of times it's not even necessary in a lot of our different uses for these activation functions. Now, we looked at activation functions, and I kind of said those are a little bit like a black box, because even if you know all the math, a lot of times you end up just playing with them to find out what works, and it also depends on what model you're working with, whether you need a flat yes, no, true, false, or you need to have something in the middle that says, hey, this isn't quite a 1, you might need to process this with the human intervention. And you can look at that. One example would be self-driving cars. You don't want a car to be yes, no, I'm going to go through the light. You want it to be like, okay, if it's almost yes, maybe we stop and have human intervention so we don't get an accident. Cost function is something you can really see and measure and is very important. The cost value is the difference between the neural net's predicted output and the actual output from a set of labeled training data. So we have our group of data that's a square, circle, and since we're looking at geometrical shapes, we've had somebody already labeled that data. They've already said this is a triangle, this is a square. And so if this is coming up and it's giving us and it's saying a square is a triangle and it's saying a triangle is a circle, the output is wrong. And so that output can then be measured versus the actual output, and that's the cost. You might also hear this as error, because that's the error value being returned. How far off is it? And what we're looking for is the least cost, or the least error value. And it's obtained by making adjustments to the weights and biases iteratively throughout the training process. And this is called back propagation. And we're going to look in that a little deeper as we look into an example. It's really hard to see when you're just looking at arrows without actual numbers and where that flow is coming from. But you can look at this as here's our inputs. They put out a prediction. The prediction comes out and says, hey, we've already labeled this data because we're in training mode and the training data is off. This is the cost. Can we send that error or that cost back and adjust those weights? And we do it in very small increments across large amounts of data so that those weights minimize that cost or that error. But what happens within these neurons? So let's look at a little example of this. Kind of helps if you have some kind of visual. Let's build a neural network that predict bike prices based on a few of its features. And we'll see here we have our CC, our mileage, and our ABS, and these are our 3 input layers. And then we have the bike price and the output layer. Now, it doesn't do us very good to just pump it in from the beginning and pump it out. And to be honest, I would use a machine learning linear regression model on this, since these are just straight numbers. But because we want a simple example, we're going to put this through and show you as a neural network what that looks like. And we got to put a hidden layer in there. The hidden layer helps in improving the output accuracy. And you could look at this as a bunch of ORs. So it might say, hey, when we compare these 3 values on the first hidden layer neuron, we're looking at one set of features, and then we might weight them in the second one. So these are a bunch of different ORs, kind of how the math comes out and behind the scenes. And then they go out, of course, to the bike price or the output layer. And each of the connections have a weight assigned with it. And you'll see here we have mileage CC with the weight 1 and weight 2 going into our first neuron. And you'd also have your ABS going in there. And so x1 times weight 1 plus x2 times weight 2 plus the bias of 1. And step 2 is our activation. The activation function coming in there. When does this fire? And the neuron takes a subset of the inputs and processes it. And then we go through and we do that with the second hidden layer neuron and the third one and so on. So you process each layer in order going forward. Now, when I told you this is in its infant stage, they now have neurons that fire into the same layer or back a layer so that you now have a time series. And there's all kinds of wild things that they're experimenting with on these layers. This basic setup has been around since the mid-90s. It's only now because of our technology that it's open to almost everybody to play with it. And that's why I say this is in an infant stage in development. Is this basic math is here, but what we can do with it is amazing, and what they're actually doing with all these different things is amazing. amazing. And so we're just at the beginning of how to use all these different tools in our deep learning and our neural networks. And so once we have our hidden layer computed, the information reaching the neurons in the hidden layer is subjected to the respective activation function. And so each one of these fires an activation output, and then those are each weighted to the final output layer. So the processed information is now sent to the output layer, once again, over weighted channels. And you could look at this as each one of these is, I always look at this as like a group of people. They're all looking at the bulletin board, and the first person says, this is what I project sells for the company, and the second person, and the third, and so on. And then their perspectives are weighted based on their expertise. So your accountant might have a very high weight, where the maybe your janitor has a very low weight because their expertise is not in accounting. And then that goes into the output layer. And once in the output layer, it goes, the output, which is the predicted value, is compared against the original value. So now we have our output layer, and since we have like already a list of bikes with the different setups and what their value is, we can now generate an error from this. The cost function determines the error in prediction and reports it back to the neural network. So this is the cost. This is how far off it is. This is your error coming back. And as you can see, this is back propagation going on. So now our error is going in reverse because we know we're not completely correct on this particular channel. The weights are adjusted in order to reduce the error. So each time we go back, we are changing those weights to reduce that error, and we change them in small increments. You don't want to fit one input. Remember, you might have a data pool with a terabyte of data. You don't want to solve for the first set of data that comes in and that be the main solution, because everything else will be off. This is going to confuse you. That's also called a bias. So we have the bias in the cell where we're adding a value, the kind of like the y-intercept, and we have a bias of the whole neural network, which means it is weighted towards one set of answers. So we want to make small changes in these weights so we don't create a bias. And the weights are adjusted in order to reduce the error, or the cost. The network is now trained using the new weights. Once again, the cost is determined and backpropagation is continued until the cost cannot be reduced any further. So let's go ahead and plug in values and see how our neural network works. So here we come in here, and initially our channels are assigned with random weights. This is important because if you assign them all with the same weight, you might be able to reproduce it, but it turns out that if I put all my weights as 1 or all my weights as 0, it takes longer to train. Where if you have random weights, they already have like a little bit of adjustment and ORs built in, and that will give us a better answer and train faster. Our first neuron takes a value of mileage and CC as inputs. So here comes our computation, whatever those inputs are, and we do that again with the second neuron with those values coming in. You can see here we have weight 3 and so on, and then our third neuron coming down, and of course our fourth neuron. So we're adding all these different values coming in here in our hidden layer. The processed value from each neuron is sent to the output layer over weighted channels. So again, here's our weights coming in, and we have N1, N2, N3, and N4. Once again, the values are subjected to the activation function, and a single value is emitted as the output. On comparing the predicted value to the actual value, we clearly see that our network requires training. So here we have it that our bike price we put out, we thought it was worth $2,000 on our random weights, and the bike actually was $4,000 on there. I'm guessing that's not US dollars, because that'd be a very expensive bike, but maybe it is. There's some $2,000, $4,000 bikes out there. The cost function is calculated and backpropagation takes place. And this is pretty simple. You can look at that as our, we're subtracting one value from the other, we square it, and then we take half of that. And that is propagated back up, and each layer generates its own errors. Let's go back one, because you have your predicted y and your actual y. That goes back to the first layer. And then based on the value of the cost function, certain weights are changed. So when we look at the next layer, that error is not the original 4,000 minus 2,000 squared divided by 2. This error is based on the error of each cell generated. How far off is that cell as far as its weights? We're not going to show you. It's actually a very complicated differential equation, and you can probably write it out if you wanted to. You just write out each formula. That goes into the next level, and you add them all together, and you can write it out all the way through. Computers make it so you don't have to. And our neural network is considered trained when the value for the cost function is minimum. So when we get our error way down as low as we can, that's when our neural network is trained. And just recently they've come up with all kinds of different means for measuring that particular value. A little bit beyond the scope of today's neural network, but you can actually see it. How far do you do this until the neural network doesn't need to be trained anymore, and you can overtrain a neural network. Now the tools that we're looking at automatically let you know when to stop, which is really nice. And that is just, like I said, we're at the beginning stages in neural networks, and it's just really cool what they can do now, and how much of it's automated, and how much of it is experimental right now. Let's take a look at gradient descent. But what approach do we take to minimize the cost function? So here we have a nice error thing coming in. This is our cost or our error. Let's start with plotting the cost function against the predicted value. And so you can see they fed in multiple y's, and these are the errors coming in and the cost of each of these inputs and changes going on. Note, we start at a random point on the curve. So usually you put in, you pick up your data and you randomly pick where to start in your data. A lot of times you just run it from the beginning because you're going through so much data, it's not that big of a deal, but you start with one point going in. So your forward propagation goes through, you're going to go ahead and find your cost or your error. It points that on the curve, and you can see how we're plotting it right here. Since the gradient at this point is positive, we may move right. So we're going to move a little bit to the right on here. And this time the gradient is negative, we move a little bit to the left. Eventually we try out the point where the gradient is 0. This is the least value of cost function. You have to be a little careful with this because this particular, they make it look nice and simple in this graph. Sometimes these curves look like stair steps, and so there is global minimums and then there is local. There might be a local point where the gradient is 0, but it's not the global one. So it might be way off to the left where it just happens to step down a little bit and you think you're in the right gradient. And with that we have all the right weights and we can say our network is trained. So here we have just some major, these are some of the big names out there right now in development for deep learning platforms. TensorFlow, which we'll actually do an example in a minute. Deep Learning for J, which is in the Java platform. So if you're a Java programmer. By the way, as TensorFlow is accessed, most people are using Python to access it, but it is a system that's kind of separate from a lot of the programming languages, which makes it a lot more flexible as far as use. Deep Learning for J is Java based. And then Keras is just exploding right now. And this is interesting. Keras is working with TensorFlow. It actually can sit on top of TensorFlow and it can also do its own thing. So if you're studying deep learning, you're getting into it, you want to know the basics of TensorFlow, but you also are going to want to know the upper level of Keras sitting on top of TensorFlow. We're just looking at TensorFlow today though in our example. And there's also Torch on there. There's a bunch more that we didn't list on here. Even sklearn or the side package in Python has a neural network you can program, a very basic one. And it is the same basic one that you could do in TensorFlow if you stripped everything out of it, and then TensorFlow has a lot of tools they've added in, and so has Keras. But we're going to be looking specifically at TensorFlow in our example. And TensorFlow is an open source tool used to define and run computations on what they call tensors. Very common language now. So more and more we see the term tensor as being a standard in the deep learning language. And this was originally developed by Google. So let's take a little bit big in there. What are tensors? Tensors are just another name for arrays. So a tensor of dimension 5. You can see here we have A, B, K, M, Q, whatever. So it's an array coming in. And the tensor of dimension 5, 4, more like a picture. Very common to see that in a picture. You can also see a tensor even more detailed in a picture as we go to the next one, tensor of dimension 3, 3, 3. This is 3D space. You might have a picture that also has colors. That might be the third dimension. You might have 4 dimensions because you have both your grid and your different color channels and your z-plot. You can see where you can now process a very high level set of data coming in, whether as an image or features. They could be features that have nothing to do with images. So there's a lot of stuff you can do now with the tensors coming in. Thus is where the term TensorFlow comes from. So we have right now that TensorFlow is the most popular library in deep learning. And I did mention Keras now works with TensorFlow. So there's a lot of stuff you can do between the two. It's an open source software library developed by Google. So they hit a roadblock and they realized, hey, this is an infant stage technology. You know, we thought it was going to be the next greatest thing and we were going to have a hold on it, but it's really infant as far as how it's applied and what we can do with it. Let's open source it so everybody can work on it. Let's take it to the next level. And that's really what open source does to a lot of these packages when they release them. And you can run on either a CPU or a GPU. So when we look at the details, if you have your graphic processing units, what's nice about those is they run a lot faster. The downside is you have to play with them a little bit to get them up and running, and it's a hardware upgrade. When we run it, I'll be running it in the CPU mode. I have played with it in my GPU on my personal computer. You know, it does increase the processing, but I did run into some version problems with my Python and stuff like that, and when I did finally work it out, I went back to the CPU because it didn't increase my speed enough for what I was working on. But in a larger group, you might be able to put that on. If you're working with a larger stack of computers, you might want to run it in the GPU. You can create a data flow graphs that have nodes and edges. So there's our edges coming in. We didn't talk about edges, but that's a very up and coming way of looking at your analytical data is how do different nodes connect? What do those edges look like in between them? And it's used for machine learning applications such as neural networks. It is mostly a neural network, but they have all kinds of tools which sit on top of our basic neural network. They have new stuff evolving into the TensorFlow library. So it's very much just exploding. Great time to jump into TensorFlow because there's all kinds of cool things they're doing with it and all kinds of cool applications you can now use TensorFlow for. So let's take a look at implementation in TensorFlow. And we're going to build a neural network to identify handwritten digits using the MNIST database, or the MNIST database. And that stands for Modified National Institute of Standards and Technology Database. It is a collection of 70,000 handwritten digits, and the digit labels identify each of the digits from 0 to 9. This is a cool example because it's simple enough that you could actually run this through some basic machine learning categorizing algorithms and train them, and you'll get about the same answer because again it's simple grid. The digits on the grid don't have a huge amount of variation like you would say an automated driving car looking at the environment. So you could still do this with a lot of your different linear models and stuff like that. You could solve this and you'll get about the same answer. When I ran a comparison between TensorFlow and between some basic regression models or category models in machine learning, they came up pretty even as far as their output. So this is kind of where we start to see the complexity of something coming in this case a tensor, or a grid of information, where the deep learning model does as good as the regular models. And when you get past this kind of complexity and features, suddenly the neural networks come up with better answers, better solutions, and a better build. And that's why there's such a move into neural networks, is we live in a complicated world, and it's just really cool what we can do with this. So the handwritten digits from the NIST database, they come in, the data set is used to train the machine, a new image of a digit is fed, and the digit is identified. And if you've looked at any of our other machine learning tools where we're doing training, where we train our model to fit and then you test it out, this will look pretty familiar. And there is some tools out there for, say, untrained categorizing, where it's just looking for features that fit together. So there are tools that don't need that training. But this is where, when we talk about neural networks, we do need to train them, and this is what we're looking at. So for this, I'm going to use the Anaconda Navigator just because it's a very nice visual tool. You might be in PyCharm or one of your other IDEs for editing Python, because we are looking at Python TensorFlow. And under Anaconda, we have the notebook, which is something we use pretty regularly, and they have the Jupyter Lab. The Jupyter Lab is the Jupyter Notebook, but with tabs and a few new features. So we'll be using the Jupyter Lab today. And under the environment, you'll want to go ahead and if you haven't yet, you'll see that I have a number of different setups in here. Right now I have the Python version 3.6 and the TensorFlow. In this case I have TensorFlow 1.12. If we scroll down you can see that. Here we go, TensorFlow, and it's version 1.12. And in here, if you haven't yet, you'll need to install those. Go in and just open our terminal. And if you've never used the Anaconda, or if you're in your other thing, you might have something simple like pip. Conda is what I use for my install, and you can simply do conda install TensorFlow. And that should bring in the most current version. Now, when I installed this a few months ago, Python version, I'm not going to run this because I already have it installed on here, Python version 3.7, the newest one out, still had a couple glitches with the TensorFlow. I believe they've fixed it as of writing of this, but I'm going to stick with 3.6 just so I don't get any surprises on there. So this is Python version 3.6 with TensorFlow 1.12 on here. And if you haven't installed it yet, you also want to install NumPy for this example. That's Numbers Python, or NUMPY. You can just simply run an install on there. Keep in mind, if you're in Anaconda and you've created one of these environments specific to this, keep with Conda. If you're going to use Conda. If you're going to use pip, keep with pip. Don't install one package with pip and one under Conda, because that's how they track those version numbers and how they fit together, and you can end up with a problem. Pip doesn't see Conda and vice versa. So just keep that in mind when you're running your installs. We'll go ahead and open up Jupyter Lab, and we're going to launch that. So here's my Jupyter Lab. One of the really cool features of Jupyter Lab is you have tabs now, so you can open up multiple notebooks. And this is nice because I have my notes I'm working on and then our actual window we're looking in. And we'll go ahead and zoom in a little bit here. There we go. So you have a nice, hopefully easy to see fonts. And then we'll go ahead and do a simple, or get our imports out of the way. And so we're going to import our TensorFlow as TF. That's pretty much a standard for TensorFlow. NumPy, our Numbers Python, as PY. And we'll import our matplot library as PLT. Again, these are very common. So if you see TF or PY or PLT, this is a standard that most people use. Do you have to? No. You could just do import NumPy instead of doing as PY. And then from TensorFlow.examples.tutorials, this is always nice because they actually include data set we're going to play with. So we're going to import input data. So those are data coming in. That's all we're doing is telling it this is where it's coming from. And if we're going to tell where it's coming from, we need to go ahead and create a variable with that information in it. And we'll just call this MNIST or minced. You know, I don't really know how they pronounce that. I should probably look that up. It's a very common data set to use. And there's our input data, and we're going to read data sets. And this is, if you look at this, we imported input data from our TensorFlow. And so this is a TensorFlow read statement for their tutorials. So this isn't like some special Python setup. This is just their setup. It makes it easy to pull it in. So once we get into their data sets, we need to go ahead and tell it what kind of data set. And again, this is what we brought in, but it's going to be the NINST data. And this part is very important. One hot equals true. This means that instead of importing a value from 0 to 9, we evaluate the data set, it's going to bring it in as one hot. Whenever you see one hot encoder, we're flattening that out, and we have true false for 0, true false for 1, true false for 2. So our output, if you remember from our output from the slide we did earlier, in this case I grabbed the one for bike price. Doesn't really matter which one we use. This has one output, so we have our bike price. On this, we're going to have, instead of one output, we're going to have 10 outputs representing each of the digits in there. And this code really isn't going to show us anything. It's good to see what we're actually looking at. So let's go ahead and do a figure. AX equals, go into our plot library, subplots, 10, 10. And that is, if you remember, we talked about tensor being data coming in. This is a 10 by 10 grid, or 100 pixels on there. And if we're going to display it, let's go do K0 for I in range 10. Just a simple loop through on the data. Let's do, what is it, for J in range 10. So I actually misquoted that. 10 by 10 is not the actual size of the pixels. The actual pixels are going to be, when we look at the shapes, and we'll get into that in just a second here. We'll take a quick look at shape on there. Turns out they're, they are, I believe, 28 by 28. So let's take a look at that. And we're just going to plot these. What are we looking at? What are we working with? As a data scientist, you should always be looking back at your data and seeing what it looks like and get that human perspective, because you just never know. You know, the computer may put something out that makes no sense, and at that point you want to go back and reevaluate what you did. So we're going to go ahead and plot. We're going to plot 10 of the digits by 10 of the digits, and here's our AX. We'll create the IJ on our subplots, and we're going to do an image show. We're going to look at the training image for images of K. And then we want to reshape this. We're going to reshape this. And we're going to reshape this 28 by 28. That's how I knew I had it wrong, is because I looked down my notes and it's like, oh no, that says 28, it's not 10 by 10. And I should know that already because I've done enough messing with this data set that I should have remembered. But it's 28 by 28, and the aspect we're going to do is auto. And this is all, if you look at this, here's our variable NIST. The NIST is coming from data set. So this is all part of the TF TensorFlow learning or examples tutorial in there. And then we'll go ahead and do K plus equals 1. So we just keep paging through our different images. And let's see what that looks like. Let's go ahead and do a plot show. And we'll go ahead and run this so we can take a look and see what we have here. And so we have a nice plot here, and you can just see that we have some random numbers showing up in each one of these little subplots. If you're wanting a copy of this code, put a note down in the YouTube video and let us know, or come visit us at www.simplilearn.com and we'll send you out a copy of what we're working on. You can get a copy of that for your own setup. So now we've taken a look, and we can just see we have, here's our pictures that are coming on. We've plotted them so we have an idea of what we're looking at. Let's go ahead and print. Let's look at the shape of the features. So when we have this, we have our NIST train images, and we'll do the shape on there. Let's take a look and just see what we're looking at as far as our count and everything. And so you can see here we have 55,000. That's basically how many images we have, and this by 784. And in this data set, there's also our labels. So let's take a look at that. We have our NIST train labels shape. Let's take a look and see what that looks like. And there we have 10 because there's 10 digits. So we brought in, that's our output we're looking at. And so we have, there we go, 55,000. They match. They should match because you should have equal numbers in both of those. You know, here's our data in, and here's our answer. If you remember, this is a bunch of zeros, and with one, each one will be 0001, would be what, letter 4 or something like that. So let's take a look at what our one hot encoding did for the first observation. And this is, when we're exploring data, you really want to dig in there and just see what the heck am I looking at. So we're going to look at the labels, and this would be the first label that comes up, and we'll go ahead and run this. And when we look at that, you can see this is what I'm talking about. 0, 0, or 1 is 0, 2 is 0, 3 is 0, 4 is 0, 5 is 0, 6 is 0, 7 equals 1. So our very first label is a 7, but our very first label comes up that it's a 7. And so we don't have like 0 through 9. We have a bunch of zeros and just the 1 to mark it as a 7 on here. So now we've kind of looked a quick look at the data. And in here you might ask some questions like, what is 784? 24 times 24. Remember, that's the size of our grid on there, or our tensor coming in. So 784 is the setup on there. And we've gone through all this viewing the data. We'll go ahead and start looking at our TensorFlow. So let's take our X variable. This is going to be our training set. We'll do a placeholder, and then we're going to have these come in as float. Now, if I remember correctly, they're actually, 0 or 1 for the values, because they're either, but we have them coming in as a float value, and we have a little bit of a shape coming in here, and there's our 784. So we let it know that this is what our input is for our TensorFlow, and this is our training set. So we'll just put a label on there to help us track that, train set, and then W, and with W we'll go ahead and do TF variables, and we'll do this as zeros. Variables, TF zeros, and we'll set this as 784 by 10, 10 being the output, 784 being our number of variables in, and this is our weights. Remember, we have a bias in there too. And I'll go back over this in just a second as we see how that fits together in our TensorFlow. And we'll do this one with our variables. Again, we have 10, so we're going to do the bias. We do it the same kind of format and setup on here. And so we'll do that as TF zeros of 10. So we'll just create an array of 10 there, and this is our bias. So with these 3 lines, and they're coming out with the eager execution, which would bypass some of what we're doing. But this is important to understand, is the first thing you have to do with TensorFlow is we have to allocate a space for the variables. And our TF placeholder and our TF variable with our weights and our biases, this actually hasn't done anything yet. So all it is placeholders. That's why it's okay to use zeros. You could have just as easily used ones or anything else, and it wouldn't matter. The next stage is to go ahead and set up some of the functions going on. But before we do that, just note that this hasn't done anything. Even if I execute it, all it's done is created placeholders until we do the final initialization. And so we need to go ahead and set up, we'll do y equals tf.nn.softmax. And the code for this is tf.matmul xw plus b. And this is our sum. Let's just put a note here so we can keep track of what's going on. We're finding weight weighted sum of inputs plus the bias. So there's our plus b, the bias. And then we need to go ahead, keep let's do y underscore, and again another placeholder. And this one will set, it actually will put in as TF placeholder on here. TF placeholder float none 10. There's our one hot encoder going on there. So our 10 values coming out. And we'll do a cross entropy on here. And this is going to be minus TF reduce sum, and we'll do y. Here's our y underscore, which is, remember, we have your y output and your actual output. So this will be our y underscore times the TF log of y. And then finally, before we do the actual initialization of all our variables, we'll set up our train step. This equals our gradient descent optimizer. Very important. Remember, we looked at that chart on our slides. And so we've set up all these formulas, and here's our gradient descent optimizer, and as it keeps looking for that 0 value. That's what we're doing with that particular formula. So let's take a look and see what we're doing here. We just put together all of our pieces for TensorFlow. And, you know, the devil's in the details. We have here our training set coming in. We have to put a placeholder on there. We have our variables with their weights. We have our biases coming out. And then we put in our the weighted sum. So here's summizing our summation here. Then we have our y variable output. So there's our y, how it works, and then of course the actual output on there. And then we have our cross entropy coming in, and that's our minus TF dot reduce sum, the y times the TF log of y. And then the training step, gradient descent optimizer. We're using a 0.01 in this, and we're going to minimize cross entropy. So we're going to let it do all the work. So once we've set up all of these different layers, we've allocated for them, we need to go ahead and initialize them. So we're going to do an init TF initialize, and it's going to be all variables. One of the cool things is they're in the process of doing away with this. So all these steps would be bundled into one instead of having to have placeholders. You initialize them in the same process going on. And then finally, everything in TensorFlow is based on your session. Now this is changing, that there's other options to be able to run this. But we want to go ahead and do session. There's our TF, which is a TF session. And then we want to go ahead and do session run. And what are we going to run? Well, we did initialization of all our variables. So this is what we're running. And this is where actually, once we do this, we actually create our TensorFlow object. So this whole piece of code right here is our TensorFlow object. We have our input coming in with our weighted variables coming in, our softmax for our metmul going out. How does it add it together for our y value? And then we have the actual float value coming out, checking on our all the way down. So you can see all the different stages going through that we're setting up. And this is one of the reasons that a lot of people like TensorFlow, is because you can designate all these different pieces one step at a time. This is also one of the reasons people don't like TensorFlow, is because you have to designate all the different layers coming down. And there's a lot of steps being made right now to minimize this, to make it either easier to automate it or to allow you to do more complicated things. And all those steps are still at play, so it's worth looking into the more advanced version of what's going on with Keras on top of TensorFlow. It's also important to understand what's going on these individual levels if you're going to play with them. It's important to understand, hey, what's going on with the finding the weighted sum of the inputs plus the bias, because there's other ways to do that. There's all kinds of other tools in there now. But this is the basic setup that you want to do on a TensorFlow coming in. And we want to go ahead and just run and init our TensorFlow. So let's go ahead and do that. Let's run this. We do get a warning here because there's a move to use global variables. This is one of the changes they're making. But as far as this example, it's not going to make a difference because we're doing, once we initialize it, this is initializing our variables. And again, these are only placeholders up here until we initialize them. And I would highly suggest put a note down there or go over to Simplilearn.com and let them know and have them email you a copy of the code so you can actually play with this code right here. Because this is the body of what's going on in TensorFlow. This is the build in neural networks. And then once we've done that, now comes kind of the fun part, is we need to go ahead and train it. So we've created our TensorFlow. We've created our network. And now we need to go ahead and train it. So let's put together that training code. And let's just do for I in range 1,000, 0 to 1,000. So we're just going to look at the first 1,000 in our training training. And the way we pull that data from our mince train next batch of 100, so you look at this, we're going to be doing groups of 100, and then there's going to go through 1,000 of them. This is very important that TensorFlow builds this in. This is one of the downsides of doing sklearn or one of the older packages, is they don't let you batch groups in. They wanted to have it all up front, and then you have to build your own batch programs right now. This lets us go ahead and do that, and you can see here we have batch x of s, batch y of s. So there's our x and our y. You can look at this as our training of x and our train of y, or the data in and the answer in. And then we simply do our session run. So here's our session that we've created. We're going to run it, and we want to do the train step. Remember, we initialized our train step up here in our TF, and so there's our train step. Feed is a dictionary coming in, which we're going to create right here, is x is our batch, x of our sample, comma, and our y underscore is going to be our batch of our y sample. And so this goes through, and we've now hit the run button, and we've trained our session. We've trained this setup on here. And once we've trained it, then we need to go ahead and find out how good our accuracy was and actually start running some predictions through there. So we'll go ahead and create a correct prediction, and this is where our tf.equal, we'll use our argmax y of 1 and tf argmax of y of underscore of 1 to help us get the correct predictions on there. And then we want to use that to feed into an accuracy. And so our accuracy is going to be tf reduce mean, and we'll take that and we'll do a cast, and this is the correct prediction that we're sending in there, and it is a float value. Keep it simple, and let's go ahead and print this out so we can see what we're looking at. So what are we printing out? We need to do a session run. This session run is going to be on the accuracy. Where did accuracy comes from? This is we're casting our TF on there with the correct predictions on that. So here's our accuracy. Feed in, so it needs a dictionary for the data coming in. We're going to create our dictionary, and x is going to be our NIST test images, and y underscore there is going to be our NIST.test labels. Let me just double check and make sure I have that typed in there correctly. There we go, and let's go ahead and run that and see what comes up, and we end up with a 0.9165 for our accuracy, which means our trained neural network does a pretty good job letting us know what these different symbols are, and guessing that a 7 and a 3 and a 4, something that as humans we kind of take for granted. I even have trouble reading this, so I don't know if I would be able, like that first one, I would sit there for a long time figuring out that's a 7 versus a 2. That could have easily been a 2 to me. So you can see we do a pretty good job analyzing this data, and this is used to analyze something very complicated on these images, very different than just a straight value of cost of sales, and here's our return and our marketing. We can now create this nice neural network that does all kinds of cool things. My name is Richard Kirschner with the Simplilearn team. That's www.simplilearn.com. Get it certified, get ahead. Today we're going to be covering the convolutional neural network tutorial. Do you know how deep learning recognizes the objects in an image? And really, this particular neural network is how image recognition works. It's very central, one of the biggest building blocks for image recognition. It does it using convolution neural network. And over here we have the basic picture of a hummingbird. Pixels of an image fed as input. You have your input layer coming in, so it takes that graphic and puts it into the input layer. You have all your hidden layers, and then you have your output layer, and your output layer, one of those is going to light up and say, oh, it's a bird. We're going to go into depth. We're going to actually go back and forth on this a number of times today. So if you're not catching all the image, don't worry, we're going to get into the details. So we have our input layer accepts the pixels of the image as input in the form of arrays. And you can see up here where they've actually labeled each block of the bird in different arrays. So we'll dive into deep as to how that looks like and how those matrices are set up. Your hidden layer carry out feature extraction by performing certain calculations and manipulation. So this is the part that kind of reorganizes that picture multiple ways until we get some data that's easy to read for the neural network. This layer uses a matrix filter and performs convolution operation to detect patterns in the image. And if you remember that convolution means to coil or to twist, so we're going to twist the data around and alter it and use that operation to detect a new pattern. There are multiple hidden layers like convolution layer. ReLU is how that is pronounced, and that's the rectified linear unit. That has to do with the activation function that's used. Pooling layer also uses multiple filters to detect edges, corners, eyes, feathers, beak, etc. And just like the term says, pooling is pooling information together. And we'll look into that a lot closer here. So if it's a little confusing now, we'll dig in deep and try to get you squared away with that. And then finally, there is a fully connected layer that identifies the object in the image. So we have these different layers coming through in the hidden layers, and they come into the final area, and that's where we have, say, one node or one neural network entity that lights up that says it's a bird. What's in it for you? We're going to cover an introduction to the CNN, what is convolution neural network, how CNN recognizes images. We're going to dig deeper into that and really look at the individual layers in the convolutional neural network. And finally, we do a use case implementation using the CNN. We'll begin our introduction to the CNN by introducing the pioneer of convolutional neural network, Yann LeCun. He was the director of Facebook AI Research Group. Built the first convolutional neural network called LeNet in 1988. So these have been around for a while and have had a chance to mature over the years. It was used for character recognition tasks like reading zip code digits. Imagine processing mail and automating that process. CNN is a feed-forward neural network that is generally used to analyze visual images by producing data with a grid-like topology. A CNN is also known as a convnet. And very key to this is we are looking at images. That was what this was designed for, and you'll see the different layers as we dig in mirror some of them are actually now used since we're using TensorFlow and Keras in our code later on. You'll see that some of those layers appear in a lot of your other neural network frameworks. But in this case, this is very central to processing images and doing so in a variety that captures multiple images and really drills down into their different features. In this example here, you see flowers of two varieties, orchid and a rose. I think the orchid is much more dainty and beautiful, and the rose smells quite beautiful. I have a couple rose bushes in my yard. They go into the input layer. That data is then sent to all the different nodes in the next layer, one of the hidden layers, based on its different weights and its setup. It then comes out and gives those a new value. Those values then are multiplied by their weights and go to the next hidden layer, and so on. And then you have the output layer, and one of those nodes comes out and says it's an orchid, and the other one comes out and says it's a rose, depending on how well it was trained. What separates the CNN, or the convolutional neural network, from other neural networks is a convolutional operation. Forms the basis of any convolutional neural network. In a CNN, every image is represented in the form of arrays of pixel values. So here we have a real image of the digit 8. That then gets put onto its pixel values, represented in the form of an array. In this case, you have a two-dimensional array. And then you can see in the final end form, we transform the digit 8 into its representational form of pixels of zeros and ones, where the ones represent, in this case, the black part of the 8, and the zeros represent the white background. To understand the convolution neural network, or how that convolutional operation works, we're going to take a sidestep and look at matrices. In this case, we're going to simplify it, and we're going to take two matrices, A and B, of one dimension. Now, kind of separate this from your thinking as we learn that you want to focus just on the matrix aspect of this. And then we'll bring that back together and see what that looks like when we put the pieces for the convolutional operation. Here we've set up two arrays. We have, in this case, they're a single dimension matrix. And we have A equals 5, 3, 7, 5, 9, 7. And we have B equals 1, 2, 3. So in the convolution, as it comes in there, it's going to look at these two, and we're going to start by multiplying them, A times B. And so we multiply the arrays element-wise, and we get 5, 6, 6, where 5 is the 5 times 1, 6 is 3 times 2, and then the other 6 is 2 times 3. And since the two arrays aren't the same size, they're not the same setup, we're going to just truncate the first one, and we're going to look at the second array multiplied just by the first three elements of the first array. Now that's going to be a little confusing. Remember, a computer gets to repeat these processes hundreds of times, so we're not going to just forget those other numbers later on. We'll bring those back in. And then we have the sum of the product. In this case, 5 plus 6 plus 6 equals 17. So in our A times B, our very first digit in that matrix of A times B is 17. And if you remember, I said we're not going to forget the other digits. So we now have 3, 2, 5. We move one set over, and we take 3, 2, 5, and we multiply that times b. And you'll see that 3 times 1 is 3, 2 times 2 is 4, and so on and so on. We sum it up, so now we have the second digit of our a times b product in the matrix. And we continue on with that same thing, so on and so on. So then we would go from 375 to 759 to 597. This short matrix that we have for A, we've now covered all the different entities in A that match 3 different levels of B. Now, in a little bit, we're going to cover where we use this math at, this multiplying of matrices and how that works. But it's important to understand that we're going through the matrix and multiplying the different parts to it to match the smaller matrix with the larger matrix. I know a lot of people get lost at is, what's going on here with these matrices? Ooh, scary math. Not really that scary when you break it down. We're looking at a section of A and we're comparing it to B. So when you break that down in your mind like that, you realize, okay, so I'm just taking these two matrices and comparing them, and I'm bringing the value down into one matrix, A times B. We're reducing that information in a way that will help the computer see different aspects. Let's go ahead and flip over again back to our images. Here we are back to our images. Talking about going to the most basic two-dimensional image you can get to. Consider the following two images. The image for the symbol backslash. When you press the backslash, the above image is processed. And you can see there for the image for the forward slash is the opposite. So when we click the forward slash button, that flips. Very basic. We have 4 pixels going in. Can't get any more basic than that. Here we have a little bit more complicated picture. We take a real image of a smiley face. Then we represent that in the form of black and white pixels. So if this was an image in the computer, it's black and white. And like we saw before, we convert this into the zeros and ones. So where the other one would have just been a matrix of just 4 dots, now we have a significantly larger image coming in. So don't worry, we're going to bring this all together here in just a little bit. Layers in convolutional neural network. When we're looking at this, we have our convolution layer. And that really is the central aspect of processing images in the convolutional neural network. That's why we have it. And then that's going to be feeding in. And you have your ReLU layer, which is, as we talked about, the rectified linear unit. We'll talk about that a little bit later. The ReLU is how that layer is activated, is the math behind it, what makes the neurons fire. You'll see that in a lot of other neural networks. When you're using it just by itself, it's for processing smaller amounts of data, where you use the atom activation feature for large data coming in. Now, because we're processing small amounts of data in each image, the ReLU layer works great. You have your pooling layer. That's where you're pooling the data together. Pooling is a neural network term. It's very commonly used. I like to use the term reduce. So if you're coming from the map and reduce side, you'll see that we're mapping all this data through all these networks, and then we're going to reduce it. We're going to pool it together. And then finally we have the fully connected layer. That's where our output's going to come out. So we have started to look at matrices. We've started to look at the convolutional layer and where it fits in and everything. We've taken a look at images. So we're going to focus more on the convolution layer, since this is a convolutional neural network. A convolution layer has a number of filters and perform convolution operation. Every image is considered as a matrix of pixel values. Consider the following 5x5 image whose pixel values are only 0 and 1. Now obviously when we're dealing with color, there's all kinds of things that come in on color processing, but we want to keep it simple and just keep it black and white. And so we have our image pixels, so we're sliding the filter matrix over the image and computing the dot product to detect the patterns. And right here, you're going to ask, where does this filter come from? This is a bit confusing because the filter is going to be derived later on. We build the filters when we program or train our model. So you don't need to worry what the filter actually is, but you do need to understand how a convolution layer works, is what is the filter doing. Filter, and you'll have many filters. You don't have just one filter. You'll have lots of filters that are going to look for different aspects. And so the filter might be looking for just edges, it might be looking for different parts. We'll cover that in a little bit more detail in a minute. Right now we're just focusing on how the filter works as a matrix. Remember earlier we talked about multiplying matrices together? And here we have our two-dimensional matrix. And you can see we take the filter and we multiply it in the upper left image, and you can see right here 1 times 1, 1 times 0, 1 times 1. We multiply those all together, then sum them, and we end up with a convolved feature of 4. We're going to take that and sliding the filter matrix over the image and computing the dot product to detect patterns. So we're just going to slide this over. We're going to predict the first one and slide it over 1 notch, predict the second one, and so on all the way through until we have a new matrix. And this matrix, which is the same size as the filter, has reduced the image, and whatever filter, whatever that's filtering out, it's going to be looking at just those features reduced down to a smaller matrix. So once the feature maps are extracted, the next step is to move them to the ReLU layer. So the ReLU layer, the next step, first is going to perform an element-wise operation. So each of those maps coming in, if there's negative pixels, so it sets all the negative pixels to 0. And you can see this nice graph where it just zeroes out the negatives, and then you have a value that goes from 0 up to whatever value is coming out of the matrix. This introduces nonlinearity to the network. So up until now, we say linearity, we're talking about the fact that the feature has a value. So it's a linear feature. This feature came up and it has, let's say the feature is the edge of the beak. It's like, or that backslash that we saw. It'll look at that and say, okay, this feature has a value from -10 to 10 in this case. If it was 1, it'd say, yeah, this might be a beak. It might not. It might be an edge right there. A -5 means, no, we're not even going to look at it. It's a 0. And so we end up with an output, and the output takes all these filtered features. Remember, we're not just running one filter on this, we're running a number of filters on this image. And so we end up with a rectified feature map that is looking at just the features coming through and how they weigh in from our filters. So here we have an input of it looks like a toucan bird. Very exotic looking. Real image is scanned in multiple convolution and the ReLU layers for locating features. And you can see up here is turned it into a black and white image. And in this case, we're looking in the upper right-hand corner for a feature, and that box scans over. A lot of times it doesn't scan 1 pixel at a time. A lot of times it will skip by 2 or 3 or 4 pixels to speed up the process. That's one of the ways you can compensate if you don't have enough resources on your computation for large images. And it's not just one filter that slowly goes across the image. You have multiple filters that have been programmed in there. So you're looking at a lot of different filters going over the different aspects of the image and just sliding across there and forming a new matrix. One more aspect to note about the ReLU layer is we're not just having one ReLU coming in. So not only do we have multiple features going through, but we're generating multiple ReLU layers for locating the features. That's very important to note. So we have quite a bundle. We have multiple filters, multiple ReLU, which brings us to the next step, forward propagation. Now we're going to look at the pooling layer. The rectified feature map now goes through a pooling layer. Pooling is a downsampling operation that reduces the dimensionality of the feature map. That's all we're trying to do. We're trying to take a huge amount of information and reduce it down to a single answer. This is a specific kind of bird. This is an iris. This is a rose. So you have a rectified feature map. And you see here we have a rectified feature map coming in. We set the max pooling with a 2x2 filters and a stride of 2. And if you remember correctly, I talked about not going 1 pixel at a time. Well, that's where the stride comes in. We end up with a 2x2 pooled feature map, but instead of moving 1 over each time and looking at every possible combination, we skip a few there. We go by 2. We skip every other pixel. We just do every other one. And this reduces our rectified feature map, which as you can see over here, 16 by 16 to a 4 by 4. So we're continually trying to filter and reduce our data so that we can get to something we can manage. And over here you see that we have the max 3, 4, 1, and 2. And in the max pooling, we're looking for the max value, a little bit different than what we were looking at before. So coming from the rectified feature, we're now finding the max value and then we're pooling those features together. So instead of thinking of this as image of the map, think of this as how valuable is a feature in that area? How much of a feature value do we have? And we just want to find the best or the maximum feature for that area. They might have that one piece of the filter of the beak said, oh, I see a 1 in this beak in this image, and then it skips over and says, I see a 3 in this image, and it says, oh, this one is rated as a 4. We don't want to sum it together because then you might have like 5 ones, and it'll say, 5, but you might have 4 zeros and 1 10, and that 10 says, well, this is definitely a beak, where the ones will say, probably not a beak. A little strange analogy since we're looking at a bird, but you can see how that pooled feature map comes down, and we're just looking for the max value in each one of those matrices. Pooling layer uses different filters to identify different parts of the image, like edges, corners, body, feathers, eyes, beak, etc. I know I focus mainly on the beak, but obviously each feature could be a different part of the bird coming in. So let's take a look at what that looks like. Structure of a convolution neural network so far. This is where we're at right now. We have our input image coming in, and then we use our filters, and there's multiple filters on there that are being developed to kind of twist and change that data, and so we multiply the matrices. We take that little filter, maybe it's a 2 by 2, we multiply it by each piece of the image, and if we step 2, then it's every other piece of the image. That generates multiple convolution layers. So we have a number of convolution layers we have set up in there just looking at that data. We then take those convolution layers, we run them through the ReLU setup, and then once we've done through the ReLU setup, and we have multiple ReLUs going on, multiple layers that are ReLU, then we're going to take those multiple layers and we're going to be pooling them. So now we have the pooling layers, or multiple poolings going on. Up until this point, we're dealing with, sometimes it's multiple dimensions. You can have 3 dimensions. Some strange data setups that aren't doing images but looking at other things, they can have 4, 5, 6, 7 dimensions. So right now we're looking at 2D image dimensions coming into the pooling layer. So the next step is we want to reduce those dimensions, or flatten them. So flattening. Flattening is a process of converting all of the resultant two-dimensional arrays from pooled feature map into a single long continuous linear vector. So over here you see where we have a pooled feature map. Maybe that's the bird wing, and it has values 6, 8, 4, 7. And we want to just flatten this out and turn it into 6, 8, 4, 7, or a single linear vector. And we find out that not only do we do each of the pooled feature maps, we do all of them into one long linear vector. So now we've gone through our convolutional neural network part, and we have the input layer into the next setup. All we've done is taken all those different pooling layers and we've flattened them out and combined them into a single linear vector going in. So after we've done the flattening, we have just a quick recap because we've covered so much, so it's important to go back and take a look at each of the steps we've gone through. The structure of the network so far is we have our convolution where we twist it and we filter it and multiply the matrices. We end up with our convolutional layer, which uses the ReLU to figure out the values going out into the pooling. And so you have numerous convolution layers that then create numerous pooling layers, pooling that data together, which is the max value, which one we want to send forward. We want to send the best value. And then we're going to take all of that from each of the pooling layers and we're going to flatten it. And we're going to combine them into a single input going into the final layer. Once you get to that step, you might be looking at that going, boy, that looks like the normal input to most neural network. And you're correct, it is. So once we have the flattened matrix from the pooling layer, that becomes our input. So the pooling layer is fed as an input to the fully connected layer to classify the image. And so you can see as our flattened matrix comes in this case we have the pixels from the flattened matrix fed as an input back to our toucan, or whatever that kind of bird that is. I need one of these to identify what kind of bird that is. It comes into our forward propagation network. And that will then have the different weights coming down across. And then finally it selects that that's a bird and that it's not a dog or a cat in this case. Even though it's not labeled, the final layer there in red is our output layer, our final output layer that says bird, cat, or dog. So, quick recap of everything we've covered so far. We have our input image, which is twisted and multiplied. The filters are multiplied times the two matrices multiplied all the filters to create our convolution layer. Our convolution layers, there's multiple layers in there because it's all building multiple layers off the different filters. Then goes through the ReLU as its activation, and that creates our pooling. And so once we get into the pooling layer, we then on the pooling look for who's the best, what's the max value coming in from our convolution. And then we take that layer and we flatten it, and then it goes into a fully connected layer, our fully connected neural network, and then to the output. And here we can see the entire process, how the CNN recognizes a bird. This is kind of nice because it's showing the little pixels and where they're going. You can see the filter is generating this convolution network, and that filter shows up in the bottom part of the convolution network. And then based on that, it uses the ReLU for the pooling. The pooling then find out which one's the best, and so on, all the way to the fully connected layer at the end, or the classification in the output layer. So that'd be a classification neural network at the end. So we covered a lot of theory up till now, and you can imagine each one of these steps has to be broken down in code. So putting that together can be a little complicated. Not that each step of the process is overly complicated, but because we have so many steps. We have 1, 2, 3, 4, 5 different steps going on here with sub-steps in there. We're going to break that down and walk through that in code. So in our use case implementation using the CNN, we'll be using the CFAR10 dataset from Canadian Institute for Advanced Research for classifying images across 10 categories. Unfortunately, they don't let me know whether it's going to be a toucan or some other kind of bird, but we do get to find out whether it can categorize between a ship, a frog, deer, bird, airplane, automobile, cat, dog, horse, truck. So that's a lot of fun. And if you're looking anything in the news at all of our automated cars and everything else, you can see where this kind of processing is so important in today's world and very cutting edge as far as what's coming out in the commercial deployment. I mean, this is really cool stuff. We're starting to see this just about everywhere in industry. So great time to be playing with this and figuring it all out. Let's go ahead and dive into the code and see what that looks like when we're actually writing our script. Before we go on, let's do one more quick look at what we have here. Let's just take a look at data batch 1 keys. And remember, in Jupyter Notebook, I can get by with not doing the print statement. If I put a variable down there, it'll just display the variable. And you can see under data batch 1 for the keys, since this is a dictionary, we have the batch 1 label, data, and file names. So you can actually see how it's broken up in our data set. So for the next step, or step 4 as we're calling it, we want to display the image using Matplotlib. There's many ways to display the images. You could even, well, there's other ways to drill into it, but Matplotlib is really good for this. And we'll also look at our first reshape setup, or shaping the data, so you can have a little glimpse into what that means. So we're going to start by importing our matplot, and of course, since I am doing Jupyter Notebook, I need to do the matplot inline command, so it shows up on my page. So here we go. We're going to import matplotlib.pyplot as PLT. And if you remember Matplotlib, the pyplot is like a canvas that we paint stuff onto. And there's my %sign matplotlib inline, so it's going to show up in my notebook. And then of course we're going to import numpy as np for our numbers Python array setup. And let's go ahead and set x equals to data batch 1. So this will pull in all the data going into the x value. And then, because this is just a long stream of binary data, we need to go a little bit of reshaping. So in here we have to go ahead and reshape the data. We have 10,000 images. Okay, that looks correct. And this is kind of an interesting thing. It took me a little bit I had to go research this myself to figure out what's going on with this data. And what it is it's a 32 by 32 picture. And let me do this. Let me go ahead and do a drawing pad on here. So we have 32 bits by 32 bits, and it's in color. So there's 3 bits of color. Now, I don't know why the data is particularly like this. It probably has to do with how they originally encoded it. But most pictures put the 3 afterward. So what we're doing here is we're going to take the shape, we're going to take the data, which is just a long stream of information, and we're going to break it up into 10,000 pieces, and those 10,000 pieces then are broken into 3 pieces each, and those 3 pieces then are 32 by 32. You could look at this like an old-fashioned projector where they have the red screen, or the red projector, the blue projector, and the green projector, and they add them all together, and each one of those is a 32 by 32 bit. So that's probably how this was originally formatted, was in that kind of ideal. Things have changed, so we're going to transpose it, and we're going to take the 3, which was here, and we're going to put it at the end. So the first part is reshaping the data from a single line of bit data, or whatever format it is, into 10,000 by 3 by 32 by 32, and then we're going to transpose the color factor to the last place. So it's the image, then the 32 by 32 in the middle, that's this part right here, and then finally we're going to take this, which is 3 bits of data, and put it at the end. So it's more like we process images now. And then as type. This is really important that we're going to use an integer 8. You can come in here and you'll see a lot of these, they'll try to do this with a float or a float 64. What you got to remember though is a float uses a lot of memory. So once you switch this into something that's not integer 8, which goes up to 128, you are just going to, the amount of RAM, let me just put that in here, is going to go way up. The amount of RAM that it loads. So you want to go ahead and use this. You can try the other ones and see what happens if you have a lot of RAM on your computer. But for this exercise, this will work just fine. And let's go ahead and take that and run this. So now our X variable is all loaded and it has all the images in it from the batch 1, data batch 1. And just to show what we were talking about with the as type on there, if we go ahead and take X0 and just look for its max value, let me go ahead and run that. You'll see it doesn't, oops, I said 128, it's 255. You'll see it doesn't go over 255 because it's basically an ASCII character is what we're keeping that down to. We're keeping those values down. So they're only 255, 0 to 255 versus a float value, which would bring this up exponentially in size. And since we're using the matplot library, we can do, oops, that's not what I wanted. Since we're using the matplot library, we can take our canvas and just do a plt.im for image show, and let's just take a look at what X0 looks like. And it comes in, I'm not sure what that is, but you can see it's a very low grade image broken down to the minimal pixels on there. And if we did the same thing, let's see what 1 looks like. Hopefully it's a little easier to see. Run on there, not enter. Let's hit the run on that. And we can see this is probably a semi-truck. That's a good guess on there. And I can just go back up here instead of typing the same line in over and over. And we'll look at 3. That looks like a dump truck unloading, and so on. You can do any of the 10,000 images. We can just jump to 55. Looks like some kind of animal looking at us there, probably a dog. And just for fun, let's do just one more run on there, and we can see a nice car for our image number 4. So you can see we paste through all the different images. It's very easy to look at them, and they've been reshaped to fit our view and what the matplot library uses for its format. So the next step is we're going to start creating some helper functions. We'll start by a one-hot encoder to help us when we're processing the data. Remember that your labels, they can't just be words. They have to switch it, and we use the one-hot encoder to do that. And then we'll also create a class CFAR helper, so it's going to have an init and a setup for the images. And then finally we'll go ahead and run that code so you can see what that looks like. And then we get into the fun part where we're actually going to start creating our model, our actual neural network model. So let's start by creating our one-hot encoder. We're going to create our own here, and it's going to return an out. And we'll have our vector coming in and our values equal 10. What this means is that we have the 10 values, the 10 possible labels. And remember, we don't look at the labels as a number, because a car isn't one more than a horse. That'd be just kind of bizarre to have horse equals 0, car equals 1, plane equals 2, cat equals 3. So a cat plus a car equals what? So instead, we create a NumPy array of zeros. And there's going to be 10 values, so we have 10 different values in there. So you have 0 or 1. 1 means it's a cat, 0 means it's not a cat. In the next line it might be that 1 means it's a car, 0 means it's not a car. So instead of having one output with a value of 0 to 10, you have 10 outputs with the values of 0 to 1. That's what the one-hot encoder is doing here. And we're going to utilize this in code in just a minute. So let's go ahead and take a look at the next helpers. We have a few of these helper functions we're going to build. And when you're working with a very complicated Python project, dividing it up into separate definitions and classes is very important. Otherwise, it just becomes really ungainly to work with. So let's go ahead and put in our next helper, which is a class. And there's a lot in this class, so we'll break it down here. And let's just start, oops, we can put a space right in there. There we go. Now this is a little bit more readable. Add a second space. So we're going to create our class, the Cipher Helper. And we'll start by initializing it. Now, there's a lot going on in here. So let's start with the init part. Self.I equals 0. That'll come in a little bit. We'll come back to that. in the lower part. We want to initialize our training batches. So when we went through this, there was like a meta batch. We don't need the meta batch, but we do need the data batch 1, 2, 3, 4, 5, and we do not want the testing batch in here. This is just the self all train batches. So we're going to make an array of all those different images. And then of course we left the test batch out, so we have our self.test batch. We're going to initialize the training images and the training labels, and also the test images and the test labels. So this is just to initialize these variables in here. Then we create another definition down here, and this is going to set up the images. And let's just take a look and see what's going on in there. Now we could have all just put this as part of the init part, since this is all just helper stuff, but breaking it up again makes it easier to read. It also makes it easier when we start executing the different pieces to see what's going on. So that way we have a nice print statement to say, hey, we're now running this and this is what's going on in here. We're going to set up these self-training images at this point, and that's going to go to a numpy array vstack. And in there we're going to load up, in this case, the data for D and self all train batches. Again, that points right up to here. So we're going to go through each one of these files, or each one of these data sets, because they're not a file anymore. We've brought them in. Data batch 1 points to the actual data. And so our self-training images is going to stack them all into a numpy array. And then it's always nice to get the training length, and that's just a total number of self-training images in there. And then we're going to take the self-training images. And let me switch marker colors, because I am getting a little too much on the markers up here. Oops, there we go. Bring down our marker change so we can see it a little better. And at this point, this should look familiar. Where did we see this? Well, when we wanted to look at this above, and we wanted to look at the images in the Matplot library, we had to reshape it. So we're doing the same thing here. We're taking our self-training images, and based on the training length, total number of images, because we stacked them all together, so now it's just one large file of images, we're going to take and look at it as our 3 video cameras that are each displaying 32 by 32, and we're going to switch that around so that now we have each of our images that stays the same place, and then we have our 32 by 32, and then by our 3. Our 3 different values for the color. And of course we want to go ahead and they run this where you say divide by 255. That was from earlier. It just brings all the data into 0 to 1. That's what this is doing. So we're turning this into a 0 to 1 array, which is all the pictures 32 by 32 by 3. And then we're going to take the self-training labels, and we're going to pump those through our one-hot encoder we just made, and we're going to stack them together. And again, we're converting this into an array that goes from, instead of having horse equals 1, dog equals 2, and then horse plus dog would equal 3, which would be cat. No, it's going to be an array of 10 where each one is 0 to 1. Then we want to go ahead and set up our test images and labels. And when we're doing this, you're going to see it's the same thing we just did with the rest of them. We just changed colors right here. This is no different than what we were doing up here with our training set. We're going to stack the different images. We're going to get the length of them so we know how many images are in there. You certainly could add them by hand, but it's nice to let the computer do it, especially if it ever changes on the other end and you're using other data. And again, we reshape them and transpose them, and we also do the one-hot encoder. Same thing we just did on our training images. So now our test images are in the same format. So now we have a definition which sets up all our images in there. And then the next step is to go ahead and batch them, or next batch. And let's do another breakout here for batches, because this is really important to understand. It tends to throw me for a little loop when I'm working with TensorFlow or Keras or a lot of these. We have our data coming in. If you remember, we had like 10,000 photos. Let me just put 10,000 down here. We don't want to run all 10,000 at once, so we want to break this up into batch sizes. And you also remember that we had the number of photos, in this case length of test or whatever number is in there. We also have 32 by 32 by 3. So when we're looking at the batch size, we want to change this from 10,000 to a batch of, in this case I think we're going to do batches of 100. So we want to look at just 100, the first 100 of the photos. And if you remember, we set self-I equal to 0. So what we're looking at here is we're going to create X. we're going to get the next batch from the very initialized. We've already initialized it for 0. So we're going to look at x from 0 to batch size, which we've set to 100. So just the first 100 images. And then we're going to reshape that into, and this is important to let the data know, that we're looking at 100 by 32 by 32 by 3. Now, we've already formatted it to the 32 by 32 by 3. This just sets everything up correctly so that X has the data in there in the correct order and the correct shape. And then the Y, just like the X, is our labels. So our training labels, again, they go from 0 to batch size. In this case, they do self I plus batch size because the self I is going to keep changing. And then finally, we increment the self I because we have 0. So the next time we call it, we're going to get the next batch size. And so basically, we have X and Y. X being the photograph data coming in and Y being the label. And that, of course, is labeled through one hot encoder. So if you remember correctly, if it was, say, horse is equal to 0, it would be 1 for the 0 position, since this is the horse, and then everything else would be 0 in here. Let me just put lines through there. There we go. There's our array. Hard to see that array. So let's go ahead and take that, and we're going to finish loading it, since this is our class. And now we're armed with all this, our setup over here. Let's go ahead and load that up. And so we're going to create a variable ch with the cfar helper in it. And then we're going to do ch.setupImages. Now we could have just put all of the setup images under the init, but by breaking this up into 2 parts, it makes it much more readable. And also, if you're doing other work, there's reasons to do that as far as the setup. Let's go ahead and run that. And you can see where it says setting up training images and labels, setting up test images. And that's one of the reasons we broke it up, is so that if you're testing this out, you can actually have print statements in there telling you what's going on, which is really nice. They did a good job with this setup. I like the way that it was broken up in the back. And then one quick note, you want to remember that batch, to set up the next batch, since we have to run batch equals ch next batch of 100, because we're going to use the 100 size. But we'll come back to that. We're going to use that. Just remember that that's part of our code we're going to be using in a minute from the definition we just made. So now we're ready to create our model. First thing we want to do is we want to import our TensorFlow as TF. I'll just go ahead and run that so it's loaded up. And you can see we got a warning here. That's because they're making some changes. It's always growing, and they're going to be depreciating one of the values from float 64 to float type, or is treated as an NP float 64. Nothing to really worry about, because this doesn't even affect what we're working on, because we've set all of our stuff to a 255 value, or 0 to 1. And do keep in mind that 0 to 1 value that we converted to 255 is still a float value, but it'll easily work with either the NumPy float 64 or the NumPy D-type float. It doesn't matter which one it goes through, so the depreciation would not affect our code as we have it. And in our TensorFlow, we'll go ahead, let me just increase the size in there just a moment so you can get a better view of the what we're typing in. We're going to set a couple placeholders here. And so we're going to set x equals tf placeholder tf float 32. We just talked about the float 64 versus the NumPy float. We're actually just going to keep this at float 32. More than significant number of decimals for what we're working with. And since it's a placeholder, we're going to set the shape equal to, and we've set it equal to none, because at this point we're just holding the place on there. We'll be setting up as we run the batches. That's what that first value is. And then 32 by 32 by 3, that's what we reshaped our data to fit in. And then we have our y true equals placeholder tf float 32, and the shape equals none, comma 10. 10 is the 10 different labels we have, so it's an array of 10. And then let's create one more placeholder. We'll call this hold prob, or hold probability. And we're going to use this. We don't have to have a shape or anything for this. This placeholder is for what we call dropout. If you remember from our theory before, we drop out so many nodes is looking at, or the different values going through, which helps decrease bias. So we need to go ahead and put a placeholder for that also. And we'll run this, so it's all loaded up in there. So we have our 3 different placeholders. And since we're in TensorFlow, when you use Keras, it does some of this automatically, but we're in TensorFlow direct. Keras sits on TensorFlow. We're going to go ahead and create some more helper functions. We're going to create something to help us initialize the weights, initialize our bias. If you remember that each layer has to have a bias going in. We're going to go ahead and work on our conversional 2D, our max pool, so we have our pooling layer, our convolutional layer, and then our normal full layer. So we're going to go ahead and put those all into definitions, and let's see what that looks like in code. And you can also grab some of these helper functions from the MNIST, the NIST setup. Let me just put that in there if you're under the TensorFlow. So a lot of these are already in there, but we're going to go ahead and do our own. And we're going to create our init weights. And one of the reasons we're doing this is so that you can actually start thinking about what's going on in the back end. So even though there's ways to do this with an automation, sometimes these have to be tweaked and you have to put in your own setup in here. Now we're not going to be doing that. We're just going to recreate them for our code. And let's take a look at this. We have our weights, and so what comes in is going to be the shape, and what comes out is going to be random numbers. So we're going to go ahead and just init some random numbers based on the shape with a standard deviation of 0.1. Kind of a fun way to do that. And then the TF variable, init random distribution. So we're just creating a random distribution on there. That's all that is for the weights. Now, you might change that. You might have a higher standard deviation. In some cases, you actually load preset weights. That's pretty rare. Usually you're testing that against another model or something like that, and you want to see how those weights configure with each other. Now remember, we have our bias, so we need to go ahead and initialize the bias with a constant. In this case, we're using 0.1. A lot of times the bias is just put in as 1, and then you have your weights to add on to that. But we're going to set this as 0.1. So we want to return a convolutional 2D, in this case a neural network. This is would be a layer on here. What's going on with the conv2D is we're taking our data coming in, we're going to filter it. Strides, if you remember correctly, strides came from, here's our image, and then we only look at this picture here, and then maybe we have a stride of 1, so we look at this picture here, and we continue to look at the different filters going on there. The other thing this does is that we have our data coming in as 32 by 32 by 3. And we want to change this so that it's just, this is 3 dimensions, and it's going to reformat this as just 2 dimensions. So it's going to take this number here and combine it with the 32 by 32. So this is a very important layer here because it's reducing our data down using different means. And it connects down, I'm just going to jump down one here. It goes with the convolutional layer. So you have your kind of your pre-formatting and the setup, and then you have your actual convolution layer that goes through on there. And you can see here we have init weights by the shape, init bias, shape of 3, because we have the 3 different, here's our 3 again. And then we return the TFNN ReLU with the convention 2D, so this convolutional has this feeding into it. Right there, it's using that as part of it. And of course the input is the XY plus B, the bias. So that's quite a mouthful, but these two are the keys here to creating the convolutional layers there. The convolutional 2D coming in, and then the convolutional layer, which then steps through and creates all those filters we saw. Then of course we have our pooling. So after each time we run it through the conventional layer, we want to pool the data. If you remember correctly on the pool side, and let me just get rid of all my marks, it's getting a little crazy there. And in fact, let's go ahead and jump back to that slide. Let's just take a look at that slide over here. So we have our image coming in. We create our convolutional layer with all the filters. Remember, the filters go, the filters coming in here, and it looks at these 4 boxes. And then if it's a step, let's say step 2, it then goes to these 4 boxes, and then the next step, and so on. So we have our convolutional layer that we generate, or convolutional layers. They use the ReLU function. There's other functions out there. For this, though, the ReLU is the one that works the best, at least so far. I'm sure that will change. And then we have our pooling. Now, if you remember correctly, the pooling was max. So if we had the filter coming in, and they did the multiplication on there, and we have a 1, and maybe a 2 here, and another 1 here, and a 3 here, 3 is the max. And so out of all of these, you then create an array that would be 3, and if the max is over here 2 or whatever it is, that's what goes into the pooling, of what's going on in our pooling. So again, we're reducing that data down. We're reducing it down as small as we can, and then finally we're going to flatten it out into a single array, and that goes into our fully connected layer. And you can see that here in the code. Right here we're going to create our normal full layer. So at some point we're going to take from our pooling layer, this will go into some kind of flattening process, and then that will be fed into the different layers going in down here. And so we have our input size. You'll see our input layer get shape, which is just going to get the shape for whatever's coming in. And then input size, initial weights is also based on the input layer coming in. And the input size down here is based on the input layer shape. So we're just going to already use the shape and already have our size coming in. And of course, you have to make sure you init the bias. Always put your bias on there. And we'll do that based on the size. So this will return tf.matmul input layer W plus B. This is just a normal full layer. That's what this means right down here. That's what we're going to return. So that was a lot of steps we went through. Let's go ahead and run that. So those are all loaded in there. And let's go ahead and create the layers. Let's see what that looks like. Now that we've done all the heavy lifting and everything, we get to do all the easy part. Let's go ahead and create our layers. We'll create a convolution layer 1 and 2 different convolutional layers, and then we'll take that and we'll flatten that out, create a reshape pooling in there for our reshape, and then we'll have our full layer at the end. So let's start by creating our first convolutional layer. Then we come in here, and let me just run that real quick. And I want you to notice on here the 3 and the 32. This is important because coming into this convolutional layer, we have 3 different channels and 32 pixels each. So that has to be in there. The 4 and 4 you can play with. This is your filter size. So if you remember, you have a filter and you have your image, and the filter slowly steps over and filters out this image depending on what your step is. For this particular setup, 4 is just fine. That should work pretty good for what we're doing and for the size of the image. And then of course at the end, once you have your convolutional layer set up, you also need to pool it, and you'll see that the pooling is automatically set up so that it would see the different shape based on what's coming in. So here we have max 2x2, and we put in the convolutional 1 that we just created, the convolutional layer we just created goes right back into it. And that right up here, as you can see, is the X. It's coming in from here, so it knows to look at the first model and set the data accordingly. Set that up so it matches. And we went ahead and ran this already. I think I ran it. Let me go and run it again. And if we're going to do one layer, let's go ahead and do a second layer down here. And it's we'll call it Convo 2. It's also a convolutional layer on this. And you'll see that we're feeding convolutional 1 in, the pooling. So it goes from convolutional 1 into convolutional 1 pooling, from convolutional 1 pooling into convolutional 2, and then from convolutional 2 into convolutional 2 pooling. And we'll go ahead and take this and run this. So these variables are all loaded into memory. And for our flattened layer, let's go ahead and we'll do, since we have 64 coming out of here and we have 4 by 4 going in, let's do 8 by 8 by 64. So let's do 4096. This is going to be the flat layer. So that's how many bits are coming through on the flat layer. And we'll reshape this. So we'll reshape our Convo 2 pooling, and that will feed into here, the Convo 2 pooling, and then we're going to set it up as a single layer that's 4096 in size. That's what that means there. We'll go ahead and run this. So we've now created this variable, the Convo 2 flat, and then we have our first full layer. This is the final neural network where we have the flat layer going in. And we're going to again use the ReLU for our setup on there in a neural network for evaluation. And you'll notice that we're going to create our first full layer. Our normal full layer, that's our definition. So we created that. That's creating the normal full layer. And our input for the data comes right here from this goes right into it. The Convo 2 flat. So this tells it how big the data is. And we're going to have it come out. It's going to have 1024. That's how big the layer is coming out. We'll go ahead and run this. So now we have our full layer 1. And with the full layer 1, we want to also define the full 1 dropout to go with that. So our full layer 1 comes in, keep probability equals hold probability. Remember we created that earlier. And the full layer 1 is what's coming into it. And this is going backwards and training the data. We're not training every weight. We're only training a percentage of them each time, which helps get rid of the bias. So let me go ahead and run that. And finally, we'll go ahead and create a y-predict, which is going to equal the normal full 1 dropout and 10, because we have 10 labels in there. Now, in this neural network, we could have added additional layers. That would be another option to play with. You can also play with, instead of 1024, you can use other numbers for the way that sets up on what's coming out and going into the next one. We're only going to do just the 1 layer and the 1 layer dropout. And you can see if we did another layer, it'd be real easy just to feed in the full 1 dropout into full layer 2. And then full layer 2 dropout would have full layer 2 feed into it. And then you'd switch that here for the Y prediction. For right now, this is great. This particular data set is tried and true, and we know that this will work on it. And if we just type in Y predict and we run that, we'll see that this is a tensor object, shape $10, d-type 32. A quick way to double check what we're working on. So now we've got all of our, we've done a setup all the way to the Y predict, which we just did. We want to go ahead and apply the loss function and make sure that's set up in there. Create the optimizer, and then train our optimizer and create a variable to initialize all the global TF variables. So before we dive into the loss function, let me point out one quick thing, or just kind of a rehab over a couple things. And that is, when we're playing with these setups, we pointed out up here we can change the 4 and use different numbers there. They change your outcome. So depending on what numbers you use here will have a huge impact on how well your model fits. And that's the same here with the 1024 also. This is also another number that if you continue to raise that number, you'll get possibly a better fit. You might overfit. And if you lower that number, you'll use less resources. And generally, you want to use this in the exponential growth. An exponential being 2, 4, 8, 16. And in this case, the next one down would be 5, 12. You can use any number there, but those would be the ideal numbers when you look at this data. So the next step in all this is we need to also create a way of tracking how good our model is. And we're going to call this a loss function. And so we're going to create a cross-entropy loss function. And so before we discuss exactly what that is, let's take a look and see what we're feeding it. We're going to feed it our labels, and we have our true labels and our prediction labels. So coming in here is where the two different variables we're sending in, or the two different probability distributions, is one that we know is true and what we think it's going to be. Now this function right here, when they talk about cross-entropy, in information theory, the cross-entropy between two probability distributions over the same underlying set of events measures the average number of bits needed to identify an event drawn from the set. That's a mouthful. Really, we're just looking at the amount of error in here. How many of these are correct and how many of these are incorrect? So how much of it matches? And we're going to look at that. We're just going to look at the average. That's what the mean, the reduced to the mean means here. So we're looking at the average error on this. And so the next step is we're going to take the error. We want to know our cross entropy, or our loss function, how much loss we have. That's going to be part of how we train the model. So when you know what the loss is and we're training it, you feed that back into the back propagation setup. And so we want to go ahead and optimize that. Here's our optimizer. We're going to create the optimizer using an atom optimizer. Remember, there's a lot of different ways of optimizing the data. Atom's the most popular used. So our optimizer is going to equal the TF train atom optimizer. If you don't remember what the learning rate is, let me just pop this back into here. Here's our learning rate. When you have your weights, you have all your weights in your different nodes that are coming out. Here's our node coming out, and it has all its weights. And then the error is being sent back through in reverse on our neural network. So we take this error and we adjust these weights based on the different formulas. In this case, the atom formula is what we're using. We don't want to just adjust them completely. We don't want to change this weight so it exactly fits the data coming through. Because if we made that kind of adjustment, it's going to be biased to whatever the last data we sent through is. Instead, we're going to multiply that by 0.001 and make a very small shift in this weight. So our delta W is only 0.001 of the actual delta W of the full change we're going to compute from the atom. And then we want to go ahead and train it. So our training, or set up a training variable or function. And this is going to equal our optimizer minimize cross entropy. And we make sure we go ahead and run this. So it's loaded in there. And then we're almost ready to train our model. But before we do that, we need to create one more variable in here. And we're going to create a variable to initialize all the global TF variables. And when we look at this, the TF global variable initializer, this is a TensorFlow object. It goes through there and it looks at all our different setup that we have going under our TensorFlow, and then initializes those variables. So It's kind of like a magic wand because it's all hidden in the back end of TensorFlow. All you need to know about this is that you have to have the initialization on there, which is an operation, and you have to run that once you have your setup going. So we'll go ahead and run this piece of code, and then we're going to go ahead and train our data. So let me run this so it's loaded up there. And so now we're going to go ahead and run the model by creating a graph session. Graph session is a TensorFlow term. So you'll see that coming up. It's one of the things that throws me because I always think of GraphX and Spark and graph as just general graphing. But they talk about a graph session. So we're going to go ahead and run the model. And let's go ahead and walk through this, what's going on here. And let's paste this data in here. And here we go. So we're going to start off with a TF session as ses. So that's our actual TF session that we've created. So we're right here with the TF session. Our session we're creating, we're going to run TF global variable initializer. So right off the bat, we're initializing our variables here. And then we have for I in range 500. So what's going on here, remember 500, we're going to break the data up and we're going to batch it in at 500 points each. We've created our session run, so we're going to do with TF session as session right here. We've created our variable session. And then we're going to run and we're going to go ahead and initialize it. So we have our TF global variables initializer that we created. That initializes our session in here. The next thing we're going to do is we're going to go for I in range of 500, batch equals ch.next batch. So if you remember correctly, this is loading up 100 pictures at a time. And this is going to loop through that 500 times. So we are literally doing, 500 times 100 is 50,000. So that's 50,000 pictures we're going to process right there. In the first process is we're going to do a session run. We're going to take our train. We created our train variable or optimizer in there. We're going to feed it the dictionary. We had our feed dictionary that we created. And we have x equals batch 0 coming in, y true, batch 1, hold the probability, 0.5. And then just so that we can keep track of what's going on, we're going to, every 100 steps, we're going to run a print. So currently on step, format, accuracy is, and we're going to look at matches equals tf argument y prediction 1, tf.arg max y true, comma 1. So we're going to look at this as how many matches it has. And here our ACC, all we're doing here is we're going to take the matches, how many matches they have, it generates a chart. We're going to convert that to float. That's what the TF cast does. And then we just want to know the average. We just want to know the average of the accuracy. And then we'll go ahead and print that out, print session run, accuracy, feed dictionary. So it takes all this and it prints out our accuracy on there. So let's go ahead and take this. Oops, flip screens there. Let's go ahead and take this and let's run it. And this is going to take a little bit to run. So let's see what happens on my old laptop. And we'll see here that we have our current, we're currently on step 0. It takes a little bit to get through the accuracy. And this will take just a moment to run. We can see that on our step 0, it has an accuracy of 0.1 or 0.1028. And as it's running, we'll go ahead, you don't need to watch it run all the way, but this accuracy is going to change a little bit up and down. So we've actually lost some accuracy during our step 2. But we'll see how that comes out. Let's come back after we run it all the way through and see how the different steps come out. I was actually reading that backwards. The way this works is the closer we get to 1, the more accuracy we have. So you can see here we've gone from a 0.1 to a 0.39, and we'll go ahead and pause this and come back and see what happens when we're done with the full run. Alright, now that we've prepared the meal, got it in the oven, and pulled out my finished dish here, if you've ever watched any of the old cooking shows, let's discuss a little bit about this accuracy going on here, and how do you interpret that? We've done a couple things. First, we've defined accuracy. The reason I got it backwards before is you have loss or accuracy. And with loss, you'll get a graph that looks like this. It goes, oops, that's an S, by the way. There we go. You get a graph that curves down like this. And with accuracy, you get a graph that curves up. This is how good it's doing. Now, in this case, 1 is supposed to be really good accuracy. That means it gets close to 1, but it never crosses 1. So if you have an accuracy of 1, that is phenomenal. In fact, that's pretty much unheard of. And the same thing with loss. If you have a loss of 0, that's also unheard of. And the 0 is actually on this axis right here as we go in there. So how do we interpret that? Because, if I was looking at this and I go, oh, 0.51, that's 51%. You're doing 50-50. No, this is not percentage. Let me just put that in there. It is not percentage. This is logarithmic. What that means is that 0.2 is twice as good as 0.1. And when we see 0.4, that's twice as good as 0.2. Real way to convert this into a percentage. You really can't say this is a direct percentage conversion. What you can do, though, is in your head, if we were to give this a percentage, we might look at this as 50%, we're just guessing, equals 0.1. And if 50% roughly equals 0.1, that's where we started up here at the top. Remember at the top here, here's our 0.1028. The accuracy of 50%, then 75% is about 0.2, and so on and so on. Don't quote those numbers because that doesn't work that way. They say that if you have 0.95, that's pretty much saying 100%. And if you have anywhere between, you'd have to go look this up. Let me go ahead and remove all my drawings there. So the magic number is 0.5. We really want to be over a 0.5 in this whole thing. And we have both 0.5004. Remember, this is accuracy. If we were looking at loss, then we would be looking the other way. But 0.05, instead of how high it is, we want how low it is. But with accuracy, being over a 0.5 is pretty valid. That means this is pretty solid. And if you get to a 0.95, then it's a direct correlation. That's what we're looking for here in these numbers. And you can see we finished with this model at 0.5135, so still good. And if we look at when they ran this in the other end, remember there's a lot of randomness that goes into it when we seed the weights. They got 0.5251, so a little better than ours. But that's fine. You'll find your own comes up a little bit better or worse depending on just that randomness. And so we've gone through the whole model. We trained the model, and we've also gone through on every 100th run to test the model to see how accurate it is. And now that we have a solid running model and an accuracy, let's go ahead and take a look at what we covered today. We did cover a lot because this is a very complicated subject, and it's not so much complicated in any individual step. It just has a lot of steps involved. So today we covered what is a convolutional neural network. And you can see we have the pictures coming in to the input layer, to the hidden layers, to the output layer, and then ordered rows. We talked about the very basics at the beginning. And we discussed how a CNN recognizes images. And very basics is we converted the image into a pixel map of zeros and ones. Then we dived into layers in a convolutional neural network. And we had our convolutional layer, our fully convected layer, our ReLU layer, and our pooling layer. And we looked at pooling layer. It reduces the data down to a smaller amount by finding the, first it finds the matches, and then it finds the maximum value in that match. And we discussed all the different layers in there. We went into the fully connected layer, which is the neural networks you're probably used to dealing with, where we're just building a forward propagation neural network. And we connected them all together. And you can see here, we took the bird, we did our feature extraction in multiple hidden layers, where we had our convolution, which then generated those little individual filters, and we had our ReLU, and then we took the ReLU, we max pooled those, and then we took all of those pooled values at the end, so they've been reduced to smaller mappings. We've reduced that, and then we fed that into the fully connected layer. And then finally, we went into the use case implementation using CNN, and we walked through a full demo on the coding on there. With that, I want to thank you for joining us today.
Today, we are diving into machine learning, the technology behind things like Netflix recommendations, Siri, and even the face unlock of your phone. Machine learning helps devices get smarter by learning from data and predicting what we might like or need. And here's why machine learning is huge for your career. Right now, machine learning jobs are among the fastest growing roles worldwide. Companies in every industry, tech, healthcare, finance, and more, are looking for people with machine learning skills to improve their products, automate tasks, and make smarter decisions. Machine learning engineers in the US earn around $112,000 on average, with plenty of room for growth as you gain experience. So if you want to jump into this exciting field, learning machine learning can open doors to high-paying, in-demand jobs. So in this video,
I'll guide you through the ultimate roadmap to master machine learning in 2025, one step at a time. So let's get started. So in the first month, start with the foundations of programming. So programming is a language you'll use to communicate with your computer and bring machine learning algorithms to life. So this month is all about Python, the language of choice for most machine learning practitioners. So here's what to focus on. First, learn Python basics. Begin with Python's fundamentals like variables, data types, loops, and functions. So spend time writing small programs daily to get comfortable. After that, explore the key libraries like NumPy, Pandas, and scikit-learn. So NumPy is for numerical operations. It makes handling large datasets faster and easier. And Pandas is to manipulate and analyze data. So Pandas allow you to filter, sort, and reshape data in a breeze. And then scikit-learn is for implementing algorithms in just a few lines of code. So now you might have heard about R, another language used in machine learning. But don't stress about it now. Python will serve you well, especially as a beginner, because it's simpler and more flexible. So aim to spend an hour or two each day coding. By the end of this month, you'll have a solid base to build on. Now in the second month, get organized with version control and data structures. So this month is about learning how to organize and manage your code effectively and sharpening your problem-solving skills with data structures and algorithms. So first is version control with Git. So think of Git as your project history tracker. So imagine working on a big project and making changes, then realizing something went wrong. You want to go back to an earlier version, right? So that's where Git comes in. And here's what you should practice. Number one is committing changes. So save different versions of your work as you progress. And then branching, which means work on separate features without affecting your main code. And then comes merging, which means combining changes from different versions once they are ready. So you have to set up an account on GitHub or GitLab to store your projects online. So not only will this be super useful, but it'll also start building your portfolio. Now next is data structures and algorithm. So think of data structures like tools in a toolkit. So each one like arrays, stacks, queues, etc. serves a specific purpose. So here's how to approach them. Number one, arrays and lists. Now arrays and lists are for storing data in sequence. After that, you can get familiar with stacks and queues. So stacks and queues are for tasks that need ordered data access. And then you have sorting and searching algorithms. So these make your programs more efficient. And that's super important in machine learning where data can get massive. So the goal here is to build up your problem solving skills, which are key to machine learning success. So take it slow, practice daily, and you'll see progress. Now in the third month, learn to access data with SQL. So in machine learning, a lot of work involves accessing and organizing data from databases. So SQL, a structured query language, is your ticket to getting the data you need for training ML models. So here's what you should focus on. Select and where. So these commands help you pull specific pieces of data. And then you can move on to joins. Joins usually combine data from different tables. So this is so powerful that you'll use it all the time. And then comes group by and aggregate functions. They are great for summarizing data to find patterns. So spend time working with sample databases you can find online and practice writing queries. Being comfortable with SQL will save you time when preparing data for your models. Now, after completing the third month, you can move on to mathematics, which is building your analytical mind. So this month, we are tackling the math behind machine learning. So don't worry, you don't need to be a math genius, but understanding certain concepts will make everything feel less mysterious. So in this month, you have to focus on linear algebra. So this is the math behind how models see data. So you can study vectors, matrices, and operations like multiplication. Next comes calculus. So you'll use calculus to help your models learn. So you have to focus on derivatives and gradients, which help minimize errors in your model. And then you can move on to probability and statistics. So understanding probability helps you make sense of data. So learn about distributions like normal distribution, binomial distribution, and then variance and standard deviation. So once you have learned maths, next you'll be moving on to data handling and visualization, which is the heart of machine learning, as you all know. So with math under your belt, it's time to dig into data handling and visualization. So data preparation is vital because your model is only as good as the data you feed it. So number one comes data manipulation. So using pandas and NumPy, you'll clean and organize your data. You might be removing missing values, like clean up messy data so it doesn't confuse your model. And then you will learn transforming variables, like converting data into formats that work for models. And then you will move on to encoding categorical data, like changing text data, like female or male into numbers. Now, once you're done with data manipulation, next comes data visualization. So visualization is how you get to see your data before training a model. So here you have to learn Matplotlib and Seaborn. So you can create line charts, histograms, scatter plots, and heat maps. So this lets you explore patterns and spot outliers. So understanding these patterns in your data is crucial for building effective models. Now, in the 6th month, you will be moving on to the machine learning fundamentals. So now it's time to start building your own models. So you will focus on two main types of machine learning this month. Number one comes the supervised learning. So this is when you train a model on labeled data, where the outcome is already known. So you'll work with algorithms like linear regression, which predicts a continuous outcome. Then you will work with decision trees, which breaks down decisions into a tree structure. And then you have support vector machines under supervised learning, which separates data into classes. Now, after supervised learning comes unsupervised learning. So here your model identifies patterns in data without labeled outcomes. So two popular techniques in unsupervised learning is number one, clustering, like K-means clustering, which means group similar data points. And then you have dimensionality reduction. This reduces data complexity by focusing on key features. So you can use scikit-learn to try out these algorithms on sample data sets. So this will give you hands-on experience with model training, and you will learn to fine-tune them to get better results. Now, before moving on, if you are interested in advancing your career in the field of AI and machine learning, Simplilearn's postgraduate program, delivered in collaboration with Purdue University and IBM, is a perfect opportunity. This highly ranked program offers a comprehensive curriculum covering essential topics like machine learning, deep learning, NLP, computer vision, reinforcement learning, generative AI, prompt engineering, and many more. With hands-on experience to 25 plus projects and access to 20 plus cutting-edge tools, you will gain the skills needed to excel in today's competitive job market. So join now and elevate your expertise with the backing of Purdue's academic excellence and IBM's industry-leading insights. You can find the course link in the description box and pinned comments. Now moving on to the 7th month, you'll be building and training models with advanced libraries. So by now you have experimented with some basic models. So let's step it up with advanced tools like TensorFlow and PyTorch. So these libraries offer more flexibility and power. So TensorFlow and PyTorch, so here you can start with simple models and work your way up. So these libraries allow for building neural networks, which you'll be studying more on the next month. Now, once you have become familiar with TensorFlow and PyTorch, you can move on to model training and evaluation. So you have to learn to split data into training and testing sets and evaluate models using metrics like accuracy and precision. So your goal this month should be to get comfortable with these libraries and understand how they handle data and model training behind the scenes. So once you are done with this, you'll be moving on to the 8th month, where you'll be dealing with advanced machine learning. So this month's concept will be number one on ensemble learning, which means combining multiple models to get better predictions. So here you'll be learning about bagging. For example, random forests. Here multiple decision trees make predictions. And then you have boosting, like AdaBoost, XGBoost. So models learn from each other's mistakes over here. And after ensemble learning comes deep learning. So here you explore neural networks which mimic the human brain. So you'll learn about neural network basics. So you can start with simple, fully connected networks, and then you can move on to backpropagation and gradient descent. So these helps your model learn and improve. So you can use TensorFlow or PyTorch to practice building neural networks. So you can work on projects to reinforce these concepts. Now moving on, you have to specialize on topics like NLP and computer vision. So machine learning applications are so powerful, and here you'll get a taste of two major fields, which is NLP or natural language processing. So here they work with text data for tasks like sentiment analysis and text classification. So you can start with basic pre-processing like tokenization, stop word removal, and move to building simple NLP models. After that, you can try out computer vision. So for image data, you have to learn CNNs, convolutional neural networks. So these networks analyze visual patterns, making them ideal for image classification. So you practice with open data sets like text, documents, or images, and apply the concepts you will learn to see results in real-world applications. Now in the 10th month, you'll be dealing with model deployment, which is bringing your models to life. So here you'll be using Flask or Django. So you can use these frameworks to create a web API so users can interact with your model. For example, build a web app that lets people upload images for classification. And then you can also try out Docker. So package your model and its dependencies so it can run on any machine. So this is super helpful for deploying models without compatibility issues. So by the end of this month, you will be able to share your models with the world. So moving on to the 11th month, you'll be starting with cloud and production. So this month, you'll learn how to deploy models on the cloud and ensure they perform well in real-world environments. So you'll be dealing with cloud platforms like AWS, Google Cloud, or Azure. So you have to learn to deploy models on the cloud for wider accessibility and scalability. And then comes monitoring and maintenance. So understand how to track your model's performance over time and update it as needed. So these skills are essential for maintaining models in production and ensuring they stay reliable. And finally, you will be creating real-world projects and portfolio building. So here you have to choose topics that interest you and showcase your skills. So first you can start with full projects. So complete projects that go from data cleaning and model building to deployment. So ideas could be a sentiment analysis tool or an image recognition app. And then you have to build your portfolio. So organize and document your projects, host them on GitHub, and create an online portfolio to share with potential employers or collaborators. So by following this roadmap, you'll be well prepared to handle real-world machine learning challenges and have an impressive portfolio to show for it. So thank you so much for joining me on this ultimate roadmap to mastering machine learning in 2025. I hope this month-by-month guide gives you a clear, achievable path to dive into machine learning, from the basics to deploying your own models. Remember, learning machine learning is a journey. There will be challenges along the way, but with patience and consistent practice, you'll see progress step by step.
Do you know, friends, that according to the lending statistics, the demand for AI and ML specialists is projected to surge by 40% between 2023 to 2027. And on an average, an ML engineer is expected to earn around $133 and $336 per year. So if you are an aspiring ML engineer and thinking about what innovative projects you can show in your portfolio, then your wait is over. Because in this video, I'll be covering 8 amazing ML projects that you can showcase in your resume. So guys, let's start first with a beginner level project. And the first project that we are going to encounter, that is home value prediction. So guys, this project aims to develop a predictive model to estimate the value of residential properties. The model will analyze various features such as location, square, footage, number of bedrooms and bathrooms, age of the property, and other relevant factors. By leveraging historical property data, the model will be able to provide accurate home value predictions, which can be useful for real estate agents, buyers, and sellers. So guys, the programming language that we are going to use all over here will be Python, and machine learning libraries that we will be using will be scikit-learn, TensorFlow, Keras, and for data handling libraries, we have Pandas, NumPy, and for visualization, we have to use Matplotlib and Seaborn. Now, what will be the approach for this one, guys? So guys, the first one that we have a data collection. So here, what is going to happen, guys? So first you have to collect the historical property data from the sources like Zillow, retailer.com. You can also get database from the public real estate databases like Kaggle datasets, where you have Zillow home value prediction. Ensure that the dataset include features like location, where you have latitude, longitude, square footage, number of rooms, year built, property type, and previous sales. The next step that comes is data cleaning. You have to handle the missing values by using imputation techniques or removing incomplete records, removing outliers that may skew the model's prediction, normalize or standardize the data to ensure consistency. The third one that we have is feature engineering. You have to create new features such as proximity to schools, crime rates, and access to the public transportation. Encode categorical variables, example property type, location, using techniques like one-hot encoding. Generate interaction features that capture relationship between existing features. The fourth one that we have is model selection. Use regression models like linear regression, random forest, gradient boosting, neural networks. Experiment with different models to identify the best performing one. Now, in the next phase, all you have to do, guys, is model training and evaluation. Split the data set into training and test sets. Train the model on the training set and evaluate their performance on the testing set using metrics like RSME, which means root mean squared error. You can use cross-validation to ensure the model's robustness and avoid overfitting. The sixth one that we have all over here is hyperparameter tuning. You can optimize the model's hyperparameter using techniques such as grid search or random search to improve accuracy. And if you're looking forward to deploy your model, then you can develop a web interface using Flask or Django to allow users to input property features and get predictions. You can deploy the model on the cloud platform like AWS for scalability. Now, if we talk about the complexity level of this, we all know that it is a beginner level project. Now let us move on to the one more set, that is music genre classification and generation. So guys, this is also one of the most beginner level project. This project aims to develop a system that can classify music tracks into different genres and generate new music composition within specified genre. The goal is to build a model that analyzes audio features to categorize music and uses deep learning techniques to create new music. This project introduces advanced concept of audio processing, deep learning, and generative models. So guys, what will be used in this? So we'll have programming language, that will be Python. For audio processing, we'll be using librosa. For machine learning libraries, we'll be using TensorFlow, Keras, PyTorch. For data handling libraries, we'll be using Pandas, NumPy. For visualization, we'll be using Matplotlib, Seaborn. For the dataset, guys, you can use GTZan music genre dataset, or you can get it from Free Music Archive. So guys, in the first phase, we are going to have data collection. You can obtain datasets containing music tracks and their corresponding genre from the sources, from GTZan music genre dataset and the Free Music Archive. Ensure that a dataset includes diverse genre and substantial number of tracks per genre. Next, we'll go for data preprocessing. Use library librosa to load and preprocess audio files, including feature extractions such as mil frequency, cepstral coefficients, chroma features, and spectral contrast. You can normalize the extracted features to ensure consistent input for the given models. Now, if we talk about feature engineering, guys, you can extract additional features from the audio files such as tempo, beat, zero crossing rate, etc. Create a feature matrix that represents the extracted audio features. Then go for the model selection. Use convolutional neural network or recurrent neural networks for the music genre classification. Split the dataset into training and testing dataset. Now, if we talk about model training and evaluation, guys, then you can train the selected classification model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use confusion matrices to understand the classification performance across different genres. Now, if we talk about model selection and training for the music generation, what you will do, guys, you can use the generative adversarial networks or recurrent neural networks such as LSTM, long short-term memory for music generation. Train the generative model on the dataset to create new music sequences. Next, we have model training and evaluation. You can train the generative model on sequences of audio features. You can evaluate the generated music by listening tests and by objective metrics like inception score or Friese audio distance. If I talk about hyperparameter tuning, guys, you can optimize the model. You can use the hyperparameters using techniques like grid search or random search to improve performance. If I talk about deployment, guys, you can deploy these models on cloud platforms like AWS. Now, let us move on to our next project. So guys, the complexity of this project is at the beginner level. Now, let us move to the intermediate level projects. Next project that we have all over here is sentiment analysis of Twitter data. This project aims to develop a sentiment analysis model that can classify tweets as positive, negative, or neutral. The goal is to analyze public sentiment on various topics or events using natural language techniques. So guys, what will be used all over here? So in this, we will have programming language like Python, okay, NLP libraries, NLTK Spacey. For machine learning libraries, you can use scikit-learn, TensorFlow, Keras. For data handling libraries, we have Pandas, NumPy. For visualization, we have Matplotlib, Seaborn, and we can use the API Twitter for data collection. Now, how you're going to work on it, guys? So guys, if I talk about the data collection, use a Twitter API to collect tweets based on specific hashtags like keywords or topics. Extract relevant fields like tweet text, user information, timestamp, etc. Then if I talk about data preprocessing, guys, clean the tweet text by removing special characters, links, mentions, hashtags, and stop words. Tokenize the text and perform lemmaization or stemming to reduce the words to their base form. Next, if we talk about feature engineering, guys, you convert the clean text data into numerical representation using TF-IDF, bag of words, or word embedding. Now, if I talk about model selection, guys, you can choose the classification algorithms such as logistic regression, Naive Bayes, or LSTM. Split the data set into training and testing data set. Now, if I talk about model training and evaluation, then you can train the selected model on the training set. Evaluate the model's performance on the testing set using metrics like accuracy, precision, recall, and F1 score. Use cross-validation to ensure the model's robustness. If I talk about hyperparameter tuning, guys, you can optimize the model's hyperparameters using grid search or random search to improve the performance. For deployment, which can be optional, you can deploy your model on AWS for real-time sentiment analysis. So if I talk about the complexity level, guys, its complexity is intermediate. So guys, our next project is customer segmentation using k-means clustering. This project aims to segment customers into distinct groups based on their purchasing behavior and demographic information. The objective is to understand customer segments and tailor marketing strategies accordingly. So guys, what programming languages we'll be using? So basically, we'll be using Python. For machine learning libraries, we'll have scikit-learn. For data handling libraries, we'll have pandas, numpy. For visualization libraries, we'll have matplotlib, seaborn. And the dataset source will be e-commerce transaction data. How we are going to work on this one? For data collection, we can obtain a dataset of e-commerce transactions that include customer demographics, purchase history, and product information. Next, we'll have data pre-processing. For data pre-processing, we are going to do the cleaning of the data by handling the missing values and outliers. Then, for feature engineering, we are going to create features like total purchase amount, purchase frequency, and recency of the purchases. Then we are going to proceed for the model selection. You can use k-means clustering to segment the customers into distinct groups. You can determine the optimal number of clusters using methods like elbow methods or Silhouette score. Now, if I talk about model training and evaluation, you can train the k-means model on the processed dataset. You can evaluate the quality of clusters by analyzing intra-cluster and inter-cluster distances. Next, we have the evaluation. You can visualize the clusters using techniques like PCA, principal component analysis, TSNE, etc. Next, we have the hyperparameter tuning. Now you can tune this model and interpret the characteristic of each segment. You can develop a target marketing strategies for each segment based on unique behavior and preferences. Now, deployment is optional. You can develop a dashboard using Flask or Django to visualize customer segments and track marketing campaigns. So guys, if I talk about the complexity of this project, so this is an intermediate level project. So guys, for dataset, you can use the Kaggle's customer segmentation dataset, which is available at the Kaggle's platform. Now, the third intermediate level project that we have all over here is building a chatbot with Rasa. This project aims to build an intelligent chatbot using Rasa framework. The chatbot will be capable of understanding user queries and providing appropriate responses, making it useful for customer support, personal assistance, or information retrieval. What languages we are going to use? So it will be Python based. We'll have the NLP libraries like Rasa, NLTK, Spacey. For machine learning libraries, we are going to have scikit-learn, TensorFlow, Keras, etc. For data handling libraries, we are going to use pandas, numpy. So guys, this was what we are going to do it. And how you can work on this one? By collecting the data, collect the conversation data and FAQs from the target domain. Annotate the data to create training examples for the chatbot. Next comes is data pre-processing. Clean the text data by removing special characters and normalizing the text. You can tokenize and limitize the text to prepare for a training. The third one, we have the models training. You can use Rasa's NLU's component to train a model for intent recognition and entity extraction. You can define the dialogue management policies to handle different conversation flows. Next, guys, you can perform the feature engineering and integration. You can integrate the Rasa's NLU and core components to build complete chatbot. You can connect the chatbot to messaging platform like Facebook, Messenger, etc. For model selection and testing, what you can do, guys, you can test this chatbot with various inputs to ensure that it handles the scenarios appropriately. And you can also select the right model using this. Now, if I talk about model training, guys, what do you have to do? You have to collect the user feedback and conversational logs to continuously work on training the model. Next, similarly, you have to retrain the model periodically with the new data to see how it is working. So that will be your evaluation. Now, for the hyperparameter tuning, what are you going to do, guys? You have to check in those scenarios where it is able to tune up with those scenarios where it can handle the input appropriately. And next is deployment. So guys, for deploying it, you can use AWS. So guys, for a data set, you can use Rasa's open source. So that's a very good data set for you to proceed. So guys, if you talk about difficulty of this project, this is an intermediate level project. Now let us move on to the advanced level projects. For advanced level projects, the first one that comes up to my mind is movie similarity from plot summaries. Now, this project aims to develop a system that can find out recommended movies similar to a given movie based on their plot summaries. By analyzing the textual content of the movie, plot summaries, the model will identify similarities and suggest movies with similar themes, storylines, or genres. This project introduces beginners to natural language processing, text similarly measures, and recommendation systems. What languages we are going to use, guys? We'll be using Python, NLP libraries like NLTK, Spacey, machine learning libraries like scikit-learn, data handling libraries like pandas, numpy, visualization we can use numpy, and dataset source will be IMDb or Kaggle. So guys, this process is also involving the data collection, then you have to go for data cleaning, then feature engineering, next model selection. So similar process as I have discussed in other projects, so you have to also go through the same one. Next, what do you have to do, guys? Similarly, what do you have to do? You have to train the model, then evaluate the model, then hypertune it, and finally proceed for the deployment. So this is overall process of this project. Try to research on the website a lot, like how you can extract it. So guys, you can use Kaggle or Towards Data Science to research more about this project. Now guys, if I talk about the difficulty of this project, then this is an advanced level project. Now, let us move on to the next one that we have all over here. That is image segmentation project for brain tumor prognosis. This is a very amazing project and definitely you can put up on your portfolio. Basically guys, this project aims to develop an image segmentation model to identify and delineate brain tumors from MRI scans. The goal is to accurately segment the tumor regions which can aid in prognosis, treatment planning, surgical interventions. This project introduces intermediate level concepts of computer vision, deep learning and medical image analysis. So guys, what we'll be using all over here? For programming languages, we can use Python. For deep learning libraries, we can use TensorFlow, Keras, PyTorch. For image processing libraries, we can use OpenCV, scikit-image. For data handling libraries, we can use Pandas, NumPy. For visualization, we can use Matplotlib, Seaborn. Now, if I talk about what is the process of developing this project, the first step will be the same, data collection. So next step, you have to go for data pre-processing. Third step, you have to do the model selection where you can use CNN models for image segmentation task. Then you go for model selection. Moving ahead, you're going to have the model training and evaluation. You have to split the data set into training and validation and testing data sets. Next, proceed for the evaluation phase. Okay, evaluate the model with certain metrics. So here I can give you certain idea like you can use dice coefficient, intersection over union or accuracy. Then go for hyperparameter tuning where you have to optimize the model's hyperparameters. You can use grid search or random search as we have discussed. And finally, you can deploy this model on AWS. Now guys, we have come to the final project. This is also a very amazing project guys. So guys, the complexity level of this project is advanced level. Now, let us move on to our final project. That is the impact of climate change on birds. This is a very amazing project and definitely you can add it on your resume. This project aims to analyze the impact of climate change on the bird population and migration patterns. By examining various climatic factors and their correlation with bird species data, the project seeks to predict how climate change might affect bird behavior and distribution. This project will introduce you some advanced level concepts like time series analysis, environmental data modeling, etc. So guys, what programming languages we'll be using? For data analysis, you can see we'll have Pandas, NumPy. For machine learning libraries, we are going to have scikit-learn, TensorFlow. For visualization, we are going to have Matplotlib, Plotly. For geospatial, we are going to have GeoPandas, Folium. For data source, we're going to have public data sets on bird observation and climate data sources from eBird. Now, what will the process flow for this one, guys? First, you have to proceed for data collection. Gather bird observation from the data like eBird, which provides extensive record of bird sightings. Okay, and for climate data, you can collect it from NOAA, including temperature, precipitation, and other relevant climatic factors over the time. And similar next process will be the data pre-processing. Then you have to proceed for feature engineering. Then you have to go for model selection. Okay, moving ahead, you have to go for model training, then evaluation, then hyperparameter tuning, and finally, you have to deploy the model. So research about this project, see what models you are going to use. Suppose I can give you a hint about this. You can use time series analysis models like ARIMA, or ML models. You can also use random forest or gradient boosting for predicting impact on the bird population. So guys, use Google exhaustively to research about this project. This is also a very amazing project and it's going to give you a lot of idea. Now, if I talk about the complexity level of this, It is an advanced level project.
Today's video, we are diving deep into the world of machine learning interview preparation. As we gear up for 2024, it's crucial to be well prepared for the questions that can come your way in any machine learning interview. We have compiled 30 essential interview questions and answers, thoughtfully categorized into beginner, intermediate, and advanced levels. So let's start with beginner level questions, and number one is, what is machine learning? So machine learning is a subset of artificial intelligence that involves the use of algorithms and statistical models to enable computers to perform tasks without explicit instructions, that is by relying on patterns and inference. And now moving to number second question, that is, what are the different types of machine learning? So the three main types of machine learning are, number one is supervised learning, and then comes unsupervised learning, and then there is reinforcement learning. Now moving to next question, that is third, that is, what is supervised learning? So supervised learning involves training a model on a labeled dataset, which means each training example is paired with an output label. The model learns to predict the output from the input data. Now moving to the fourth question, that is, what is unsupervised learning? So unsupervised involve training a model on data that does not have labeled responses. The model tries to learn the patterns and the structure from the input data. So guys, these are the beginner level questions, and now we'll move to the fifth question, that is, what is reinforcement learning? So reinforcement learning is a type of machine learning where an agent learns to make decisions by performing actions and receiving rewards or penalties. The goal is to maximize the cumulative reward. So now moving to the sixth question, that is, what is a model in machine learning? So a model in machine learning is a mathematical representation of a real-world process. It is trained on data to recognize patterns and make predictions or decisions based on new data. So now moving to seventh question, that is, what is overfitting? So overfitting occurs when a machine learning model performs well on the training data but poorly on new unseen data. It indicates that the model has learned the noise and details in the training data instead of the actual patterns. So now coming to question number 8, that is, what is underfitting? So underfitting occurs when a machine learning model is too simple to capture the underlying patterns in the data. It performs poorly on both the training data and new data. Now moving to the next question, that is ninth question, and the question is, what is a confusion matrix? So confusion matrix is a table used to evaluate the performance of a classification model. It summarizes the number of correct and incorrect predictions made by the model, and that is categorized by each class. Now moving to the 10th question, that is, what is cross validation? So cross validation is a technique for assessing how the results of a statistical analysis will generalize to an independent dataset. It involves partitioning the data into subsets, training the model on some subsets and validating it on the remaining subsets. So this was all about, that is, the 10th question or the overall 1 to 10 questions for beginner level. Now we'll move to intermediate level, and here we'll cover 10 questions. So we'll start with 11th question, that is, what is a ROC curve? So ROC, that is, receiver operating characteristic curve. It is a graphical representation of a classifier's performance across different thresholds. It plots the true positive rate, that is TPR, against a false positive rate, that is FPR. Now moving to 12th question, that is, what is precision and recall? So precision is the ratio of correctly predicted positive observations to the total predicted positives. And recall is the ratio of correctly predicted positive observations to all actual positives. So the formula is precision equal to TP slash TP plus FP, and the recall is TP slash TP plus FN. So now we'll move to the 13th question, that is, what is the F1 score? So the F1 score is the harmonic mean of precision and recall. It provides a balance between the two metrics and is useful when you need to balance precision and recall. F1 score is equal to twice into precision into recall, and that is divided by precision plus recall. Now we'll move to 14th question, and here we will cover regularization. So the question is, what is regularization? So it is a technique used to prevent overfitting by adding a penalty to the model's complexity. And the common types of regularization include L1, that is lasso, and L2, ridge regularization. Now we'll move to the 15th question, that is, what is the bias variance trade-off. So the bias variance trade-off is a fundamental issue in machine learning that involves balancing the error introduced by the model's assumptions and the error due to model complexity. So a good model should have low bias and low variance. Now we'll move to the question number 16, that is what is feature engineering. So feature engineering is the process of creating new features or modifying existing ones to improve the performance of a machine learning model. It involves techniques like normalization, encoding categorical variables, and creating interaction terms. So now we'll move to question number 17, and that is about gradient descent. So the question is, what is gradient descent? And your answer is, gradient descent is an optimization algorithm used to minimize the cost function in machine learning models. And it iteratively adjusts the model parameters in the direction of the steepest descent of the cost function. So with this, we'll move to the 18th question, and that will cover with the difference between bagging and boosting. So the question is, what is difference between bagging and boosting? And you could answer this with starting with bagging, that is bootstrap aggregating. That involves training multiple models on different subsets of the data and averaging their predictions. Then comes boosting, that involves training models sequentially with each new model focusing on correcting the errors of the previous ones. And then we have the question number 19, that is what is a decision tree? So a decision tree is a non-parametric supervised learning algorithm used for classification and regression. It splits the data into subsets based on the value of input features, resulting in a tree-like structure of decisions. Now we'll move to question number 20, that is what is a random forest. So random forest is an ensemble learning method that combines multiple decision trees to improve the accuracy and robustness of the model. It builds each tree using a random subset of features and data points and then averages their predictions. So these were the questions that are for the intermediate level, and these are just the basic questions, or I will just say the theoretical questions that can be asked in an interview. So be prepared for that. Now we'll move to the advanced level interview questions, and we'll start with question number 21, and here also we'll cover the 10 questions. So number one question, or that is 21st question, and the question is, what is a support vector machine? So support vector machine is a supervised learning algorithm used for classification and regression. It finds the optimal hyperplane that maximizes the margin between different classes in the feature space. And then comes question number 22, that is what is principal component analysis. So principal component analysis is a dimensionality reduction technique that transforms high dimensional data into a lower dimensional space by finding the directions, that is principal components that maximize the variance in the data. And then comes the question number 23, that is what is a neural network. So a neural network is a series of algorithms that attempt to recognize underlying relationships in a set of data through a process that mimics the way the human brain operates. It consists of layer of interconnected nodes or neurons. And then comes the question number 24, that is what is deep learning. So deep learning is a subset of machine learning that involves neural networks with many layers, that is deep neural networks, and it is particularly effective for tasks like image and speech recognition. Now I'll move to question number 25, that is what is convolutional neural network, that is CNN. So we will start the answer by answering the interviewer that a convolutional neural network is a type of deep learning model specifically designed for processing structured grid data like images. It uses convolutional layers to extract spatial features or the spatial features and patterns from the input data. Now we'll move to the question number 26, that is what is a recurrent neural network or RNN. So a recurrent neural network is a type of neural network designed for sequential data, and it has connections that form directed cycles, allowing it to maintain a memory of previous inputs and process sequences of data. So this was all about question number 26, and now we will cover the question number 27, that is what is the difference between batch gradient descent and stochastic gradient descent. So batch gradient descent computes the gradient of the cost function using the entire training dataset, while stochastic gradient descent, that is SGD, computes the gradient using only one training example at a time. So SGD is faster but noisier. Now we'll move to question number 28, that is what is dropout in neural networks. So dropout is a regularization technique used in neural networks to prevent overfitting. and it involves randomly setting a fraction of the neurons to 0 during training, forcing the network to learn more robust features. And now we'll move to question number 29, and that will be about transfer learning. And your question is, what is transfer learning? So we'll answer this to the interviewer by starting that transfer learning is a technique in machine learning where a model developed for one task is reused as the starting point for a model on a second related task. It is particularly useful when there is limited data available for the second task. Now we'll move to the last question and the 30th question. So that is, what is a generative adversarial network? That is GAN. So you can start answering this. So generative adversarial network is a type of deep learning model consisting of two neural networks, a generator and a discriminator, that are trained simultaneously. The generator creates fake data while the discriminator tries to distinguish between real and fake data, leading to the generator producing increasingly realistic data. And these questions and answers are over, and these covers a wide range of topics in machine learning and should help prepare for interviews at various levels.
Come to the end of a full course. Thank you for joining Simplilearn's course on machine learning. We hope you enjoyed learning about this powerful technology and its many uses. If you found this video helpful, do appreciate with a thumbs up and subscribe for more such content by Simplilearn. Thank you and keep learning. Hi there, if you like this video, subscribe to Simplilearn YouTube channel and click here to watch similar videos. To nerd up and get certified, you can check the description box below.